Mais um, dois, C, E, A, C, O, E, A. O, E, A, E, E. Não. E. Mais um, dois, C, E, A, C. Mais um, dois, C, E, C, E, A, C. Mais um, dois, C, E, A, C, O. Okay?
Oh.
And this is not normal, okay? It's not
Yeah.
supposed to be happening. See, this one
Yes, yes. One.
The Dynamic Language Symposium. Also everybody in the back row. Octave, thank you. So you might have noticed this year's DLS is slightly different. We have basically only invited talks. The idea was we have now roughly the 20s, it's actually the 19th year of DLS running, and we want to not do a look back, but a look forward. So I don't know whether any of you remember where you were about 20 years ago. 20 years ago, I basically was in the first weeks of university, started studying computer science, felt math was never as hard before. I was always good at math, but then suddenly in university, that was a very different ball game. So I don't think 20 years ago I could have imagined where we are today in terms of computer science, mostly because I didn't know anything. But I gave the brief to the speakers to imagine where we want to be in 20 years. So looking forward, trying to anticipate the big problems we want to have solved in 20 years and how to get there. So I hope we are going to hear some interesting ideas a little bit of vision, because if I kind of look back how we got here, 20 years long research, I don't think there were all that many paradigm shifts the last 20 years. Maybe that can change, maybe can bigger jumps forward. So no pressure, Walter.
No, absolutely.
Please take it from here.
Okay, thank you, Stefan, for the introduction, also for the invitation. I don't know if I'm going to show something big problem, but at least I will try to explain what is my vision and where we can go in the future. Maybe not in 20 years, but in 10 years or 5 years.
Maybe you have to speak on the microphone.
Yeah. Maybe I have just to move it in front. Okay, so my talk should be about polyglot programming. Maybe this is a new term, I don't know. But anyway, it's something that is real at the moment. Polyglot programming is the practice that often we have to write a program using several languages, not just one. This is pretty well defined. But the point is, why we want to do that? Yeah, there are several reasons. The most popular is the fact that something is more efficient. Some languages are more efficient than others, especially if they are compiled, and others are more simple to use than the others. So this is normally when you are thinking of C, that is way more efficient than Python, but Python is way more easy to write code in. And so one reason could be this one, but it's not the only one. Others are just because they are not fully fledged languages, like, for example, CUDA or SQL, and they need to be hosted in another language. Still, this is quite diffuse. If you look at GitHub and you search for two languages, there are several repositories that are using two languages, more than two languages also. Some notable cases are OpenJDK. OpenJDK is written in C, C++, and Java. The same is for TensorFlow, that has three languages inside, C, C++, Java, and Python, and also CPython, C and Python, and many, many others. If you are thinking, well, you are surely using something that has been written using several languages. So it is real. It's a real thing, and maybe all of us are doing this. Okay, I tried to figure out how they are classified. Since the things is real, what is really needed is to understand how it's real. So the first category that I spotted is the embedded languages. This is the easiest one. For example, this is C, but C has some keywords that permits to include assembler code inside. You note the ASM one, the one with the frame around, the piece of code between the braces are just a piece of assembler code. This is called assembler templates because they are interacting with the rest of the C through templates. Those percentage symbols are indicating some parameters that are taken from the environment. And this is one example. This is more popular, probably. This is a HTML page, but all HTML pages nowadays have at least a script in it. This is written in a different language, in this case JavaScript, and it is clear where it is the code because you have some special keyword, in this case script, and then the type of the script, and in there is the code. And last but not least, this is quite famous, you have SQL. SQL is not really a full-fledged language, so it needs another language in order to do its stuff. And this is C with a piece of SQL. Still, the common point in all of this is that there is a keyword, a function, something that clearly states, okay, from this on, the code is written in a different language. In this case, is exec SQL. In the other case, is the script keyword or the ISM keyword. Okay, this is the first category. The difficulties in this case is how things work together. So if you have data that have to pass from one language to the other, there should be some support from the runtime environment or from the compiler that is doing the magic. Second one is more smoothly in some sense because we have two languages, but they are sharing a lot of the architecture, so the things are working together smoothly. And this is, for example, the case of JRuby. JRuby in Java. JRuby is an implementation of Ruby for the JVM. And it is clearly working on top of that, and behind there is bytecode at the end, so they can smoothly work together. And this is exactly the case. We have one class called me that is defining something, and we have also an interface that is asking for something else to be defined. And in the Ruby part, we have exactly the use of this. The arrows are showing which part are you using, and what is interesting is that the two languages are so intertwined that you can extend, you can implement the interface. And this happens through the include. Call Java is a Ruby class, and you are using the iSpeaker interface, and then you can implement the method that is asked for. And this is all smoothly. And this is another example. We are speaking of Scala and Java. We are still in the context of the JVM, bytecode, and whatever. So the things is still the same. And in the top part, we have the Scala piece of code, where we are defining a companion object that is a sort of a class with a singleton for the things. And we have a set of methods, instance methods, or class methods, and these in Scala can be accessed. Also those that are have the same name, the static one, depending on how you call it, you call that. From Java, you can call it as well, but there are some limitations because the companion object is a static class, but is not anymore a Java class, and it is not overshadowing the hello method, so the second method is not callable. At least I don't know how to call it. At some point, there was some tricky that I was going to use some internal definition of Scala, but they are not working anymore. But still, this is a good compromise. You have something that is not available in Java, but you can still use it because of the interconnection with the Scala environment. Okay, third kind, this is the most common, probably any of you already saw that, are the use of bindings. So basically, we have to write some piece of code that permits the people, the two languages to speak. And this permits also to have a different environment that is cool, but also you can have interpreted the languages with compiled languages. This is Java again, you probably know the GNI, the Java Native Interface. This permits to have a piece of code written in C or C++, and you can call this through Java. And also the vice versa, with some limitation. Okay, how it works, you have the Java piece of code that wants to use the GNI, and you have to define which is this method. In this case, it's say hello. And we specify that this is native, so that it should be defined somewhere else. Okay, so it is written in C, and we can expect that has to be compiled, and then it should be loaded as a library. And the load library command at the beginning is initializing this connection. Okay, so when we compile, we use the -h flag, and this is generating a sort of a stub that is describing how the method, the say hello method, should be in order to cooperate with Java. And this sounds a little bit strange because the magic behind this is that the types that are used in C are different than the types that are used in Java, and the runtime environment is providing some mappings, and this is those strange names that you are finding in there. Last but not least, you have to implement this, and you have to know the name, you have to know the kind of type that it is going to use, and your C function is a little bit different than what you are expecting. And this is part of the problem that we are speaking later. This is the example with Java and C, but we can also add something more esoteric. This is Erlang. We have something similar to GNI. This is called NIF, that is Native Interface Function, or something like that, implemented function, or something like that. The example is more or less the same, but at this point we are writing it so that it can be called by Erlang. So we have the piece of code is say hello in C, and then at this point we have, okay, I can move. We have to write the C binding manually. This is the main difference with the one in Java. There is no magic at the moment, but you have to write it manually and still hold what I said before. You need to know the mapping of the types. You need to know how this is working. And if you look, the call to the C part is just one line that is more or less in the middle, this one. And all the rest is something that permits the two languages to communicate. And it is quite a standard pattern, but still something complex to write, especially the first time. And then given this, you have to write a module in Erlang that is calling it, that is providing that this is an if, and there is, again, a library defining your piece of code, and this is the one you use, and it should be initialized when you are using the module. Finally, that one is the REPL for Erlang. You are loading this piece of code, and from there on, given that you did the things correctly, you can call the methods as you would do normally in Erlang. Okay. And then there are still some approaches that are mixed, and they are using many of them in once. And the more prominent probably is Graal at the moment. We are still in Java in some way, but there is a polyglot protocol that permits you to basically have several languages cooperating together. In this case, we have the polyglot protocol is defining two methods, export and import, that permits to have the combination between the two languages. In our case, we are speaking of JavaScript and Python. And this is more or less as the interoperable one, the one like Java and Scala. Then there is also the one through the bindings. In this case, the bindings is written in LLVM and is provided by the Graal virtual machine. And it permits to have mixed the languages, like in this case, we have Rust and JavaScript. Rust is providing a factorial, and JavaScript is calling it in order to get the information. And okay, now, what happens? Okay, the thing is quite diffuse. So I brought to you several ways to do this. I brought you a lot of languages that permits to do that. The way made on bindings, basically, the only limitation is your fantasy, because you have to write a lot of code, but at the end you can connect any kind of language. Okay, so which are the problems? Well, the problem are the real interconnection between the two. If we are just considering them as a sort of a process, a separate process, and you are just sharing something through socket or other, that is simple. But what you really want to have is a real deep interconnections where the data written by one function in a language can be used smoothly from the other language. This is still a piece of code, and should put in evidence this problem. We are using, on the left, we are using PyCUDA, so we are defining some piece of code in Python that is using this GPU in order to do some vectors summing. And the piece of CUDA code is the one in gold in some way. This is a string. This is another well-known problem. So we have a piece of code, but this is just test, and you can't do any static analysis from you can expect any static analysis from the compiler. Similar problem is present also in the other one. This is OpenCL, that is still a way to do GPU computing. This time is in C, but still the portion for the GPU is written in a string that has to be compiled separately later. Which is the problem? The problem is these two are spotting a type error. If you look at the add, we are saying that our vectors, those that we are summing, are float, but when we are defining the real type, we are using int. And this is making a problem when you are, it is more clear in C, because C is defining the types, Python is not. But still, what happens? When you are trying to do the calculation, there is an implicit conversion, no warning, nothing. You can look at the execution. And the three vectors, as we did them, the two vectors as we do them, are made, one is negative and the other one is the same vector but positive, so the sum should be 0, but it's not because of the conversion. So we are promoting the int to float, and no one has noticed this, and the result is wrong. This happens also, this is CUDA in C. CUDA in C is not anymore made as a string. The piece of CUDA code is not anymore a string. We have two kernels, one kernel there and then another one. This one has still the same problem as before. So we are defining it as float, but we are passing some int vectors. And the compiler is spotting this. So this is the main difference between the one before and this one. And it's spotting this, so we have at least a warning or an error that we have something to solve. And this is the main point. So we change the function using the int, and at this point we get the expected value. So the problem are many in this case. We have the fact that some languages are embedded, but they are embedded as a string. So they are not really languages, and there is no part of the compiler that is looking at it in some way. And then we also have some problem with dealing with the data and the compatibilities between this data. Okay. The second one should be more evident, at least from the NIF example that I showed before. It is complex. It is a little bit complex. Okay, normally everything C code and Erlang code is not that difficult, but when you have to write your own bindings, not in Java. Java is generating it for you, but you still, you remember, you have still to know the names, and the names are something difficult. You have to know the types that you are dealing with, and you have to open there is a type that has a mapping inside. So passing classes could be complicated. Passing objects could be complicated. But when you are going to another language where there is the idea of bindings, but there is not a real support, like in this case, you have to write this by yourself. And the real code is just this line. All the rest is some mocking code that is needed in order to have the system working. And it is way complex. And this is something that I don't want to write in any way. Last but not least, if we are going to have a polyglot programming, this should be supported at any level in the development cycle. At the moment, since we are good in developing code, and we are good in developing code in some way, in some specific way, what happens is just that we are considering each piece of code written in a single language in isolation. Okay? That works, yes and no. For example, when we are doing something that should involve the whole analysis of the code that we have, taking into consideration the languages separately can do some problems. For example, for debugging, if you have you want to debug your application and you are just considering the part in Java, but the value is created in the C part and you don't have a way to look at it, could be a problem. But also for something more general, if you have a continuous integration mechanism and you want to do regression testing, for those that doesn't know, is a way to reduce the number of tests that you have to check when you go to the second revision, and you are just considering one part, this could be a problem. And we did experiment about this. We took TensorFlow and OpenJDK that I told at the beginning that they are using several languages, and they are also quite huge, so the number of tests is relevant. So in the case of OpenJDK, we are speaking of 35,000 tests. So running every time you commit something, all of them is something that is taking time, and you don't want, so regression test selection is something you need. But in this case, since most of the approaches are just considering one language at a time, we are losing more or less 10% of the tests that should be reselected. That means, okay, you can be lucky and they are not spotting any error, and okay, but in general, 10% of 35K is a quite huge number, and avoid using that, neglecting to use them could be a problem at the end. We are doing this experiment now. I'm just having a few data, and we are also considering that we are writing a mechanism for having all the language together and doing the test. Later, more on this, not today, of course. Okay, so what I'm expecting in 10 years? Well, I'm expecting evolution in several directions. From the programming perspective, I would like to have something simpler. Graal is going in that direction, but still I think there should be something to be improved. For sure it will become more common, and this need to be more simple, for sure. And it should be available for any language. It would be nice to have it interoperable for any language. For example, .NET, when it was famous at the beginning, any language written for .NET has this kind of interoperability, as now is done for the Java virtual machine, more or less. From another perspective, the one from the programming languages, I would like to have any sort of a standardization of this. For example, the main problem is the types, the data that you are sharing between the different languages, and the languages have all int, they have all float, but they are all different implemented. And this is making problems. If there was a standard that is not just for the language, but is for all the languages, or a way to consider objects in a general way for any kind of a language, could be an improvement for this kind of programming. So that is part of the problem, many problems created by that. But last, but not least, we have also the software engineering perspective. We can't anymore consider our program by each language. We have to consider it as a whole. And this is more difficult because the other two directions are already in some road, but there is really little or nothing about the last one. And still, remember that, okay, we are doing programming language, most of us are doing programming languages, but at the end, people outside the academia is using a real context where software engineering and the development cycle has a role, and we have to think also to that. Okay, that should be all. So if you have questions, I'm here.
I'll start with a question.
Oh, yeah.
So you mentioned software engineering as a big problem.
Yeah.
But how do you see the human aspect in there, especially the skill of being able to work with multiple languages? Is that something?
Yeah, I didn't consider that, but yes, this is one, especially if we don't have some magic for creating the bindings, for example. We are asking people to understand two languages. That is still possible. Many of us are speaking several programming languages. And, but writing the connecting code is the most difficult part because you are moving in the between, and you need to know how the things work. And this sometimes needs you dig a little bit more. For example, when I was speaking about the Java and Scala example, that is pretty easy. But if you want to call the static method that has the same name, what I did is look at the bytecode generated by the class, and then I discovered there was a special field that I can use for call this. This is not something that all the people is doing, and this is part of the problem because we don't have a clear interface, we don't have a lot of things for this kind of programming. Most of the things for polyglot programming is left to the writer, to the code writer. Yeah, so the human part is relevant as well.
Do we have any?
Maybe more comments than a question. I've been very surprised that all along this presentation you have not been using the word garbage collection. So how come you have not been talking about
This
that?
is because you are thinking that it's all garbage. Okay, I didn't because that is another huge problem, but I am eating that in the, we need tools for, as well as the Bagger garbage collector is one of the tools that we need. And having several languages with several different rules for garbage, for saying what is garbage, is a problem at the end, and yes. But it is not mentioned directly, but it is meant to be there. as well as linters, as well as many other things that you are running into. Yeah.
Okay, just to keep going with this question, don't you consider or don't you believe that this is maybe the main problem when you are interfacing a high-level language and C, for instance, dealing with different strategy for memory allocation?
That's true. It's still, it's still a valid question. And, this is still about the fact that data are dealt in a different way. Python is still allocating stuff somewhere, but you don't know about that, and it is automatically garbage collected. And C, you have to do that manually, and you have to be sure that there are not memory leaks. You can consider that in isolation because you can be able to write whatever is needed for that piece. But when things are moving from one code to the other, you have to think of something that is dealing with this case as well. At the moment, there is nothing of that. I think there is a lot of code, but most of them are using, like, for example, TensorFlow. That is a nice case. We have 3 languages because they are providing the bindings for different languages in order to call the library. So you have Java and Python. Probably if you look around, there are several other. But they are basically 2 processes, and they are sharing some data through, they are not directly using the data. They are sharing through sockets or something like that in order to understand what happens. But this is not what we are looking for in the long term. In the long term, we are thinking about the problem that we are mentioning. So the thing that data are moving, are really moving. I think more or less the problems are the same. Take this with Salis Granis, as we had in the past for the distributed system, when data were moving like object migration and stuff like that. We have exactly the same problems. Now, just maybe not anymore in different machines, in different computers, but we still have the problem, the same kind of problem. The data have to be dealt in the same way. You have to migrate data that have some memory location information. They are dealt in some way. You have to discover how to deal with them, and so on and on.
Hi, thanks for your talk. This is more like a comment, perhaps an open question. So you show CUDA, and then you show OpenCL, and then you show one with embedded string, and then moving to the CUDA language. The issue I see is that, well, I see the trend as well. There is one new programming model, it's called One API from Intel, also the SQL standard, single source property. So you have your device code and your host code in the single source. And I see the trend moving there, right? But the issue I still see is that the same source, you see different programming models and execution models. Right? Programming model is how you program things. Execution model is how the machine executes. Because you have a single property, and you're running on the C side, on the CPU, you have the C or CPU execution model, while some part of the programs go to the GPU programming model, execution model, which is very different. So my question is, do you see any change or how we should approach future software?
GPU computing is quite new as well, and this is a real problem because exactly you have the model execution that is different, and yeah, you have problem, and in the future we have to think of this, also without polyglot programming, but just in order to understand how the 2 hardware architecture are working behind, and your code should take this in consideration at the end. Yes, so yes. It's still part of the problems that the framework have to be defined. Yeah. Yeah.
Let's thank Walter one more time.
Thank you.
Next up is Stephen, and I think he's pretty much going in a similar direction.
Shall I start? I'm good. Okay, thanks, Stefan. Yeah, so thank you, Stefan, for inviting me. And I think I wrote my abstract in a moment of mania when I thought I could write a talk covering 5 different topics at a time when I was also very solidly occupied by teaching in the previous few weeks. So this is going to be a bit bumpy, I think, but apologies for that. I thought I'd start with some classic Alan. This is the Dynamic Languages Symposium, after all. So this is a great way of putting something that I've also felt for a long time, that software just it seems to somehow require more work than it should, right? I think that's something that many of us share. And one of the things that Alan Kay also likes to mention is this guy, Licklider, JCR Licklider, who was one of the early program managers at DARPA. And he was talking about how if we get this thing called the internet off the ground, then we're going to have this problem of bootstrapping communication between mutually unknowing parties, right? And that's essentially where I think the mess that I think Walter was talking about has really come from, in that this is only accelerating, right? The fact that we have more and more software arising from more and more disparate places and in more disparate forms, and it wants to talk to each piece wants to talk to each other. So this is my third, I'll stop doing quotes in a second, but this is my third quote, which I don't actually know who said this. It's another one that Alan Kay likes to come out with, but how programming is 95 or 99% glue code. Does anyone know who actually said this? I've been looking for a source and I don't know. It's probably just some meme that gets circulated. But my 20-year vision, coming back to Stefan's theme for the event, is how can we get past this problem? How can we stop this getting worse and actually make it get better? So I've actually been thinking about glue code quite a lot over my so-called career. And this is one piece of work that I've done, I suppose, fairly recently, along with a very good student, Guillaume Bertolon. And just to give you a little preview, this is Python code. It might not be completely obvious first. It's Python code, and all it's doing is it's using libpng, so PNG image decoding library, to read an image, and then later on, you can't quite see, but it displays the image on the screen. So your basic stuff using this library. But there's a little hint of what might be different about this is that, well, we're calling a C function to start with. We just seem to call it in a fairly natural way, and it seems to work. And similarly, all these library functions are actually they're taken directly from libpng. And the sort of punchline a bit later will be that there isn't actually any glue code behind this. It's more that the implementation of Python has been written in a slightly different way that knows how to deal with these libraries. So the reason I think that dynamic languages have a potential to sort of combat glue code is that they have this very direct style, it's very flexible, and it's very usable. So what do I mean by that? Well, I mean that we can write something, doesn't really matter what the language is. Here I wrote x.y.foo, and I'm saying something very high level. I'm saying it in relatively little text. And this is the classic abstraction stuff. We've abstracted away a lot of details, so there'll be stuff about memory going on here that we've sort of hidden. So, it's a high-level notation, right? Fair enough. But there's also something else that I think we don't remark very often, which is that we're being very flexible about what structures can go underneath that. So it's not just that there exists a concretion and we're abstracting away from that. It's also that there might be many, many different concretions, and they can all sit underneath this high-level intention, that there's an operation called foo associated with a data item called y that we get through a data item called x. So we can hide a lot of diversity underneath. And this is, I think, the same idea that the Jonathan Aldrich's essay from about 10 years ago about interoperability and why object orientation sort of lends itself to interoperability is the same idea. There can be many, many different concretions underneath each high-level intention. And indeed, the essence of late binding, people sometimes call it duck typing. I think it's nothing to do with typing, it's about binding. So it's about finding commonality where it exists. And dynamic languages are in a very good place with respect to this, because we've traded away a lot of stuff that make, if we want to have very strong ahead-of-time assurances using classic syntax-directed means, then we don't get this kind of heterogeneity and this kind of diversity. If you imagine doing, if you have some sort of Hindley-Milner type system, you end up with things like, lists have to be all the same type, and then otherwise things break. So we've traded away that, and in return we've got a lot of flexibility. So we want to use that flexibility in a constructive way. And the final thing to observe is that the world is dynamic, right? So dynamic languages are almost tailor-made for grappling with the diversity of the world outside the program, right? So we want to bring things in from outside, we want to communicate with the outside. That's a world that respects relatively few invariants. A lot of things can change in the outside world. Things can be very diverse. It's a large world, but it's an explorable world. So we like to interrogate the world. We like this fact that dynamic languages let us program exploratorily. And so maybe we shouldn't really talk about glue code at all, right? Maybe glue is sort of disparaging term. We should talk about, integration or communication or something. But anyway, it feels like dynamic languages should let us perform these tasks that are interacting with a diverse outside world in a good way. And yet, this isn't how we implement dynamic languages at all, right? We still implement them as a closed box, and off you go. Your code goes here. Start now. You're going to enjoy being trapped in this box. So this is my metaphor for sort of the virtual machine paradigm of language implementation. And of course, we can make it slightly more comfortable. We can have nice standard libraries, but you're still, to some extent, trapped in a box. So the theme of what I've been trying to do with a lot of my work is trying to invert the box somehow. So make our code be something that exists that talks with the language being a window onto the world, right? So what if we weren't in a box, we didn't start with an empty box that says your code goes here, please enter some code. But actually we started with a view on a much bigger world, the world that is already out there, the world that already exists. So going back to my Python example, well, that happened to be an implementation of Python where all those libraries that were on my system were sort of immediately accessible in the Python environment. I didn't have to write that sort of binding code to make them available. Somehow the implementation had figured it out. Oh, there's the code again. That's what I want to show you. So how did it work in an outline? Well, we avoid writing this kind of thing. So this is one of the simpler sort of bits of Python C API code you might need to write. It's just wrapping a single one-argument function, which is the system function from the C library. But it's quite a high sort of noise-to-signal ratio. This is the same sort of topic that Walter was talking about. So what did I do instead? Well, the first step is to take a step back and say, what is our scope? And our scope is memory. So we've got an address space. Memory, it consists of a bunch of memory, and the memory has a structure to it. And this is a structure that is, it's outside our language implementation. It mostly comes sort of from the operating system. And what I did was build a runtime that basically understands what is in memory in a hierarchical sense. So we can divide up memory into a bunch of memory mappings. Underneath memory mappings, there might be, maybe this mapping is an arena for my malloc, and then I have a chunk in there. So the runtime is somehow, I won't go into details here, but it's somehow keeping track of what this structure is at all times in our address space. And the very leaves of this tree are the program variables, or you might have a malloc chunk, and then inside the chunk there's some one or more program values that we've stored there. So the leaves of the tree are somewhere where we can hang some kind of type information to say, what those things actually mean. And then we can make it explorable by adding some kind of API for querying things like what's on the end of this pointer. So this is a project that I've been working on for quite some time now called liballocs, because it's all about viewing memory, an address space, as a collection of allocations that have various metadata associated with them, including types. Types in the sense of, well, a label saying something about how data is structured and what it means, not types in the Hindley-Milner sense or any other sort of static sense. So another kind of glue code that we might want to eliminate, not just code between languages, but it's actually code doing I/O, so code between my local view of data and some external view of data, like the format of a file that we might be storing or reading from. So this is just some code I stole from Stack Overflow, where someone's asking, how do I do file I/O in Python if my file looks like this? And the answer is, well, you write a quite significant amount of code to munge bits of strings and remove commas and things like this, which isn't really, again, commensurate to the task, right? The person had described their problem in just, an example and a sentence, and the answer was, well, write all this code that's actually pretty boring. So that's another sort of flavor of glue code that we should be able to eliminate. So doing this sort of thing, it feels like, yeah, there's definitely work we can do there. But what's the sort of deeper view, if any, on these ideas? And for a long time, I used to say that there's basically two paradigms of programming language, programming system implementation. One is the language virtual machine, which is kind of this closed box. Another is the tool chain with the linker, and then you can have many different sort of compilers that slot into that. But I've started to think that there might now be a third paradigm, which is actually much more outward-facing than the other two. I'm not sure how generally this works, right? So see what you think. So my first example of a really outward-facing programming system is a shell, right? The Unix shell. This happens to be possibly the earliest Unix shell that existed. This is Unix version 0 running on PDP 7, I think. Anyway, it's a really cool video. You should watch the video because it's really fun. Obviously, the shell is a programming language, but it is addressing the whole system image of the operating system, right? You've got the file system, it's got all your devices in it. It's very much facing outwards. So that seems like pretty useful, right? Pretty sort of, I actually find myself way more powerful from the shell than I do from a Python REPL, because there's so much more data that I can just directly manipulate, directly address, directly play with. Whereas with Python, I'm always worried about how do I import stuff, I've got to write all that code and so on. So something about the outward facingness of the shell is something that we can build on. Another kind of outward-facing programming system, it's a bit of a cheat really, but this is a machine monitor. This happens to be the Apple I machine monitor, right? So it's basically a little program that sits in your memory, and you can interactively inspect memory, and you can also it's basically got an assembly language REPL in it as well, so you can type in, you can enter little bits of code. And these were very common on early microcomputers. And the whole point of them was that there'd be stuff in your memory, let's say there'd be stuff in your ROM that you could mess with from this little REPL. So it wasn't that the REPL was giving you a closed environment. It was trying to expose the whole of the computer to you in a way that was interactive and sort of definitely outward facing. And my third example is debuggers, one of my favorite topics. So this is a silly little GDB session that I just did earlier, where it amused me to print printf for some reason. And then I could evaluate an expression that was, calling the printf function and combining it, adding some value to it. And so inside the debugger, there is an implementation of the language. Here it happens to be C, it doesn't really matter. But it's a really, really wacky implementation, right? It's completely separate from what's in C compiler. And it keeps almost no state of its own, right? So when you tell it to evaluate this expression, it's looking in the program saying, okay, there's a thing called printf in there. We can look that up. And then we can, this variable x where we're storing our result is also just a program variable. So it's an implementation of the language that is entirely addressing the state that lives outside that implementation. I thought it was worth giving a plug to some other work that is even not very dynamic languagey, but it's definitely ticking this outward-facing box. So this is some F# code that's using this type providers thing, right? So what is a type provider? Well, I think it's a bad name, really. It's not really essentially to do with types, but it's a way of saying, well, I've got some data in the outside world. So in this case, it's World Bank data. This is from Thomas Petrczek's paper, 2014. It happens because it's a statically typed language. There's some staging going on where a little bit of code runs at compile time that will talk to the data source and generate some data types that are basically the main role of this type provider thing is to take features of a data set, like, for example, you've got country codes, but they're just integers, right? They're just numbers, or you've got some sort of identifiers going on, and just to lift them up to the features of the language. So country codes don't exist in the abstraction that the programmer sees. Instead, there are countries that are named things in some sort of enumeration or abstract algebraic data type or whatever is appropriate. So this idea of lifting up features from external data into features of the language and doing it in a mechanized way is a really neat one, and it's one that I think dynamic languages could do even better than in something like this, where there are some sort of compile time versus runtime complexities to manage. And the final thing I wanted to sort of shout out to was, is Marcel here? No, maybe not. Anyway, so Marcel Weyer, he's got this Objective-S language that I think is really cool. So it's very much a Smalltalk and Objective-C inspired language, but it has this feature called polymorphic identifiers. So the idea is that, well, normally program variables, we have a name for them, but actually we might have many namespaces, and some of them might be naming things that are completely outside the current program. And so it's a way of hiding the complexity of bringing those things in from the outside. So all of these things are things you can use in place of an ordinary identifier in your code. I happen not to like URLs very much. I think they're really ugly and not a very nice conceptual model anyway, but I'm quibbling. So this is a really nice feature, and it's definitely one more example of trying to bring the outside in a very direct way. So I don't have that much more to go. It's worth thinking a little bit about why is glue code necessary to bring data in from outside? And the reason I came up with is that inside our language implementation, we like to take control of how data is represented. So we say, well, objects look like this in my virtual machine, and they have a header, and the fields are either this or this or this, and this. So there's some very restrictive form that our data takes when it's inside our box, and that means obviously it's going to have to get translated to some other form when it's going in and out, right? So that's the basic bargain. And I sort of realized that it's a little bit like how you can think of this as a sort of an intermediate representation, right? We bring data in, and when we're working with it, it has this form that we control. But we always want to transform it from and to something else. So thinking by analogy a little bit with what the truffle and Graal people are doing, and also the meta-tracing strand of work, both of these are saying, this intermediate representation thing, we don't actually need it. Right? We can just say, let's just write an interpreter, right? That's your definition of your language. Or describe the data you want to work with if we're talking about data. And then we can have some very clever dynamic compilation things that can basically do as well, not as well, but people are working on this, as we could when we actually siphoned everything through this quite restrictive intermediate representation. Because doing that siphoning is quite a lot of work for a lot of people. It limits the ease with which we can support new languages, or in my example, new data. So as a little anecdote of what that might mean for the internals of a language implementation, I showed you this Python thing that I've been working on. Well, there was an earlier iteration. In fact, there were two earlier iterations of that Python system. And the first one was a pretty conventional Python called Parathon. And it had this representation for, this is what a Parathon value looks like. So, values inside our runtime, they have this form, and they always have at least these 9 fields, and there's like 25 methods or whatever. So that's quite bulky. But anyway, and then in a later iteration, I realized that I could strip that all out. And I said, well, actually, there's no guaranteed representation of what's on the end if I pass you a pointer to these Parathon values, passing them around. But what I really mean is there is some useful information in memory at that position. And I have a whole separate service that was like an earlier iteration of my liballocs memory querying service that I used to figure out how should we actually interact with this memory. So a sort of slightly more principled way of viewing that might be, what if we just said, we take some very wideband formalism for describing data, like a data description language. This snippet of code is from a data description language called DataScript that was created by Godmar Bach about 20 years ago, and I tinkered with it a little bit during my PhD. And this snippet happens to be describing the Java class file format, which is a bit meta. It can basically describe any binary data up to some, it's embodying a sort of data-dependent grammar, so there's some limits on what structures it can recognize, but it can recognize an awful lot of structures. So in this scenario, we could say, well, analogous with our truffle Graal thing, where we just care about interpreters of languages, can we just say we just care about working with data, and we have a very wideband notion of what that data is, and then can we build our virtual machines around that very accepting view of what the data is that they work with, and can we recover efficient access patterns using these clever dynamic compilation strategies analogous to what's been done in the space of interpreters. So that's my wild and crazy idea. I actually had an even more wild and crazy idea, which was, can we do the same thing for operations? So can we eliminate this idea of a built-in notion of what it means to do a call? That's even more. I've sketched some stuff out because it was fun, but that's even more crazy. So I'm not gonna dwell on that one. But it's a thought experiment that I've got intermittently ongoing, and it's really about what should the core of a language contain, right? If we think of building up a language in this vaguely meta-circular way, where we start from a core and we try and extend it, it's an interesting question about what should the core look like if we make an assumption that we want to embrace as wide a space of existing stuff out there in the world as we possibly can. Okay, I think that's everything I've got, so thank you very much for listening. You've been very quiet and respectful, which could be good or bad. So I'll take questions.
Who got a question for Stephen? Then let me start.
There was one from Andrew.
I'm curious to see type providers come up. I was expecting you to talk about that, but I see it as actually almost advocating for static types, because on one side you've got some kind of slightly, unspecified data. Maybe it's got a schema or something, or it's an Excel spreadsheet or whatever. And on the other side you've got a statically typed language F#, and you're basically bringing the outside world into this world where you've got invariants expressed by type. So I'm curious that you say that there's something for dynamic languages here. I always think of it as bringing dynamism into the statically typed world.
Yeah, what to say about that? I mean, I think the basic thing to observe is if you try and think of the closest analogous thing, but in a dynamic language context, so let's say, what I want is data from a CSV file to be very naturally, idiomatically manipulable from whatever my host language environment is, then there's still a gap that can meaningfully be bridged there in the context of dynamic languages. So I wouldn't say that there's no value added by also having static typing on top of that. It's more that there is an analogous thing to be done there, and you could, this is me being very intuitive and hand-wavy, you could possibly do more by exploiting the fact that you have more freedom, but also fewer assurances, but more freedom in the dynamic language context. Yeah, that's about all.
Hello, Stephen. Thank you for an interesting talk. Can I ask you about whether you think components should be self-describing, or whether it's better to have some kind of omniscient description service that you query? That's one question. And the second one is, what are the security implications of being able to kind of hand an address to someone and say, tell me everything you know about this?
Okay, so the first question, is it better to have everything be self-describing or to rely on an omniscient external service? I think the latter, and the reason I say the latter is that if things are self-describing, then an omniscient service can just delegate back to the thing. But not everything in the world is self-describing, therefore one needs to have some, I mean, this is a very conceptual argument, right, that if not everything is self-describing, you're going to have a third party to talk to about the things that aren't. I don't know if I've grasped your question. Is that getting to it, Jeremy?
Yes, I think so.
Okay, thanks.
So you're accepting that there are some things that can't or don't describe themselves,
Yes,
I guess.
I think that's necessary. Yeah.
Thank you. And how about security? Thank you.
Well, whether you can name something and whether you can access it, so I have to be careful what I'm saying here, because I love capabilities. I think they're great design, but I do seem to be working against them here, and I want to be able to say that naming something and accessing it are orthogonal. So there's both traditions exist, right? In the classic operating system case, where you can have a single virtual address space operating system, but different threads or processes have different access rights on the same piece of memory, right? So just being able to name something shouldn't mean that I necessarily have access to it. And I guess that is the model I have in mind with my stuff. rather than the capability one where we constrain the flow of names and therefore provide access control that way. But yeah.
Hi, interesting talk. I have two questions. First one is pretty simple. So I didn't really get your point for the first x.y foo example. So do you, is the language you want a kind of language in which you have a very strong type inference and you don't really have to write any types? Is that right understanding?
Yeah, so I'm imagining this being a dynamic language with no static type checking. But you're right that it could be, type inference could let you write something very similar.
Right. So you can write x.y.foo even in Java, although in Java you have to write types. And the second question is, so I like your outside world example, but your outside world is still within a computer machine.
Ah.
But the real challenging thing is, the outside has to be, real world.
Sure. Well,
so how do you think about that?
Yeah. So I definitely, when I talk about the world, I intend to embrace not just the computer but the network. I just didn't have any examples of that in my slides, which is my bad. I suppose the closest I got was this file one, where we're talking about pushing data, and who knows where the data is actually going to end up. It could be a network file system, whatever. And then this idea that, at the very end, I was saying, well, what is a procedure call really, and how can we sort of how can we bootstrap a notion of interactions that is very general? Yeah, I'm not trying to stop at just the computer, but I suppose in terms of my work so far, I have done. So yeah, it wasn't the intention to limit the scope, but there's only so many things I can talk about. Yeah, good point.
So when you did the libpng in Python example that it looked quite natural, I wanted to ask about that because I didn't notice any area where you tell it to, for instance, load libpng. So does it just know all of the functions exported by all of the SOs on your entire system and load whichever shared object it needs to for that? Because that sounds like it could get complex quick and have potential, undesirable effects.
Sure, yeah.
With
I
names.
mistakenly left off. There is an import. Basically, you can import a native library very much like you import a Python library. The ideal is that they look exactly the same. I chopped that off in the name of eliminating noise, but now you mention it, it actually confused things, so I should have left it in. But yeah, it works the same.
That actually sounds quite good then. I was a bit worried before, but yeah.
Okay, just quickly, is Max here?
Yes, hi.
Great. Could you set up? So while you set up, one last question from me. I do really like the inside of the box. It's warm and fuzzy and nice. And the outside is really harsh and ugly, and I disagree with the design decisions. And is there some way to make it look nicer automatically, omnisciently, magically?
Yeah, I certainly think that we often when we're programming, we get hung up on making everything the same. And this could be something as simple as like coding style, where we say, oh, this project has this really stupid coding style where they use tabs, not spaces. Actually, I like tabs, but anyway, it doesn't matter. And for some reason, we tend not to invest in what are technically super feasible little mappings. We say, well, actually, I write in my style, and my editor converts it to the style that the remote project wants, and I never actually have to see that style. So there's a lot of really feasible, quite shallow transformations one could do, and I see the same issue coming up in the case of APIs and all this sort of, whenever you import stuff from the outside, you really want to tailor it. But that tailoring needs to be done in a sort of rule-based way. It doesn't need to be, I explicitly code a wrapper for every function that I import, because that way lies madness. So getting this sort of rule-based adaptation thing going is, I think, one way to solve this problem, hopefully.
All right, let's thank Stephen. Our next speaker is Max Heiber from Meta, and he's going to talk about something quite different. We are still looking outwards from our dynamic languages, but this time with the help of gradual typing and to support tooling.
Thank you. So do I just put it in the hole? Yeah, I hope so. And then, I have. Ah, I see. It's giving me another monitor. Sorry, just a moment. Whoever saw that, thank you for the sharp eyes. Okay, I just need to tell it that there's another display. I hope all the other talks were this entertaining. I want to turn off mirroring. And we're good, we're good. So I'm going to be talking about telling the truth at scale, technology that we used at Meta. I wanted to say that if you have any hard questions, by the way, can everybody hear me? Yeah. If you have any hard questions, Andrew, could you raise your hand? That's the person to ask the hard questions to. So we work on the hack language team at Meta. None of the good ideas in this talk are mine. They're from these people who are also at Meta. So sound dynamic is I want to explain why I'm here, like why I'm talking about this. I think it's a new point in the design space of languages that are not fully static, what's sometimes called gradually typed languages. And I think that this is just the beginning. So if you're interested in these ideas, there's a lot more theoretical and practical work to be done to go further with these ideas. So I'm hoping people in this room can pick up some of these if you find them interesting. So in order to understand why we chose this solution, I think it's important to understand the context, the particular problems that we were solving. This is the Dynamic Languages Symposium, and I think there's a place for dynamic languages. I can say why Hack, our language, got less dynamic over time. So we have much more than 10 million lines of Hack at Meta, most of it in just a single code base. So you can see how it might be difficult to make changes. Hack evolved from PHP, a language that was once fully dynamic. And some features that are relevant for this talk is that Hack has static type checking with generics, and it also has shallow runtime checks. And I'll say what those are soon, very soon. So when I say shallow runtime checks, I mean that if you call this function foo, by the way, there's a $ in front of variables and parameters in Hack, just something we got from PHP. So if you call foo with something that's not a string, you will get a runtime failure. If you try to return something that's not a vector, where we've annotated vector in the return position, you will get a runtime error. However, we don't check deeply. So in the code here, you can see that we're actually returning a vector. Do I have a pointer? We're actually returning a vector of string, and we're claiming that it's a vector of int, and the runtime will not catch this. And actually, in this example, before sound dynamic, you wouldn't get any type errors either. Because foo, there is no type annotation on the return position. So this is an example of the interaction of untyped and typed code. So it's like foo returns a t_any. So t_any is a type that can be used anywhere. It might be familiar if you've seen Python with mypy or pyr, or TypeScript or Flow. A lot of these languages have this unlawful any type that you're allowed to use anywhere, and it can be useful for interoperating between static and dynamic code, but it's unsound. So we're going to present an alternative to t_any later in this talk. So I think Hack is great. It's got static type checking, it's got runtime checks. However, the types can still tell lies. So here's a case where the type checker is telling the user via this hover, x is an int. I know statically x is an int. but unfortunately it's wrong. X can turn out to be a string at runtime. And I think it's interesting. Feel free to ask me later in the question section about more sources of lies. When I say a lie, I mean statically we think something has one type, but at runtime it turns out to have another. One source of lies that you've already seen is untyped code. But there are also escape hatches and dynamism, and this is true for most gradually typed languages, that they have these sources of lies. So what's the problem? Yeah, this is where we infer a t-any type. What's the problem with lying? Why do we care that types used to be able to lie in Hack? Well, we actually hit some real problems at Meta with lies. One is that when something goes wrong at runtime, it can be hard to find out why. You don't know which types are trusted and which are not. Sometimes they're helping you and sometimes they're lying to you. But also, we rely on a lot of language tooling, and this language tooling can be very limited when the types are not trustworthy. So here's an example of what happens when you rename a function at Meta. We don't really rename it. We keep the old function around and we put a deprecated marker on it, and then we make the new one. Because due to the lies and due to dynamism, we don't actually know for sure that that function isn't called. And we try to have our tooling not do too much unsafe stuff. However, some of our tooling did unsafe stuff anyway. It's really hard to weed the stuff out. So we had a lint against redundant casts. So here somebody is pulling something out of a vector, and they're casting it to an int. Why would you cast an int to an int? The linter says this is stupid, you should remove this. But if you listen to the linter, who knows? Something bad. You might get a sev, and this is the sound of a sev, which is when Facebook goes down. Because of the linter told us that the cast wasn't valuable when in fact it was, because as I explained, our runtime checks are only shallow. So we're not actually checking at runtime that we have a vector of int. It might have floats in it. And try to avoid those things. So I'll stop doing that. It's just runtime type errors are just very painful. It doesn't mean I need to cause you pain, though, so I'm sorry about that. So there are some solutions that we considered to this problem of types that lie. One is doing full runtime checks, and that's what C# does, and that was some applause for C#. But unfortunately, we couldn't do that because with our 10 million plus lines of code that run in some of the web's most valuable properties, I think, we can't really do much to change runtime behavior or performance characteristics. So it's a pretty invasive change, changing what the code means in order to add more runtime checks, and we just couldn't do it. But there was a new option on the table, which is sound dynamic, the topic of this talk. So with sound dynamic, types tell the truth. This is a claim about the relationship between syntactic and semantic types. So syntactic types are the ones that the users write. Semantic types are what those types represent. And you can think of these as roughly sets of values. An important type here is dynamic, and it's not t-any. It's a sound alternative. So dynamic is a tool that lets users move from the untyped world to the, between the untyped and typed worlds using an upcast to dynamic. And we'll see this with code examples. Just check the time real quick. So before I get into these code examples, I wanted to explain something about Hack. This is just a minor syntax thing that will keep these examples succinct. This is called a promoted parameter. And what this code here means is that when you call the constructor, we create a property called item of type int. So you can think of it as desugaring to the code at the bottom. This is not the most innovative thing in the talk, but it does make the examples easier to read. So here's a class intbox, and we think of this as having an invariant. You can see it on the line with the constructor. An invariant of intbox, for it to do what it says it does, for the type not to lie, is that item is always an int. So I'm going to talk about preserving an invariant. We want to check that this invariant is preserved. The item is always an int. So on the first line, we call the constructor. The invariant is preserved because we've just assigned the number 3 to item. Item is an int. Everything is good. And again, parameters are checked at runtime. So if we happen to sneakily try to put something other than an int in there, the code would have failed. On this line, the user is upcasting to dynamic. They're opting into dynamic operations. And this means that for our purposes, you can do most things with this variable BD, this dynamic box. So we call the set method on BD, which at runtime is an int box, and we try to set the item to a string. Just take a second to think like what you think should happen when this line of code is run. Exactly, you got it. Exactly. And that's what, oops. Exactly. Because the parameters are enforced, you see that set has this parameter that's annotated as int. We know that there's a runtime error here, and so the invariant is preserved and the last line is never run. So this is code that has a runtime error, but type checks, because the important property for us is not a relationship between the syntactic types and runtime behavior. It's between the syntactic types and semantic types. Here, no types are lying. Here's a harder example. Take a moment to think about whether this code should type check. The whole thing. So we have this, we have declaration site generics, and an important thing to know about generics in Hack is that they're erased before runtime. And this means that you can't check a generic type in a parameter because it's not around. The runtime doesn't know about them. And we have an invariant here. Our invariant is that item is of type T. Is this invariant preserved by the code? I'm not asking for an answer, just to think about it for a moment. It's not, it wouldn't be preserved if we allowed this code to type check. So our type checker rejects this code. It rejects this line that's highlighted in red. Because we have no runtime checking to ensure that the invariant is preserved. If we were to allow BD to, if we were allowed to cast a box int up to dynamic, then we would have no guarantee that when methods are called on it, they are checked. So if we allowed the set method to be called on the next line with the foo, that would actually go through, and item would be supposed to be an int, but actually a string at runtime, and that's exactly what we want to avoid. So the really important thing here is, I said that in a very convoluted way, but I think it's better to think about what happens with the int box example, which is that it's the enforcement that enabled us to preserve the invariant, that the types are not lying. So I showed why this, on the face of it, relatively reasonable looking code with a box of T couldn't type check. So how are users actually supposed to write box of T and then use it? That's a problem to be solved. So we're sound, but so far not very expressive. That's a clap for how sound we are, but I think they should withhold their applause until we add back some expressivity. So the way that we did this is with like types. And so if users can't write types that tell the truth when they say that item is of type T, maybe they can tell the truth when they say that item aspires to be of type T. So when we put this tilde in front of something, we pronounce it a like type. A weaker invariant is that item has type like T. And this is just sugar for T or dynamic. So we have union types in Hack. We don't let users write them in very many places, but they're in the type system. And so what is still true is that item either has type T or type dynamic. So the following code is safe. And what's nice about this is that it's not so different than the other code, but we're a bit more honest about what can be known and what cannot be known. And what we could have done is, instead of like types, we could have written dynamic everywhere. So the constructor takes a dynamic, get returns a dynamic, set takes a dynamic. But then we've lost the ability for the user to tell us what the types aspire to be, what their intent for the code is. And we've also lost the checking that, yeah. So on the last line here, we still fail because we're returning something that's not an int, and we said it would be an int. We get the return type enforcement fails this code. But at no point do we lie, which is exactly what we were going for. Lies were the problem that we were trying to solve. And we enable expressivity by letting users express weaker invariants.
But when the return type is like T, so is it a perfectly happy return string?
Return type is like T. So I was talking about the last line of foo.
Right.
Good question.
The return type of get is like T.
Yeah, but the function wants a T, an int. So you can't. The return type of foo itself.
Oh, it's the return that fails, not the call.
That's right. Yeah, thank you for that. That was important. Okay, so the problem that we had was that the types were lying, and now the types tell the truth. And this sound dynamic technology is used in our IDE features. It's used in our static analysis. We no longer have a linter that's telling people to remove casts that are actually very important at runtime. And what's next for us is to give users fine-grained control of dynamism. So we do have a lot of like types now. We would like fewer of them, and we want to give users tools to opt out of dynamism where it's important to do so. This has been modeled in Coq. There should be a paper coming out soon. And I want to briefly say what I think the next 20 years looks like, which is always very speculative, but I think worth doing. I want to point out that it took about 20 years for us to get here, where the world's most popular industrial dynamic languages are starting to adopt some static type checking with varying degrees of depth. And a few of them have static shallow runtime checks or experiments with shallow runtime checks. So I think in 20 years, we'll probably see more runtime type enforcement, deeper adoption of static type checking, but also more work on the relationship between the runtime and static type checks, like the sound dynamic technology. I think if you have these two levels of type checking, it's important to be able to relate them in a meaningful way. And also I want to point out that to even explain what sound dynamic does, I needed to allude to semantic types, which is not a very common thing to talk about. So I expect in the next 20 years, we might talk about semantic types more. Now we're ready for questions. Thank you.
Thanks, great talk. For historical reasons, I really like types. Can you tell us what your users think of this addition? Or any, do you have insight whether this will be adopted, liked?
Yeah, that's a great question. I should point out that we were a bit subtle in how we rolled this out, so I didn't get into details in the talk, but we used this technology, implicit pessimization, which means that for this box thing, I'm having trouble going back slides. This is not what it actually looks like at Meta yet. It was just a bit hard to explain. I didn't go into too much detail, but I'm glad you've asked about it. Users do not write squiggle T. However, when they hover over something in their IDE, then they see the squiggle T. So the way we've explained this for our first stage of rollout is that the type checker is giving you more information so that if you have a runtime exception, if you're trying to figure out what happened, we tell you which types were trustworthy and not trustworthy. So the only place users see it now is in error messages and in hovers. And I think overall the response has been positive. I think our power users get it. It was, there were some bugs to be fixed, of course, like when we were overly liberal with where we put the like types or when our error messages were confusing. So there were a couple weeks there where we had to iterate, well, not me, but the people who did the real work had to iterate very quickly to make users happy. And since then, I think they like it. Yeah.
You mentioned union types. I assume for this to work, you also have intersection types. And if yes, can you say anything about that? Particularly in the context of intersecting function types.
Absolutely. Yep, we have intersection types. They're also used for type refinement. So if you have a union and then you do a condition that checks which branch of the union you are, inside the conditional, we know which branch you're on. And actually for this work, when we type check a function or a method, we type check the intersection of the type that the user wrote and a dynamic version of it.
I have two questions, actually. The first one is that I have not really understood why you cannot enforce a type for a generic. And the second question is that you seem to have motivated all this work because of the generic. Otherwise, you don't need this upcast dynamic. Is there another reason, or it's just that you have just mentioned this one for this talk?
Sorry, I'll answer the first question, then I might ask for a clarification on the second one. So for the first question, if we have generics, why don't we enforce the generic types? I wish we could. We can't because they're erased. So the runtime, when it does its runtime shallow type enforcement, it doesn't see those.
But why do you erase them?
Oh, why do we erase them? I think that's probably historical. So HHVM, which is the runtime for a hack, it evolved from a PHP runtime. And yeah, it's a good question. I'm sure there are other languages that erase generics. They probably have good reasons. And Andrew, can you?
I mean, yeah, it's historical. I think generics were added to hack as a static only feature. They could have chosen to put it into HHVM, which is what they did with C#. But I mean, Java made the same choices as active. Many languages do the same.
Okay, and the second question I think is simpler. Is there another motivation for upcast dynamic than generic, or is generic the only motivation for this extension? If you were...
I see what you mean. I don't think that we would need any of this if we didn't have generics, because if we didn't have generics, my understanding is that everything would be shallow, like all my examples of, and if everything is shallow, everything is enforced, you would be able to trust all of the types.
So the conclusion, if you were not erasing types, you would not be needing all these probably.
Yeah, that's right. I think there are probably other advantages to erasure. Okay, sorry, if we kept the generics at runtime and we wanted to enforce, you've returned a vector of floats, is every item in the vector a float? That's an ON check. So the C# model I think is different. I think things are checked as you put them in, which is a little bit better than deep checking everything as you go through. So depending on how if we kept the generics around at runtime and we did deep runtime checks on every parameter and return position, I imagine it wouldn't perform well, but there might be smarter ways of doing runtime checks.
Thank you for the talk. I can imagine at the scale of Meta, runtime performance is really important. So what's the cost of doing these runtime checks as opposed to not doing them?
I'm very glad that you asked. I'll say something suggestive. So there's a work by colleagues at Instagram for, let me see what it's called. Bonus slide. Nope. Well, I've lost it. Let me see. Okay, we'll go from memory. I can find you the reference afterwards. So at Instagram, they added static type checking to Python with runtime checking, and they got incredible speedups, and can give exact numbers. And so this experiment has been done. I think, so adding runtime checks sped things up at Instagram, and something similar might be true for Facebook and Hack.
But I guess that needs cooperation from the VM.
Oh,
Right.
yes, absolutely. So the runtime checks are done by the VM, and they enable a type analysis in the optimization for the bytecode. I'll just say it. Facebook would be a lot slower without shallow runtime checks.
Okay, thank you.
Any more questions? Then one technical question. I don't know whether you are an HHVM expert, but since you talked about shallow checking and the collections, does HHVM use storage strategies, which might be one way to get those checks fast or avoid them?
Yeah, you've caught me not being a runtime expert. What is a storage strategy?
It's basically you're trying to specialize on your erased collection, the type of the elements in the collection. So V8, for instance, uses that for integers or doubles instead of storing it all as boxed objects.
Yes. Yeah, there are quite a lot of types in the analysis. I think some of the optimization happens in the JIT, and some of it happens in a bytecode to bytecode compiler that sees the entire thing and infers the types. And so I'm pretty sure we don't box all the ints, I think. One thing I also know is that you mentioned V8. I know that V8 uses hidden classes so that when you're passing around JavaScript objects, it knows the shape of the objects and can optimize the layout. We do almost the same thing. It's the things are dictionaries according to what the user actually writes, but at runtime we treat them more like records, and that's through type analysis.
Okay, cool. Thank you. Any last question? Well, then let's thank Max.
Thank you.
So that was our very first session. The next session starts in half an hour. If you're a speaker, please find Manuel and check your laptop. Thank you.
So hi everyone. Thank you for attending this session, and I think it's time for us to start. And the first presentation is by James about dynamic everything.
All languages are dynamic, that's right. My text today actually comes from Douglas Copeland's novel, All Families Are Psychotic, where I think he's actually riffing on the famous quote, it's not Dostoevsky, of all the families being, all unhappy families are different in every way, but all the happy families are the same. What's that got to do with programming languages? We might get there, I don't know, we'll see. Why on earth would I say all languages are dynamic? Because that's clearly stupid and clearly wrong and clearly not true. Well, once when I was younger than anyone in this room, I can still remember sitting in my bedroom reading this book, the ZX81 Basic Programming Manual, because I had a computer like this, the ZX81, which had 1K of RAM, and 1K of RAM lets you write more or less one screen worth of programs, and I have to stand here or the camera won't pick me up. So this is actually ZX81 Basic. There's a bunch of stuff I could talk about that, notably how it was impossible, for example, to make a syntax error. Who thinks that being able to make a syntax error is an important part of a language being dynamic? Is that everybody or nobody? Because you couldn't make a syntax error. The reason is because that little K there meant keyword, and when you press the key on your keyboard, which I don't have a picture of, sadly, it would jump up and say, actually, I don't know what it would jump up and say, because I can't remember the basic keyword that began with K. But if you hit P, you got print, and if you hit G, you get go to. And what this was actually doing was translating your key presses into what we could almost call bytecodes, and sticking those bytecodes into memory. And then the way it drew that was it actually ran through what you could think of as bytecodes and printed the damn bytecodes to the screen. So it was a print bytecode in memory followed by the bytecodes for that temperature converter. This just came off YouTube or sorry, yeah, whatever, Wiki. So is this dynamic? It felt dynamic. When you ran your code, you had a slow mode where it would keep the picture in a fast mode because it was using the main CPU to draw the picture. So most of the time, the thing was only ever drawing the television picture. And it just stopped drawing a television picture and computed 20 times fast, which was really rather slow, of course, these days. But anyway, as an aside, looking at this code, type declarations. Are languages with type declarations, static type declarations, dynamic? Who thinks that you can't have static type declarations and have a dynamic language? Come on, this has got to be easy, right? Anyone? Yeah, who thinks you can? Can you have static types? Because really, let's face it, this is what it's about, isn't it? Really what this entire symposium is that people writing papers about small talk and about Perl or whatever couldn't get their papers into the main conference. And you might think that's funny, but if you really, really want to see something funny, I recommend going to YouTube and typing Popple the next 50 years. And listen to a panel at Popple this year where the panelists go through the list of the famous papers, like separation logic, like typed assembly language, and there are several others that get mentioned by name, all of which were rejected from Popple, and all of which the Popplites are really proud they rejected them, because they could rebuild all that work based on true Popple foundations. That, ladies and gentlemen, is why we are at Uppsala and not at Popple. But why are we here at Dynamics? So where do we get to? You know, like type declarations bad? Yeah. Static types bad? That's the point of this, isn't it? Because you couldn't get a paper into the main conference. Okay. What about that? Is that statically typed or dynamically typed? This is basic. Come on, it's literally basic. It's basic in at least 3 different ways. Untyped. We have an untyped from Jan. Who else? Typed. Yes. Manuel wins. Yay! That's right. Basic is a statically fucking typed. Sorry, statically. Oh, I'm not in America. Statically is a fucking statically typed language. All right? Because you can see the types because that's what these things here. I had a conversation with all those dollar signs, and if you're into a more sophisticated basic, you might get percent signs as well, which means that you've got an integer variable instead of a float. And even in ZX81 BASIC, it's not shown there, you have to declare your arrays before you use them. I know that's a difficult concept for Python programmers to understand. You can't just, or Perl programmers, you can't just start subscripting stuff and it manually creating all these variables. Fortran programmers may have difficulty with that as well, but in BASIC you have to declare everything. And the original BASICs, I don't know if you count if this one's being compiled, but you're not running the code, we're running bytecode, and the original BASIC and the VAX BASIC that I was forced for some stupid reason to do at university was all compiled. It was compiled line by line. You could call it a jitter perhaps, or a dynamic compiler, but it sure as hell was compiling. What about that? Anyone know what this is? I never used it, but I'm sort of just gesticulating to Niklaus Wirth. It's not RAT4. Where's Robert? That sounded like Robert. It's not. Yeah, it's RAT4. That's right. With the spirit of the what is it? This photograph was taken from a Canberra tweet stream. Yeah, it's RAT4. It actually, it might be fucking RAT4. I just grabbed the thing. It is, isn't it? I was going to say this is Pascal, but it's not. It's actually RAT4. One of the things we've already heard about is that dynamicness is about being open to the environment and being able to take advantage of serendipity in the programs you write or the talks you give. So yeah, you're right, that is RAT4. It's actually RAT4 apparently running on the UCSDP system. If you know what the UCDP is, if you were older, and in New Zealand case we couldn't afford the computers, but if you were slightly older than me, you may have learnt your Pascal programming on this thing, which was a bytecode interpreter that ran on Apple IIs and various other bits and pieces. The UCSD Pascal bytecode interpreter was one of the 3 alternative operating systems that was available when the IBM PC launched. What was it? It was a bytecode interpreter. Static or dynamic? I don't know. This is RAT4, same thing for Pascal. The user interface there was called the filer, and not long after that, when the Macs came out, they changed the name of the interface to the Finder. So in fact, that thing across the top is arguably the ancestor of Mac's menu bar and a whole lot of other things as well. But this is Pascal. No, that's actually RAT4. It's even better because, of course, this goes to the point. What is more static here? You can use these variables without declaring them, right? And famously, it didn't lose a spaceship. I did check on risks, but if you change that comma to a full stop, then that's a declaration and assignment of a variable do 30 cycles equals 1.15. And this hasn't actually caused spacecraft to crash, but apparently it did cause errors in trajectory planning that were fixed and removed by someone putting the comma into the right place. As we know, these days talks are really just tweets done in person. And so Sriram was very proud about the finally beating the vocabulary out of the HCM curriculum standard. What vocabulary? Well, interpreted versus compiled. Is Smalltalk compiled? Is BASIC compiled? I'd argue BASIC is compiled. That USDCP system is compiled to bytecodes, and it feels static. But if I told you that that's the way Python is implemented, you'd say that's a dynamic thing. What's going on? Well, Anyway, after doing the ZX81 thing and doing computer science, actually, this I got, believe it or not, from the public library. Just before I started university, it must have been, for some reason, my municipal library subscribed to Byte magazine, and here was Byte magazine, and this great picture, and of course, Smalltalk, which you can still get today for aficionados. This is not Smalltalk 80, which has actually caught me out. This is actually Smalltalk 78, and you can get Smalltalk 78 the way you get anything else in the entire world, by going to your favorite search engine and typing in Smalltalk 78. And so this is actually a Java implementation of Smalltalk 78, which will actually run various important Smalltalk 78 programs, notably Alan Borning's ThingLab, which of course invented, what do you call it these days, object constraint? No, it's not. Functional reactive programming, that's right, yeah. Anyway, sorry, right. Smalltalk 78. We're declaring a class. We've got to declare a class. Here, the way it works in Smalltalk, basically anything from 76 onwards is you have this editor here. We're going to fill in those fields and hit go. And so, you know, we can do that there. I think I've said, okay, there's a definition of one. That's a point class. It's got fields X and Y. I have to declare my fields before they're used. What? That's not, is that dynamic? If I declare a method like this, for example, here is the classic one. Here is a method to return X. And as you can see, Smalltalk 78 is not bound by the constraints of ASCII. For you people want to think it's going to be great when we can really use non-ASCII characters, the answer is yeah, and this demonstration would have been slightly more interesting if I'd worked out how to type the damn things. It's dynamic if you're APL and you can't actually type your program, I don't know. Anyway, so what I tried to do here is edit this. So now we have a new method called XX, and it's going to return the value. You have to use that. I have to use this. Very close. Very close. Right, so the entire previous half of the talk is scrambled. And I got to, you know. Fine. All right, sorry. I don't really, yeah, okay. I got to use this. Right, so there we go. Now what we're doing, and if we say accept that or whatever, compile, actually I think the menu item on this version was compile, we get that. Which says, oh, do you want to declare this as a global variable, XX, which means I can't find the current variable. So Smalltalk, a dynamic language, won't actually let you misspell the name of a variable. So it's like, it might be dynamically typed, but it knows something about the structure of your program. It's not, I was going to say it's not dynamically scoped, and which is the overloading dynamically scoped in at least two different ways, but I mean, you cannot just magic variables out of the air by assignment the way, for example, you can in BASIC. Or the way you can in Python or various other bits and pieces. How far can we actually go? How mutable, how random, how Turing award-winning can our language be if it really is going to be dynamic? I mean, obviously, syntax checking is good, right? Yeah? Syntax checking is good, unless, of course, you are one of my personal heroes. Here's a small program in a programming language that we probably, frankly, everybody in this room has used this month, yeah? Everybody? Right. And especially, what's best about this, of course, is especially, am I allowed to say this? Especially the Popple guys. Especially, you'll never, ever find a Popple guy using Word or something, whereas occasionally there are still papers that sneak in. You know, so, right, anyway, what's the point of this? Well, there it is, okay. There's a program, it's just defining a function called foo, and it ends, and we run it, and it's evening and it's morning, and there we go. It's gone, yeah? Great. What's the problem? Well, here's a slightly longer program, and in this slightly longer program, we're actually going to call that function or macro or whatever the fuck it was. And when we do, we get this. Yes, we get a crash, okay? Is crashing like this actually what makes a language dynamic? Because the thing here is that this is actually a syntax error. Illegal unit of measurement, point inserted, because I typed IX instead of PX or PT or whatever, or IN. There's no latex unit IX, and my definition had it. But what this shows is that TeX, as we all know, TeX programs are not actually parsed before they're executed, at least not in any sensible sense of the word. And you could say, well, of course they're not, because it's a macro system, and the answer is, remember what Shriram said about interpreted versus compiled? Well, that's an implementation. You know, just because Don Knuth, may his name be praised, implemented this as a macro system, doesn't mean that that's an excuse. You know, it doesn't necessarily mean that's an excuse for the fact that, well, here is a typo in your program, which is only ever going to, you know, it's a syntax error in your program, which is only ever going to appear should execution happen to get there. Right? And this is the way we are supposed to present all our functional mathematics and all this kind of thing. So just pointing it out. There was actually an Australian attempt, various attempts, to do to do typed versions of LaTeX. Or at least typed versions of layout languages where these kind of things would be impossible. You know, could you really have a publication language where the syntax errors were all detected before it started typesetting? Do you think you could? Do you get a PhD for doing that? I don't know. Does it matter? Well, that's a separate question. Does any of this matter? I was hoping to be more interactive, and I was hoping to spiel a bit more about, what's the line? Improvisation in terms of languages. This is a rather long sequence. So, you know, there's the question, what about dynamic definitions, dynamic dispatch? I do come from the object-oriented side, which means I gesticulate to Simula. And, you know, we all know that Simula has inheritance, and the whole point of that is that you might have any of these objects, A, B, C, or D, and you can stick them in and it will work. But is Singular really a dynamic language? Because, you know, you had to use a file editor and you had a static compiler. But it's doing this dynamic dispatch thing, right? Well, once I'd got over the byte issue, I found in the basement of the university library, which was generally used by amorous couples for other purposes, but I looked at the computer science books, and I found this one, Smalltalk. Smalltalk, a dynamic language. It's clear, it's simple, it's easy to operate. Yeah. Do I know what that is? That's the inside of Smalltalk. It's the meta-class hierarchy. I used to be able to recreate that from memory. Anyway. What's this things got to do with being dynamic? Being dynamic does clearly not necessarily mean things are simple, and it clearly doesn't mean that you can have incredibly complicated class hierarchies, and I haven't got the slide in, but you could imagine the art of the meta protocol book here in this point in the slide. Okay, I actually did a bit of Smalltalk. I did quite a lot of self. This is a cool bit of self. This is actually the definition, this is the definition of if that the self compiler had, and because some very clever and now unimaginably wealthy people implemented self, Urs Herzley and Craig Chambers, particularly Urs, this definition was actually taken by his compiler and basically went as fast as anything could at the time. Well, that's all right. And so if you think about, let me see, Smalltalk, effectively what that meant at a very high level, if you think about a meta level, is you've got objects in Smalltalk, you've got a get superclass method, it returns something that's an object. Nice paper by Dave Ungang de la Bracha, which points out that the self-design, what we now have is mirrors, is in fact you separate out the meta level in terms of the objects that implement it. So if you call get superclass or get mirror, you don't get something that is in some sense in this domain, you get a separate object that is off in a different domain, and they try and cut out some of the recursion there. How well it works? Ooh, don't know. When do I need to stop? In a few minutes. Self has its problems. I'm not going to go into them, but late versions of self, by the way, have a subclass me button. When the entire point of self was programming without subclasses, or programming without classes. We're going to program with prototypes. You can talk to me afterwards. Which part of this didn't you understand? Things like JavaScript goes on, and in some sense this is more dynamic than self. What I'm saying here is that, you know, even if you think about object-oriented languages in this similar Smalltalk, self, I'm going to say that Newspeak in this thing comes as a bit of a throwback. JavaScript, whenever you do assignment, it just dumps it into the lowest object, whereas, well, you know, self is like Smalltalk, and as we've already seen, it only lets you assign to variables where you've actually declared the damn variable first, because you don't want your spacecraft that's being programmed in Smalltalk to sort of disappear off into the wrong direction. But JavaScript will always do an assignment, and it always does it to the lowest object, and in some sense, that is being more dynamic than self and Smalltalk and similar. We all know Dijkstra would have said this. Right, so I was going to sum up this bit, and my slides are going to do it for me. Basically, I think if you even think just about this category of object-oriented languages, and you want to say, are these things dynamic or static, and you want to do this in terms of the if you like, the structure or the meta model of the language. It's not as simple as saying, well, they are dynamic or they're not dynamic. In fact, we can see almost different kinds of object-oriented programming through 4 or 5 generations about what needs to be defined where, what can be changed where, what happens together, and what happens apart. I will skip this because that's basically a list of the things. Ooh, why have we put this here? Oh, that's right, here we go. This is our Smalltalk 78 again, and I'm going to write one foo, which is going to call foo on 1 or something. And I can, look, I tell it to compile. Actually, I don't, I have to tell it to do it, but anyway. And what do I get? I get this. Okay, the crash. The things that people in Popple Land, I shouldn't say this, but what the hell, I'm exhausted. The people in Popple Land upbraided Smalltalk and object-oriented programming for not being type safe precisely for this reason. That you could do a call, in this case I tried to call foo on some integer, and message not understood. There was not a definition of foo for that integer. Right? And this was, for quite a long time, a stick used to beat programming languages and object-oriented people with by people who want to publish in other conferences. So I'm going to show you another language. And it's got 2 important features. And the first important feature is that it doesn't have any real static type declarations. Okay? There we go. We're declaring some classes. For some reason, this language says data instead of class, but that's declaring some record structures. It's not actually really declaring the types of variables. I'm going to pretend that anyway. There we go. And this environment actually is really pretty dynamic. So I've got my definitions here, and I can type code in here, and it updates it, and it shows it the value. So for example, if I accidentally change the way a dog barks to Rolf or something, that other code gets executed, it gets updated live, and basically immediately as soon as I do it. That's pretty good. That's pretty interactive. That's pretty tight. Okay, and what's more, this system is clearly dynamic, because what if I do that? What if I ask a cow to say something? Oh shit, I haven't given a definition. What do I get? What's that red thing there? Oh look, it's this crash. Okay, it is this crash. It does say non-exhaustive patterns in function say, but what this really means is does not understand. The cow does not understand the message say, maybe things around the other way, but that's it. Okay, and I call this crash, I did actually check it yesterday on the most up-to-date version of this language. If a dynamic language is a language that can have precisely this kind of crashes, and if those sort of languages are bad, well, what is this language, by the way? Anyone know? That's right, it's the H word, Haskell. And another thing people will say about dynamic languages is, well, you can just continue on. And the answer is you can just continue on, because from here, if you then give that definition, it all just carries on. It will run, it will update, the exception will go away, and on it goes. And yes, that was Haskell. That thing is still there in the version of Haskell I was using, which I actually reluctantly love, which is Haskell for Mac. And one of the things that I discovered I loved about it, which is really weird, was because, it seems odd to say it, but I'm going to say that there's a bit of the same sort of flavor that you find in Smalltalk code. I'm not sure whether that's a good thing or not, but there's not very much line noise, and stuff happens on spaces, and I'd probably still prefer Smalltalk over Haskell. But maybe if Haskell can interact like this, and importantly, can provide these sort of crashes when things aren't defined, which is a hallmark of dynamic languages, which let's remember that since approximately 1995, so in other words, before many of the people in this room were born, it was absolutely impossible to create this kind of crash in Java. Okay? Absolutely impossible to do this in Java. You might call it a type error. But that would mean that Haskell has got dynamic type errors that Java doesn't. Let me just say that again. Haskell today, as defined in the standard, admits dynamic type errors that Java never has. Yeah, tweet that. Anyway, What's going on here? Well, part of it is you know, as Tudor puts out again, all my talks just come from tweets, there is this issue of static versus dynamic programming languages. Sriram points out it's about the implementation of the language, and Tudor's saying it's also about the IDE. It's also about the IDE. And I think the Smalltalk and self for me line is it also about, you know, in some sense, where do you draw the lines? Do you say this operation may be adding a new field to a class? Because in JavaScript, well, actually I don't know what JavaScript does today, but in JavaScript 5 years ago, you did an assignment and it added a new field into the instance. I believe in JavaScript today, if you do some kind of structural freezing of the instance, that won't happen, but if you don't, it still will. That seems pretty dynamic, but then again, Smalltalk programmers don't really mind that they don't have to do that and quite like the idea that they can't randomly invent variables in their programs and don't really mind having to go and say, oh, look, I'd like you to add a variable, declare a variable for this method, declare a variable for this block. And I've been told to finish up, but I did start a couple of minutes late. I find myself saying this a lot. Ontogeny recapitulates phylogeny, which means, if you want to understand how something is, you have to understand how it evolves. Originally, it actually meant that you could look at the development of the embryo, and the idea was that would actually mirror the evolutionary descent of a particular species. I'm kind of generalizing it a bit, of being slack about it, and just saying there are a lot of things we can understand which happen only because of the way they happen, you know, because of the way they came about. So whether it's things like the fact that Daphne has one if statement with one if statement without a then clause, but an if expression with a then clause. That doesn't make any sense to me, at least. Why would you do it that way? Well, the only way you can think about it is because, well, they took one from Haskell and they took one from C#, and then they didn't think about whether this was consistent or if you'd ever want to change an expression into a statement or a statement into an expression. If you want to think about why JavaScript is the way it is, well, we want to think about why even Smalltalk is the way it is. You have to think about this. And kind of regrettably, all languages are dynamic in the sense that, I did have some extra super notes that I didn't really get to. All languages are dynamic in the sense that, well, in at least two different senses, I suppose. One of which is we are programming with them. And these days, any language from, well, ironically, even the more hardcore formal things, the Cox and the Agdas and the Daphnes, are really leaning in to highly interactive programming environments in the way in which, you know, kind of might be surprising. On the other side, there are languages we think of as dynamic that have what we could consider static implementations, etc., etc., etc. And I'm going to stop there because I was asked to leave nominally some time for questions, but I'm not sure whether I have or not. Thank you for your time and patience.
Thank you, James. So we have time for one or two questions. Come on, don't leave me alone with that.
So I guess I'm just curious, if we accept that all languages are dynamic, beyond the fact that we should let more dynamic language papers into POPL, what do you feel like are the implications of that? If once we all accept the premise, what then should we be doing? Are there different ways we should be thinking about how we design languages or tooling, or is it just sort of an epistemological thing? We should be more willing to not let language boundaries define how we think about ourselves, since it's all sort of the same thing anyway.
I'm not necessarily saying it's the same thing. Maybe in some ways I'm, as the French would say, denying the binary. Or there are even politicians that say that now, which is a bit distressing. It did turn out that all those French existentialists were right and that truth didn't really exist. But anyway, so part of it I think is saying, yeah, well, there's implementations, there are IDEs, there are those which in some sense are also implementations. There's the question of what, you know, where you draw the line between, you know, what's reflexive and what's not. And it's perhaps more useful to think about things in those terms. And the other thing I think is it's actually better, and you know, it took me a long time to work out some of this shit because I didn't really know Haskell, and I couldn't believe that Haskell did not have the completeness test on pattern matching. And again, I understand why it didn't. It didn't because at the time they didn't want spurious errors if they were using guards on their programs and everything was covered anyway. But, you know, so I think part of it is actually kind of looking at what actually happens in actual languages as used in actual IDEs. And I'm not saying you have to do empirical studies. You may have to do human studies, but not necessarily well, I don't think you can do double-blind studies. But you know, just being honest about the fact that, oh yeah, well, Haskell, as currently standardized, nobody's contradicting me, doesn't check that all your pattern matches are covered. You do now. You do now. You didn't. You do now if you're running the right version. I did say I'm pretty sure I was running the most up-to-date version of the Haskell thing. And if I go screaming back to here, wherever it was, okay, that didn't give me the warning. Maybe it just suppresses all warnings. I'm not sure whether it does or not, but I didn't give me the warning. So this is a Haskell system that you can and should actually pay money for because it really is pretty good if you've got a Mac.
Okay, a very short one for ending this.
Sorry.
More of an observation, James.
Excellent.
So, and kind of in support of your thesis. All languages are interpreted. The thing in my bag here is an x86 bytecode interpreter. It happens to be pretty fast.
Yep.
But the rest is all the degree of partial evaluation. So it's all a matter of degree, not really of kind.
I think so. I think so.
Okay, thank you very much for this presentation.
Thanks again for your time and patience.
So our next speaker is Maxime, talking about dynamic languages, programming implementation, maybe?
Today I'll be asking the question, are we heading towards a dynamic language winter? The notion of winter comes from an analogy with AI, where there's the concept of an AI winter, so a period of reduced funding and interest. The field of AI research has experienced at least two so-called AI winters. What some of you may or may not know is that neural networks were first proposed as far back as 1944. The concept of backpropagation was first derived in the early 1960s, but it took a really long time for the deep learning boom to happen, even though people thought about deep neural networks a long time before the current century. I think something that's also somewhat interesting with this is that there's also a connection with the field of compilers and programming languages. So when the code for backpropagation was first published, it was published as Fortran codes. So one of the first high-level languages that had sufficient degree of expressiveness to be able to express tensor algebra. And the modern deep learning boom came about after the Torch framework was released, which incorporates automatic differentiation and was built in Lua, a dynamic language, and eventually ported to Python to become PyTorch, which is the dominant deep learning framework today. So I'd like to start with some disclaimers. I want to take a critical look at our fields. I'm going to share some opinions that may be controversial. I think we could be doing things differently. It's not my opinion to offend you, but I think sometimes it's useful to be able to take a step back. My opinions are my own, and I don't claim to have all the answers or to be able to predict the future. So dynamic language winter, first thing I thought we could do is to maybe take a look at some programming language trends. So the first thing I thought about doing was to look at Google Trends, which provided no useful information. And
it's all right. You put it up on the slide.
But then maybe we could look at some programming language popularity indices. Since the TOB index is widely regarded as being bullshit, I thought I would look at a different index. So there's the popularity of programming language index. which is based on tutorial searches, which is maybe a little bit promising. So I produced this graph on an awful logarithmic scale, and we can see that in the last few years, the popularity of Rust and TypeScript, two prominent statically typed languages, has been increasing. And if we look at this data that I carefully cherry-picked, with no scale given on the y-axis, we can also see that some commonly used dynamic languages have been decreasing in popularity over the last 10 years or so. But unfortunately, then, if we look at Python, we see that Python makes everybody else look bad and break the narrative that I'm trying to construct, that we're headed towards a dynamic language winter. Python is the most popular programming language today, and it is a dynamically typed programming language. So dynamic languages are far from dead. JavaScript and Python are just as popular as ever. But these trends also take a long time to evolve, so years and decades. There's still a lot of jobs for C++ programmers, even though when I speak to people about C++ programming, I feel absolutely zero enthusiasm. So I don't think we should ignore the signs. Like, subjectively, it seems to me that there's some amount of pressure to move away from dynamic languages. I think industry wants to shift away from dynamic languages. I'm not representative of typical programmers. I'm very involved in the blogosphere, the research sphere. The average programmer is probably not a blogger or researcher. It's probably just someone trying to pay the bills and enjoy their lives. But what we know objectively is that DLS is not getting as many submissions as it used to. So it seems like there's a lot of negative sentiment towards dynamically typed languages. I see things like this on Twitter all the time. Dynamic typing is like driving a manual. Static typing is like driving an automatic. Personally, I feel like it's probably the reverse, but whatever. So why the dislike for dynamic languages? I think part of it comes down to bad gambles. So some of the most popular languages today were created around 1995, in the mid-90s, where it seemed like CPU clock speeds were going to increase forever. And there was like this mentality of like, who cares about performance? Computers are always getting faster. So, you know, Python was designed with the global interpreter lock, and in some ways, some of these languages have failed to adapt to modern computing realities where single core clock speeds are not increasing forever, and things are becoming increasingly parallel. I think there's also a question of like JIT versus ahead of time compilation. So dynamic languages are typically interpreted or JIT compiled, but there's some pressure to move away from JIT compilation. People like the predictability of ahead of time compilation. There's also mobile devices now. You can't really ship your own JIT on iOS, so that makes it more difficult to rely on JITs if you want your apps to run on mobile. There's also a push to make WASM the future universal binary format, but support for building a JIT compiler that runs on WASM is immature and incomplete, and this seems to be kind of intentional. It's like it's been coming for years, but it doesn't really seem to be happening. There's also maybe this notion that static typing is seen by many as superior to dynamic typing because it can detect some type errors ahead of time. I think this is a genuine advantage of static typing. It does make some classes of errors easier to detect, but there's also some unjustified negative sentiment, like the notion that dynamic typing is just bad or unsafe, or as the Rust community would put it, you know, if it doesn't match Rust semantics, it is by definition unsafe. And lastly, I think there's maybe an interesting parallel to make with music school and music theory. So music school puts a heavy focus on classical music at the expense of everything else. So there's kind of like a rigid notion of what kind of music is worth studying. So classical, maybe jazz, which is a recent addition. You know, there's this concept of music theory. You go to music school, you study music theory, but music theory is like the theory of Western classical music, which is thought to encompass everything that's worth knowing about music. And maybe there's a notion of classism in there as well, but other musical genres seeing as less sophisticated. Other musical genres come from people with no formal background in music theory, maybe no university background, maybe from poor neighborhoods. So the parallel is that in computer science, we have programming language theory with a heavy focus on type theory. Type theory devotes itself almost exclusively to the study of static typing. So Hindley-Milner type inference, which is the theory of typing for languages such as Haskell, ML, and Coq, which is thought to encompass everything worth knowing about programming languages. Popular dynamic languages are seen as historical accidents created by people with no type theory background. They're seen as less sophisticated and refined. And you have a language like JavaScript, which is the language of web developers, people with possibly no university background. And the notion that dynamic languages are untyped, which is kind of a slur, which is just to say that type theory doesn't really have the vocabulary necessary to express their type system. I think it's also important to take responsibility. There's this quote which may have been misattributed to Ford. If I had asked people what they wanted, they would have said faster horses. I think if you ask industry what they want in terms of dynamic languages, they will say faster JavaScript, Python, and Ruby, or maybe TypeScript, which is to shoehorn static typing into a dynamically typed language. But in some ways, I think if you just give industry what they want, you're looking in the rearview mirror. It seems to me there's a declining interest from the engineering community into what our academic community is doing, because there's a perception that academic researchers don't really care about the realities of the engineering world. Maybe because we're looking in the rearview mirror, maybe because there's a lack of novel ideas and innovation. We're optimizing technology based on past use and not really asking where is technology and the world going. There's a strange obsession in this community with meta-compilation. How many PhDs, how many papers? It's commonly accepted in this community that meta-compilation is a great idea, but there's just about zero adoption in industry because it's considered hugely impractical because of warm-up time, very high memory overhead, and also because those mega frameworks are complicated systems with lots of moving parts. So is meta-compilation a solution looking for a problem? I think there's potentially simpler ways to build VMs, and we're kind of forgetting how to build VMs and compilers in this community. So maybe we're losing track of the value proposition, what we have to offer to the world in terms of innovations in the world of dynamic languages. We spend too much energy trying to work around bad design decisions in existing dynamic languages, maybe too much energy working on meta-compilation, mega frameworks that people outside of academia aren't using. Not enough time trying to build something that's genuinely new. I think in an ideal world, academics would take risks that the industry doesn't dare to take. But in the modern world, this has become kind of inverted because there's a publish or perish culture which discourages you from taking risks and makes it so you want to take safer bets. Now that I've talked about all these negative things, I think it's useful to think about dynamic language strengths. So where are we here in the first place? I found this comic panel on Twitter and used part of it with permission. So refactoring in Rust is very painful. I also found this on Twitter. So on the left, you have a really simple piece of programming code. And on the right, you have the incantation you have to use for the type system of TypeScript to make the thing compile. So I write code in Rust on a daily basis as part of my job. I frequently run into arbitrary restrictions of the type checker. Rust makes writing cyclic data structures, which are like computer science 101, unnecessarily hard. And I feel like having to fight the type checker is a waste of my time. Statically typed languages can be very restrictive. I often get the feeling like the type system is just getting in the way. You know, it's reducing expressiveness. So static ahead of time type checking is a trade-off. It's kind of like I'm wasting time now during development, so I can hopefully save some time later in terms of debugging and troubleshooting. So I'm trading flexibility for safety guarantees, but I think there's also like different ways of making that trade-off. Like maybe we can build dynamically typed languages that have some amount of ahead of time type checking as well. So how can we innovate? I think it's important to remember where dynamic languages came from. So what's the origin story? Why were dynamic languages invented? Lisp is credited by many as being sort of like the first dynamically typed language, which goes back as far as 1960. John McCarthy was a mathematician. He wanted to express mathematical concepts in code. And so he created a language to manipulate lists and data structure at the algorithmic level. So the notion of a higher level language with garbage collection, so you don't have to think about memory management, which just gets in the way of doing these symbolic manipulations. Dynamic languages have always been about expressiveness. They came from a research environment as a way to express complex ideas concisely by working at the right level of abstraction. So my view is that the success of dynamic languages is not a historical accident. Even if you think about languages like JavaScript and Python, etc., the popularity of dynamic languages exploded with the rise of the web, where you had a fast-changing technological landscape. And so you needed very expressive languages to be able to cope with that. And now Python is exploding in popularity with the rise of deep learning, where again, you have a fast-changing technological landscape. So maybe there's a notion that dynamic languages thrive in dynamic times. And I don't know about you, but it seems to me like technology is not about to slow down. So I'm Canadian, so I had to insert a quote about hockey in my slides. Predicting the future is hard. We can still kind of try to ask the question, where's the world going? There are some obvious trends. So the world is increasingly online. We're seeing more and more distributed computing, more and more complex software systems, massively multi-core. We have neural network training and inference. We have heterogeneous computing. So can you anticipate any other technological trends? I don't hear enough people in our fields talking about these things, asking these questions. I think maybe we could ask the question, can you make the complex systems of the future easier to build? So maybe again, it comes down to expressiveness. I think if you want to innovate, you should talk to engineers. I often get the feeling that academics look down on engineering, but the notion that CS as a subfield is so kind of a subfield of abstract mathematics is kind of a bullshit notion, in my opinion. When I went to university and I studied computer science, there were people basically telling me, well, we just happen to do computer science using computers, but computer science could kind of just exist in a vacuum as a branch of mathematics. But I think that's obviously not true. Your entire career revolves around machines designed by engineers, and computer science as a field blurs the line between research and engineering, maybe more than anything else. So successful inventions often come out of necessity, and that means applications. So to have impact, it's useful to be in touch with real-world problems. Python's dominance in machine learning. Python is currently the most popular dynamic language, and I've heard through the grapevine that the Truffle and Graal folks at Oracle are starting to invest more in Python because it's the most popular language right now. But I think maybe that's also looking in a rearview mirror. Even though Python is the most popular programming language right now, I think that dominance is unlikely to last forever because Python is actually poorly suited for these kinds of workloads for a number of reasons. So you might think that this is a silly notion, but in the early 2000s, I wanted to do research on dynamic languages for numerical computing, and I was told by multiple people that MATLAB was the dominant language in scientific computing, and the scientific community would never give up MATLAB. But today, where is MATLAB exactly, right? Like, there's been a clear migration towards Julia, R, NumPy, other technologies. So even though these trends take a long time to evolve, I think it's important to remember that things do change and to be open to new ideas. And I'm going to conclude by just bringing up this paper, Polymorphic inline caches. This is one of the most influential papers in our fields. According to Google, it has 533 citations. This paper came out of work that was done on Smalltalk and Self, and this is not to say like Smalltalk and Self invented everything in the 1970s. It's more to say like Smalltalk and Self were created by researchers at a time where researchers dared to dream big and create things that were a little bit out there, and a lot of innovations came out of it. So that's it. Thank you for listening.
we do have time for plenty of questions.
Hey, thanks for the nice talk. I do agree that there's a bunch of trade-offs between dynamic and static languages. You know, these days we have gradual typing, or we are moving more and more towards that. But are there things that you see that, you know, that just won't be able to happen in that space, where like more purely dynamic languages, for whatever that definition should be, would still be able to have innovations that you couldn't have if you were kind of uniting with a more static approach in the same language?
I think that it's, well, what I see a lot from industry is kind of just a notion that people don't want new languages very much. Like they like the idea of kind of like retrofitting a type system into Python, for example, or retrofitting a type system into JavaScript. But I feel like that's not where real innovations come from. I think there's a lot of opportunities that come up if you design something new from scratch. I guess that's what I would say about that.
More by way of an observation, I really like the point you made about expressiveness, and I think that really is key because it has to do with productivity of development of programs. You know, being able to build more interesting, useful functionality in the same amount of time and expense. And you know, a key thing that's been happening over the decades of computers and computer science is people design a more expressive language. At first, it doesn't run really fast, and then the implementation types dig in on compiling and the runtime system and everything, and they make it go fast. You know, people said, there'll never be garbage collection in popular languages. Well, we saw what happened with that. So I'm not sure it has necessarily to do with static versus dynamic, but if dynamic somehow is necessarily part of expressiveness, then I would agree.
Hi. So thank you so much for the talk. I want to pick up on the point that the last speaker made and talk a little bit about what you mentioned about the web platform. So one interesting thing about how the web platform was designed is it was designed to be liberal in what it accepted and conservative in what it executed. And I think that that's part of why JavaScript was designed coming from Self and Smalltalk and other languages like that. One thing that I observed in my career is that when I began programming, I'm self-taught, so I showed up to work for my first job at programming and I asked, what can I do? And I was told, well, JavaScript's a terrible language. Nobody wants to write it. So how about you start working on that code base? And I've developed an entire career around JavaScript. And I know a lot of other self-taught people, a lot of them women, who have entered into careers that are programming within the web platform because they haven't been respected, because the discipline hasn't been respected. And I think it's interesting that we're now entering a winter, potentially, if your thesis is correct, of dynamic programming languages, because I think that those winters might be interesting opportunities for people who wouldn't be able to enter otherwise. And I'm wondering, I don't know if it's going to be the same as it was when I entered into programming, who those opportunities are going to be for. The question I have for you is, like, this is a room full of academics, how could academia sort of bring these kind of ideas like being, what did I say earlier? Liberal with what you accept, but conservative with what you execute. That's a really interesting idea that allows non-professionals to become professionals in those fields. Could we build something like that in the dynamic language space? Because I think maybe this is the most.
Yes. I don't know if it's exactly going to answer your question. I think a lot of us got into programming because we thought it was fun. And there's kind of like a notion of programming as play, you know, playing with code. So making languages accessible kind of fits into that, making systems accessible. I think if ultimately you can't really stop innovation. Like if you build a system that has less friction and that has like a real value proposition, people will adopt it. It's kind of like an unstoppable force. You just have to have like a good value proposition. If academia wants to design languages that people will use, I think they need to make them accessible. And part of that means like really simple things. Sometimes like making the system easier to install. Like if you publish a project, a system, and in order to install it, people have to run 20 commands, very few people will actually run the system. So accessibility comes in many different forms, not just the language, but also like having something that's conceived with pragmatism in mind.
Thanks. Thank you. It was a great talk. It kind of resonates with me even more because I'm recently actually more on the engineering side. So I like the points about, how academics and engineers should or could work together. But I think there is one aspect of what you said which omits a rather important point. So you mentioned about expressivity and being able to write faster and prototype, built better, or no, actually faster was probably the word. Using dynamic languages as opposed to like those that have a static type system that stand in your way and such. So the aspect that I'm talking about is cost. So it's not always just the trade-off between the time you spend fighting the static type system and then after the fact debugging or finding bugs. It's what happens kind of as a result. And in industry, dynamic or problems that happen at runtime can be very, very costly. So there's like an extra layer to it. And that's why I think that maybe there's space for both, right? I mean, there's dynamic languages you can use for prototyping and doing things faster, but in a certain setting, whereas statically typed ones maybe are better suited for like critical applications and those that if you make a mistake really cost you a lot.
Yeah, I think that's a very fair point. Like I guess my answer to that would be I think it could be possible to design a language that has dynamic typing but static type checking, essentially.
I think I agree. I'm just saying that you mentioned the trade-off of like Rust bad because it tells you too much about what you're not supposed to do versus say JavaScript, which allows you to do almost anything you want. But again, there's the cost involved in writing code in one.
That's a good point. I'll let Jan Vitek come up.
Thank you for the very interesting talk that actually puts these questions on the table. And I think it's more like around related to the comment of our colleague earlier and to your talk definitely. I think it's like the expressivity, it's not the theoretical expressivity. What we should think about is the gap in between our minds and what we want to express in our formalism. Lambda calculus, it's dynamically typed. It was invented in the 30s to think about computable functions. You have Lisp, as you cited, dynamic typed to think about mathematics, whatever. Smalltalk, invented for, amongst the problems was simulation, where you had these objects like planets and whatever interacting. Now, what is the next metaphor that we have in our minds that we want to translate in things? And for that, in Coq, for instance, the tactic language, the historical tactic language, it's dynamically typed because they were exploring ideas and they were trying to play with things and they didn't need the barriers of maybe maturation that then you want to add some rigor, some engineering into your prototyping. So yeah, I think these are some things that we should bear in mind.
Yeah, I think in terms of like things that are next thing we want to express, I know one thing that's really hard to express right now in any language is we're having systems where we have more and more heterogeneous computing. So we have all these different adapters, and like the way you interact with a GPU is by like sending a program over in a different programming language in textual formats, and just the interface is just very, very clunky. So like I think we have a very poor solutions to that problem, and it's only going to get worse. So
that's funny because in those
So this time we are done. Thank you so much. And so our next speaker will be Jan, which doesn't need an introduction, I guess. So you will not be introduced.
Okay. Okay. Hello, everybody. It's a wonderful set of talks. And with the microphone on. So yeah, what should I talk? So this is a session about the 20 years of DLS and looking forward, and I think I'm going to look back, if that's okay with you. So the point, the goal of my presentation is mostly to talk about those who are starting research and who have heard that this field is going away, that you have to be engineers, and that it's really, really hard to publish, right? So sort of all these encouragements should, make your heart warm. So I tend to disagree. I think dynamic language research happens. It happens to everyone, even good people. Fundamentally, I'm a good person. I want peace, I love love, and I believe that static types will save the world. Yeah. And I worked on a variety of things. So, ranging from, what does it say? Ownership types. I did a bunch of language implementation compilers, some garbage collection, some transactional memory, some gradual typing, and even spent about good 10 years working on real-time and embedded systems. Let's take a more numerological view of all this. I've had my hand in about 140 publishable units. This is how we count in my world. And out of these, if we sort of do a rough, sort of separation, bucketing, Trump-style accounting of them, could say that most of my work is in language design implementation, but, quite a lot is in static types. See, I told you I'm a good person. On a day-to-day basis, I have programmed in Pascal, C, C++, Java, Rust. Pointedly, I have never programmed in Lisp, in Smalltalk, in Lua, in Ruby, and God forbid, Python. Java maybe is the most dynamic language I've used sort of like day to day. And it's a very dynamic language. It's got eval. You can load new code at any time. You can do reflection. So don't discount its dynamics. But still. Yet if you go to my DBLB page, you'll find that quite a lot of my papers relate to dynamic languages. So dynamic language happens even to a good person. So what I would like to do now is spend a few minutes just sort of telling you how and why. And mostly, like the rest of the talk, this will be anecdotes. I hope that they can be useful and amusing or so, but mostly anecdotes, no deep thoughts to be found here. Don't worry. I'm the last thing before lunch, right? So how did I get into this field? So if you think over the years, in the 1990s, when I was a young pup, I'm still young, but not a pup, I started publishing. My very first published paper was actually static analysis of PostScript. The language in your printer, which is dynamic, very dynamic. And that was complete random chance. My advisor said, hey, you know, we could do an abstract interpretation of this thing. And okay, why not? Then the next bit I actually picked, and this was following Olling Shiver's work on control flow analysis. I thought, that's for functional languages. Maybe we could do something for object-oriented languages. They're not that different. So I sort of wrote a paper on that, and I mean, yeah, that was fun. I liked it. I was thinking Smalltalk at the time, but I never programmed in Smalltalk, remember. I'm a good person. So, and the last thing I did in the 90s was to work on how to implement these languages. So there I was doing message dispatch implementation, and the target was Objective-C. But I never programmed in Objective-C. Then we switched to the 2000s. So there I spent a whole lot of time implementing Java for embedded systems. So Java is a dynamic language, but yeah, that's not the most dynamic setting. And towards the end of that decade, I somehow got in contact with IBM, and they wanted to develop a new language that would bridge scripting and programming, and we called that language Thorn. And so we did a bit of work on that. But yeah, so that was a fairly static decade. Then things got more interesting in the 2000s. So in the 2010s, we pushed on that Thorn language, and we actually had that question in mind about those types that lie. So we had types that don't lie, which we called concrete types. They're real. And we had the like types, which we called like types, which were these aspirational types. And then a little bit later, sort of pushing on that same direction, I hooked up with Matthias Verleisen at Northeastern, and we wrote a paper that showed that most of the academic research in gradual typing was hopeless. And both of these got into POPL, and that was so fun. I thought about just putting one Greek letter somewhere just to you know, no, but no. So then the work on Thorn kind of died because IBM pulled the plug. And so I switched over to looking at different languages, and it was good because the question I wanted to answer was, well, why do people need dynamic languages anyway? What is it they like to do with them? And that led me to analyzing large corpuses of code. And where did you find larger corpuses of code? Well, with JavaScript, right? Any website has code and it's runnable, so you can run it, dynamically analyze it, and start to understand what it is people do. And that was a long set of papers, very interesting. And you know, like the answer is mostly they'll do anything. A lot of time it's good. Well, no, let me admit it. Some of the times the crazy stuff is good. A lot of the time it's just mediocre laziness and so on. And then I decided that I needed to work on a language where there was actually a chance of helping people I cared about. So I picked the language R, and I started looking at R as an object of research and working on it. And then the last few years, well, we keep doing work on R, and there is even a paper at this UPSLA on RJIT. And we also looked at Julia. Julia is a wonderful dynamic language in which there are more type annotations than in Haskell. And as a side note, we found out that the subtype relation is not decidable, which is like a lot of fun when you have a dynamic language whose subtyping can't terminate on all inputs. So, all right, so that's sort of the breadth of it. Now what I want to do is tell you a little bit how, you know, sort of philosophically, how one can approach doing research in dynamic languages, especially when one doesn't really use dynamic languages most of the time. And for this, I'll tell you an anecdote about Northeastern. So at Northeastern, every year we have a session where new students come to meet faculty, and we present ourselves, try to sort of show ourselves in the best of lights, and usually Olin Shivers starts, and he talks about purity and elegance. Doing research in PL is to, I'm trying to get this right, is to strive for true beauty of expression. And usually I come a bit later and I say, yeah, I'm an ambulance chaser. I'll come after the wreck, try to pick up the pieces that are salvageable. That's been my approach and it works. The uglier the language, the warmer my heart feels. So why reject purity? Purity has a lot of positives, but it usually means you're building things ex nihilo. So we try to do that with Thorn, and one, it's a lot of work, which I always try to avoid, but even if you succeed, which we didn't quite, but even if you succeed, how do you evaluate your success? How do you know what you have achieved, right? The point of a programming language is to help people express their thoughts. If you have no users and no programs, how do you know that you have helped anybody? So, and that's a real problem, right? I mean, if you think about doing a new language, my point to my students is always, what is your experiment? What experiment are you going to have in the paper that will convince the dreaded reviewer 3 that this is worth publishing? So what I've done in my career was to always try to say, well, what's something that is used by real people, and what are the real problems they have on a day-to-day basis, and can we do something to help? Ambulance chasers. So let me illustrate this with some work we did on JavaScript. So at some point we had this idea of what do JavaScript's program really do? So we took a lot of websites, we sort of somehow had analyses that showed what people were doing. And one of the things we noticed was that the behavior on websites, real code, was so different from the behaviors people had on benchmark. So this is about 2009-ish. And so these graphs, I'm not going to explain them in more detail, but just to say on the left, you have the Sun Spider benchmark. On the right, you have the Google website at the time. And let's just say one or two things. So the yellow thing, the yellow color suggests, so the idea is these are over time what you do to an object, sort of a summary of the life of objects. And the fact that it's a big square box means that objects live for the whole application. They never die. In the Google site, over time objects disappear, so you see this sort of gradual tapering off. The other thing in Sun Spider was that the red spikes here are operations on an object, and especially operations where you add properties. And basically, what happens is you create objects, you add a bunch of properties, and then you read them. Google website, yes, you create an object, you add a few properties, and then you update them. So this looks more like a functional language, this looks more like an imperative language. So we thought, that's funny. If people are using these benchmarks to drive the development of their research projects or industrial browsers, maybe there's something not right. So that sent us chasing down a path where we built a tool to generate benchmarks. And my student, Gregor Richard, went to Microsoft Research, where he built this automated record replay systems. He implemented the whole thing, he had the paper ready, and then the research side was shut down by production, which said, oh, this paper that you're about to publish, it's not going well with our marketing strategy for our latest doomed browser. So the tool was shelved, the paper was killed, we went home. Learning, sort of one teaching moment. If you work with industry, make sure that you contractually have the right to keep your source code, the one you wrote, and publish the results. If not, So, but it didn't end too badly. A year later, Mozilla reached out. They wanted the tool, so Gregor went to Mozilla, re-implemented the tool from scratch. We wrote a paper for UPSLA with Brendan Eich, Mr. JavaScript, and Mozilla never used the tool. At least not publicly, I'll tell you why. But Apple, where my student Phil Pidzlow was, did make us think about it. So this is their keynote, and they have Safari, and they have the JS Bench suite. That was the thing we were doing. And so, yeah, we're so good. So what happened? What happened, as the best I can tell, is that, so this is back to this Sun Spider benchmark, and this, the other line is the Amazon website. And what you see here is performance of versions of Firefox, speed up, so higher is better. So we start with 1x, and on Sun Spider by version 3.6, you're going 13 times faster. Really good. And then when we run with our benchmark, and and the biggest discontinuity comes with the tracing JIT technology that was introduced at that time. When you run on real-world benchmark, you're running three times faster, but the tracing makes zero difference. Okay? Remember, the behavior of Sun Spider had nothing to do with real-world behavior. Right? So you were optimizing for something that isn't real. So one of my research contributions is to kill research directions. Thank you very much. All right. I told you I like mine ugly, but how ugly? So I mentioned I work with R, so let me amuse you with little bits of R. I find them funny. So the first bit of R is not particularly funny. This is just a small detail. R, if I call this function with two print statements, what will I print? Well, I end up printing 0 because R is the most widely used lazy programming language in the world with millions of users, dynamically typed. Yeah, the first argument is not evaluated, the second is. Okay. No big, we know laziness. Let me amuse you with something more fun. Here's a function 2, and I give it argument 3. The question is, what will it print? And if you know R, you know that it will print the vector of 3 plus 1 and 3 plus 2, 5, 4 and 5. Now, how do you get there is interesting. So you notice that the function has a variable named C, as it's up for its parameter. But C happens also to be the name of the most widely used function in R, which is the function that creates vectors. And they have a single namespace. It's a dynamically typed language. So how does this work? Well, you get to the first C when you're evaluating, and you have what I call context-sensitive name lookup rules. So you're going to say, this first C is in the context of a call. So I'm going to look my environment, find a definition of C, and check, is that definition bound to a function? If yes, I can call it. But here, it's bound to 3, so no. So I keep going until I find a function. And the second definition of C just finds 3. All good. And here's the trolling part. If I call 2 with bad as an argument, what do I get? Well, I get clearly symbol C not found, so same thing. So what is going on? So bad is not evaluated. So what happens is when I call C, the first C has to be found. I have to, so I look in the environment, I find that's the parameter. Is it bound to a function? Well, since R is a lazy language, I don't know. I have to evaluate the argument to know whether it's bound to a function. As a side effect of evaluating the argument, well, I call bad, And what does bad do? Well, bad, it says, walk your call stack. If you find a variable C in your caller, delete it. All right. My ugly duckling is ugly, yet millions of people use it. So another thing I spent a lot of time doing, and I had, it was amazing fun, is actually looking at how these languages are implemented, and more specifically actually implementing them. So spent about 10 years working on Java, and this is a really dynamic language, and then I spent another 10 years working on R. Each iteration, each n in this list, you can assume that n minus 1 was a failure, right? So now we're at this last compiler named sh. We hope it'll work. It hasn't failed yet. So why is it so hard to implement languages that are dynamic? Let me tell you, so we had a paper at DLS in 2019, and it did a reasonable job of summarizing the difficulty, and its title is enough to actually sort of feel the pain. So say I want to, I have to stay here. So say I want to compile this function in the middle. So it's a piece of code, and it's going to call other functions, and it gets arguments. So in a dynamic language, we have to worry what those other functions will do. Will they add new code? In the case of R, will they delete some of my local variables just for fun? Right? So I'm already sort of stressed out about what this can do. So maybe if I'm calling functions that are local to my package, maybe I can do some interprocedure analysis and get a good guess that it's going to be safe. Maybe. But then I'm called by somebody. And whoever calls me is sending promises, unevaluated computation. So anytime I read an argument, I will trigger computation. That computation may cause reflection, cause new definition, cause variables to be deleted. So in order to compile a function, not only do you need to know what's below you, but what's above you. So basically, it's like this tangled mess. And unraveling it is what causes your brains to melt. Okay. And it's also an interesting point of the tension between static and dynamic, right? You say this and you say, well, wouldn't it be nice if the programmers could tell us, yeah, but these arguments, they really are not going to delete your variables. A little bit of annotations would be nice. And the problem is, as soon as you start doing that, you restrict the expressiveness of the language. You remember I told you earlier that people do a lot of crazy things, and often these are, or sometimes they're for good reasons. Well, you would lose a number of use cases. And your language would become less usable. And I'll spend one or 2 minutes on usability. How much do I have left? 5? You see? 4. So I'll be faster. So I spent a year working for a startup that was doing some security work, and they had a pipeline where they had 50 Java programs that had embedded strings of SQL that would generate the SQL dynamically, send it to a distributed database, run it on a cluster of 1,000 machines, roughly, so heaven. And the boss said, Java is a horrible language. We have to kill it. We will program in Rust. And I thought, you know that you've hired 600 Java programmers in the last 2 years, yes? You have a plan for training them, yes? No. The reason I left doing ownership types is I was thinking nobody could use this. This is too much of pain on programmers. So basically what they were doing was a big data analysis pipeline. And I thought, well, I could take some of the steps and see how to re-express them. Right now it's Java and SQL embedded. What would it look like in R? well, this is just an example, but it sort of gives you this idea that I can read two CSV files, I can group them by name and age, I can add a column that has the mean weight, I can join the tables, I can compute, I don't know, my weight times my salary because it's interesting, and return that. Okay? So that's a data analysis pipeline in R. I don't do Python, I've never did, and I will never, but ChatGPT gave me the equivalent Python code. Python code looks like retarded R. It's R from about 10 years ago without Hadley Wickham at the board. So it's okay, you know, but you see there's way more strings. Whenever you see strings, you sort of have to say, yes, this is not going to end well. And then I wrote the code in Rust. Wonderful. It has even more strings. So the Rust code is unreadable, unmanageable, untyped, and slower. So, yeah, usability, it's important. So I'll conclude. So parting thoughts. Well, what I've been telling you is that if you want to do research in this field, think there's 4 things that are important, and most researchers just do the last one. So the first thing is you pick yourself a community that you want to be in. People that are doing something interesting, or people that you like. For instance, in R, I like statisticians. They're nice people. They're not practical, but they're nice, on average. And then you sort of look at what they're doing and you find what is it they're doing that's bad or painful or that they don't like. That leads you to actual problems that are real-world problems. And then you go and you do the thing that you do, which is propose great solutions, blah, 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 blah. But if you don't do the first 3, you're left to think of solutions. How do you know they will connect? And if you don't have the first 3, how are you going to evaluate your solutions? All right, so thank you very much. It's been a pleasure to talk to you and to sort of misattribute one Kubrick to another. It's full of dynamic languages.
So we have time for a couple of questions.
So funnily enough, we have at least 3 people from the JavaScript team at Mozilla here in the room. And it's actually kind of delightful because as you were starting to introduce this benchmark creation thing, Matt leaned over to me and was like, wow, we should really get our hands on that. And this all happened before our time, but I did think it would be nice to point out that like the web browser community has slowly but eventually come around to the standpoint, and like, you know, the creation of new benchmarks that actually match the real web is something that's being actively worked on this year. So the industry does eventually catch up. It just takes us some time.
My point was not to sort of disparage. My point was one of, you know, sort of more philosophically, how do you find problems? You find by looking at what is happening. And yes, of course, since then, people have done much.
Please do disparage. It was, okay. It was correct.
No. I'm a good person.
If you're a good person and you're designing a new programming language, presumably you'll do a static one, right? But you gave that example of what it looks like to do data analysis in Rust. Could you just explain what you believe? Like, what did Rust do wrong? How could you do better? Or should we just use R?
So if you're, okay, so you've packed a lot in a sort of fairly tight package. Of course, you all use R if you're doing static data analysis. For data analysis, it is objectively really the best tool. Now, if you sort of zoom out and say, well, as a programming language, could we have something that has the benefit of Rust? And so why do I like R for data analysis? Because the programming model in data analysis is your programs are irrelevant. The only important thing is the data. Your programs are just there to excite the data, to get a little bit of insight. And you will throw them away 99% of the time. So what you're doing is you're trying things, because you have no clue. You try things, and then you get something. And then maybe you want to deploy it. So I remember Netflix was using R for their data analysis, and then for deployment, of course, you can't use R, so they would recode everything in Java, which is horrible, right? Because now your edit debug cycle is very long. I was told that one of the reasons they had a big failure for their pricing model was that they were testing their code on a small data set in R, and then they deployed it, but yeah. So what you want is both, right? You want to have the types when you care about, when the code is becoming more structured, rigid, like you want it, but you would like to not have the types while you're experimenting. So, to go back to this, is Rust, the right answer? If you could tell Rust, stop checking this file, just interpret it, compile everything else, but this, I really don't want you to bother me with your type errors and your ownership and your borrowing and all of that, because I don't know yet what I'm doing. And then, start. So it's something like, sort of stop getting in the way while I don't know. And when I need you to get in the way, start getting in the way. I don't know how to do that transition nicely. I mean, we've been looking at it with these gradual type languages, but that may be not yet exactly there. So it's still an interesting research topic.
Thank you. Do we have other questions?
Thank you for the talk. From an industry viewpoint, developer productivity is one of the primary things that companies are trying to optimize for, because that's one of the biggest expenses that they have. Human time is one of the most valuable things you have in a company. And until your talk, I haven't seen anyone actually mention that. We just keep talking about programming languages and how expressive they are, but we never talk about how much time we're saving developers, or how much safety guarantees we're giving them, or how flexible it is for them, or how fast can they develop their software. Would you agree that that's an important thing for researchers to strive for as well?
Oh yes, but it's also the hard thing. Remember, we're all lazy gits, right? We'll go towards the easy answers. The hard thing is, well, I keep bugging friends at Meta that they should publish a paper on their experience with Hack, right? Went from n million lines, because you can't say what n is, to n times m million lines of code, while gradually tightening the screws. What worked? How did they get there? What were they? There's like a wealth of data that would be so cool to have. Yeah, there's a rejoinder.
So we are getting more and more obsessed actually about productivity at Meta, and that is what we now have to use to justify work on programming languages. And that, so we have to argue why static typing, say, is going to improve programmer productivity, or some IDE feature, or whatever. So it's a kind of interesting place to be now, because we can't just say, yes, obviously it's the right thing here, and just appeal to general trust in programming language folk. We have to actually justify in terms of productivity.
So give us the data. We'll help, right? I mean, we have armies of unused grad students who are currently, finishing their POPL papers, but we could retarget.
Okay, I think we are done for this session. Thank you so much, Jan, one more time.
working. Yeah.
Ah, okay. Is it a video? If it's while last question or something like that, I will tell you, try to set up while we finish the question so we can be smooth. Yeah. Perfect. Thank you. One more minute. Yes, correct. It's just yeah, I think like you have to, if you want to set up a single like a mirror, as you wish. This only wants HDMI port. Yeah. I have USB. It works. The monitor's got Okay, so welcome everybody. Let's start the third session of DLS. So it's my pleasure to present here Kevin Maynard from Shopify. He's going to talk about JIT are nice, but why aren't we using them? So, floor is yours.
All right, thank you everyone for having me. Flip this around. All right, so in keeping with the theme of this year's DLS, we're looking at where the next 2 or 3 decades of dynamic languages might go. It's a really broad topic to cover in 20 minutes, so I'm going to focus really on just JIT compilers and why we aren't really using them. So by way of background, I work at Shopify. I'm an engineer there, and I've contributed pretty heavily to the Truffle Ruby implementation of Ruby. I've worked in industry for a couple decades. That's not to convince you I am a captain of industry or anything like that. It's just there's an astonishingly high percentage of people working on optimizing runtimes that have never actually written code. So Shopify, we're over 5 million lines of code. We have a fairly modern development process. We do everything through pull requests that kicks off a CI process. If the repository is connected to a service, upon merge, we'll initiate a deploy through a continuous deployment process. We open pull requests automatically for security things, so a large amount of our CI is actually triggered not by humans. We make extensive use of Rails. This is a MVC web framework for Ruby. It came about at a time when web frameworks required a lot of XML configuration and were mostly written in static languages, so they had a compilation and deployment step. Rails puts a premium on developer productivity. So this is a console session. We can see is if we call find by name and age on this user class, that method does not exist. It's making use of Ruby's metaprogramming facilities, and Rails registers a message missing hook, which it then takes to break apart the method and dynamically construct an SQL query. So this makes it really efficient to work with data. Likewise, in Ruby, you can modify the core classes, you can redefine methods and things like that. So Rails makes use of that to add these helpers on core classes that make text generation easier, which is useful for API responses, email generation, and web pages. So performance matters, but so do other things. So we make use of Rails knowing in advance that it is not the most efficient way to do things because it allows us to focus on building applications easier. So we make technology choices. Peak performance matters, but consistent peak performance is even better. We look at performance at different percentiles, and if there's a huge amount of variance in there, it makes it very difficult to do capacity planning or know when something isn't working. We care about test performance. We care about developer productivity. We need to be able to hire and retain people. They need to enjoy the stuff they're working on. Security is a concern, maintainability, our ability to measure and diagnose issues at production, and code compatibility. So when we talk about performance and why it matters in industry, it really boils down to three things. One, it makes the application faster. That's pretty straightforward. If we have higher peak performance as a web-based software company, it means generally our response times go down. It makes for a better user experience, makes people happy. Cynically, it makes revenue go up. But we can also reduce our operational expenses. We do cloud-based deployments, so we got to pay for whatever we allocate. If we can run on smaller machines or run with fewer machines, then that's a realized cost savings. And finally, we want to save developer time. So we hire really talented engineers to work on building out the Shopify application and the back-end services and such. We don't want those developers trying to work around performance limitations of the VM. Likely they don't have a firm enough understanding of the internals of the VM to really know what the problem is, and whatever solution they come up to work around it probably is going to be difficult to maintain, but also we're finding is difficult to JIT compile. So we're trading off a short-term performance gain for something that actually hampers performance longer term. On the topic of performance, though, I just really want to emphasize that peak performance isn't everything. I think this is a topic that perhaps gets lost on a lot of academics, where test time is viewed as this thing where, well, it's not exposed to the end user, so they don't care. But again, developer time is a huge, if not the largest expense for a lot of software-based companies. I think you'd be amazed to know how much time and effort and money has gone into optimizing test suites at big companies. And that spills into continuous integration too. I know there's this belief that because it's asynchronous, who cares how long CI takes? First of all, I don't think it's actually asynchronous all the time. If it's fast enough, no one's going to switch context and begin on something else, just come back a few minutes later. So we may have developers waiting around for it. We want consistent test time as well. If it takes 3 minutes most of the time, but 17 minutes, 20% of the time, that's difficult for the developer to work with. But even then, if you cut all that out, because we do continuous deployment, a slow CI means it takes longer for us to deploy bug fixes. And just from a simple resource allocation perspective, we have a fixed amount of capacity in our CI environment. If the queue gets too large, we need to expand it, so it's going to cost more. So when we're talking about performance, for us, we're running Rails, so this is going to be a really deep web stack. It's quite comprehensive. It's way more involved than what you'll see in typical micro benchmarks. For that reason, like a 1 to 9% performance improvement is actually quite meaningful for us. At the scale we operate at, those kind of small gains actually accumulate, and we're willing to invest in something like that. at the 10 to like 100%, that's fantastic. And we're building a team to do that right now. So Shopify invests in YJIT, which is a JIT compiler based on Maxime's research in lazy basic block versioning that's built into the reference implementation of Ruby now. And at the 100% up, this is where I think a lot of the various talks and peak performance really want to get. That is remarkably compelling, but in all these cases, there are the attendant disadvantages of slower warm-up and slower test time. So I'm actually working on a project to integrate Truffle Ruby into Shopify, and it doesn't help if Truffle Ruby gets faster, basically. So it's already a huge performance advantage in cases that we've seen over the status quo. So continuing to make peak performance faster isn't actually going to materially change our ability to adopt it. It would be better if more time were spent on addressing things like warm-up and memory consumption. So I work in a group called Ruby on Rails Infrastructure Team. This is a small support team at Shopify. We're tasked with ensuring the long-term longevity of our core technologies, principally Ruby and Rails. A lot of that is around CRuby, the reference implementation, although we try to be good stewards and make sure that our stuff also works well for alternative Ruby implementations. But interestingly, Shopify is investing in 2 different optimizing Ruby runtimes at the moment. So there's YJIT, which is the JIT I just talked about, and Truffle Ruby, which is a complete new re-implementation of Ruby based on the GraalVM platform. So it's going to use the Truffle framework for self-optimizing AST interpreters and uses partial evaluation to generate its peak performance. Sometimes we get asked, why are we doing both? And that's the fun part about Shopify. We care about the long-term health of Ruby, so it makes sense to invest in both of these. It's quite likely that there'll be a place for both. It's rare that one JIT fits all sizes, and we're just operating at different timescales here too. So I've kind of just talked about Ruby and Shopify. I have some operational experience with other dynamic languages, and the experience is quite similar there. I also have colleagues at other tech companies, and I think everything I'm talking about here is pretty widely applicable. So I won't get into all that for time constraints. So when I was working on this talk, I found the question of where dynamic languages will be in 2 to 3 decades kind of intriguing, and then worked backwards and said, well, what if we asked ourselves that 2 or 3 decades ago? Would the current crop of dynamic languages be what we came up with? And kind of surprisingly, the preeminent dynamic languages of the day right now really did get started 25 or 30 years ago. And I'm not sure anyone really thought that is where we would be. Part of it is these languages got to start at a particularly interesting time. In the 90s, I don't think anyone really liked the programming languages they were using. They weren't terribly ergonomic, and that left a lot of opportunity for experimentation with different syntax and semantics. And so we ended up with Python and Ruby and PHP. But on top of that, the static languages weren't really that good either. They were really rough around the edges. A lot of them actually required commercial licenses. So if you were a new student at the time, and there were a lot more getting into the field, you could download Python for free, and you didn't have to deal with an awkward type system. You didn't have to deal with memory management, and you didn't have to pay a license fee to Borland. So that really allowed dynamic languages to thrive. And even then, we knew interpretation was slower than AOT, although the AOT compilers didn't have super sophisticated optimizations at the time, but we were also benefiting from rapid advancements in CPUs that helped kind of paper over the interpreter performance. So if we look at Ruby, for the first 16 years of its life, it shipped as an AST interpreter. I had to deploy this in production. It was not fast, it was not memory efficient, but Rails marked such a huge improvement over the status quo that it was worth going with. It took almost 25 years for Ruby to get a workable JIT compiler for it. And all this seems remarkable to me. I think it'd be really challenging to get a new language off the ground and expect any production deployment with only an AST interpreter. All right, so kind of cutting back. We're not in the 90s anymore. The environment's different. And a lot of that has to do with cloud computing. So you used to be able to buy or lease hardware, and you knew exactly what you were getting. You could even over-provision if you wanted. But nowadays, at Shopify and a lot of companies, we work with cloud computing. Cloud computing has been great for startups. It allows you to get going without a huge upfront investment, but we've given up something in return. For the most part, you're running on a hypervisor, so you may have some performance disadvantages there. But you're working with these abstract machine definitions. So you don't know what the clock speed is. You don't know what the processor family is. And if you're kind of budget-minded, you're probably working on oversubscribed hardware. So you have to deal with things like CPU steal and leaking data through speculative optimizations. Moreover, RAM has gotten expensive. And this seems kind of weird because we can buy tons and tons of RAM for fairly cheap now. But a cloud provider can't really oversubscribe RAM. The only way to do that is with a really efficient balloon driver, and we just don't have it. So you'd have to page out, and that's not great. So in practice, what that means is if you need an extra gigabyte of RAM, you probably need to double your machine size and double your costs. So there's a huge impetus to try to keep your RAM consumption down. So cloud providers really optimize for small machines and going wide. And we even see that with CPUs now, where they're not really increasing CPU clock speed, they're adding cores. And our current batch of interpreters aren't really well suited for this. Having a global interpreter lock, I think, is a liability in 2023. There's also functions as a service. This really favors static languages, and I think dynamic languages need to find a way to address distribution to make it easier for you to shift that workload to another server. So for new languages and the current ones, I think we need to start to adapt to the new compute environment. With our current batch of languages, it seems unlikely we're going to just up and drop them, but if you're working on a new language, you do need to take this into account. And unfortunately, I really think it would be challenging for a new language to gain traction. I don't really have a good mind for new syntax and semantics, but from a practical point of view, if a new language wants to be adopted, it needs to have some selling point. And the current batch dynamic languages have a huge amount of libraries and an ecosystem built up for them. But those languages have also evolved over the last 3 decades. So they haven't been sitting targets. On top of that, static languages have learned from dynamic languages and now have more developer productive features. They ship with package managers and test libraries, and they've replaced the verbose type systems with type inference. They have better tooling, and so on. And as I mentioned, we have a much higher requirement for performance these days. So if Ruby were to come out today, I don't think it would be a success relying with its slow AS2 interpreter. On top of that, we now need to be able to monitor things, and we need to be able to debug them. So these are baseline requirements for building a new language. And we're seeing Python excel by being able to integrate with external libraries. I think that's going to be something we need to consider and have as a first-class feature in any new language. All right, but coming back to the mature languages, we've known about JIT since the 60s, and we have all these really popular dynamic languages, and outside of JavaScript, like none of them have JITs used in wide-scale deployments. So why is that? If we look at Ruby again, Ruby has actually had a lot of research poured into it. Even now, there are several active implementations of the language, some pushing on different avenues of JIT compilation, others on AOT. And there's a whole kind of graveyard of projects that were started and no longer live on. And some of these predate Ruby's own adoption of a bytecode interpreter. Out of this list, only JRuby has had any amount of success, I think, and even then it's basically a rounding error. I think most people use it more for its Java interop than its ability to optimize Ruby. So what happened? It comes back to these factors and technology choices. It's not just about peak performance. But moreover, for a language like Ruby or Python, it's really difficult because there isn't a language specification. So compatibility really becomes whatever the reference implementation does, whether that's intended or not, and developers will build around that. On top of that, because these languages didn't have excellent performance, there was a huge corpus of native extensions that came about. And kind of getting to the point I had about more efficient up and down calls, these languages don't really have a native extension API. What they do is they expose all their internals, and then people use that. That's created some challenges for the languages to evolve, but it really makes it difficult for a new implementation to come along because they need to treat these internals as if they were a stable API. Truffle Ruby can do this, but it pays a performance overhead in doing so. And then crucially, warm-up and test time have been problematic with all of these alternatives. It's really hard to compete with a hand-tuned bytecode interpreter. Tooling's also a problem. So in the JVM, we have a standard tooling interface. We don't have that in Ruby or Python. So if you want a profiler, those end up becoming implementation specific as well. But we have had JIT successes. So broadly, I think that comes down to two categories. We have those that optimize for the VM at the bytecode level. Hotspot pushed on this really hard in the 90s and is probably the state of the art. And then on the languages side, there's no shortage of JIT compilers for JavaScript. Lua has done well with LuaJIT, and Ruby now has YJIT. So these implement the semantics of the language directly, allows them to generate really efficient machine code. And we know that they work. Both Hotspot and the JavaScript JITs support a huge amount of the world economy. But if we dig into the JavaScript JITs, well, first of all, we see there's a lot of them. So basically every browser vendor has their own. That's kind of be expected. There probably wasn't a ton of collaboration. But several of the vendors have multiple implementations. And that gets a little concerning to me because JavaScript just isn't that complicated of a language. So this gets to a point, I think, about language-specific JIT compilers. While they can generate really efficient machine code, they're incredibly expensive to build. All of the major ones, except maybe LuaJIT, have had corporate sponsors. They came out of a time when companies owned languages. JavaScript's a little bit different because companies own browsers, but there's a big mismatch, I think, between that world and the current one where we expect languages to be developed in the open. And when someone doesn't own it, it's really difficult to expect a group of enthusiasts to try to match what Hotspot can do. Ruby's got an interesting situation where it was developed in the open, and there is now a company investing in a JIT compiler, but it took 25 years to get there. These language-specific JITs seem really difficult to maintain. I've never actually built one, but the fact that we seem to get to a point where they need to be rewritten suggests to me that the choice of your IR or what semantics you're going to optimize may make adapting to growths in the language difficult. And I find that the JITs really work best when they're developed in tandem with the language. So LuaJIT ended up in a situation where it made some assumptions about the representation of objects, and then Lua core evolved away, and now there are compatibility problems. All right, so if JIT compilers are how we plan on really unlocking the performance that people are looking for, how do we streamline their development? Because this doesn't really seem scalable to me. So there's two options I see. One is we can do bytecode generation. So like JRuby will do this. It generates JVM bytecode. Now it uses invoke dynamic, and it even layers in its own Ruby IR so it can do language level optimizations before it generates the bytecode. And this works pretty well. You get to benefit from all the work going on in Hotspot or Beam or what have you. But the bytecode that you're targeting almost certainly will not support all the language semantics you want. So then you have trouble optimizing those. You might not even be working in an area that's supported, so there's no guarantees about that bytecode being stable, perhaps. But more critically, this is a major dependency you're taking on. So for something like JRuby, you need to run on the JVM. You might be able to use GraalVM native image to ahead of time compile that away, but that option doesn't exist for all VMs. So the other approach is metacompilation, and this is kind of similar. Now we're going to delegate the construction of the JIT compiler to another tool. And I happen to really like this approach. I find it really rare for someone to be an expert in language design and in VM design and in compiler architecture. So with metacompilation, you can focus on the semantics of the language, implement them once, and then let someone else that might be more familiar with the low-level ISAs and whatnot to generate efficient code for you. So the two main projects I see for meta-compilation are Truffle and RPython. These both make it really easy to build interpreters. So it's really nice if you want to experiment with things. You don't have to deal with low-level C or C++. You get higher-level abstractions. You don't have to develop your own custom byte code. They'll also give you some additional functionality for free. Truffle gives you a regular expression and a string subsystem, so you don't have to do that. Truffle will also generate a debugger and profiler and heap dump for you, so you get all that stuff for free. But most importantly, you get the JIT for free. So it's a way faster way to develop languages. All right, so now we're just kind of going another level. If meta-compilation is so nice, why aren't we using that? So Truffle and RPython, like I said, I think are the two big ones in this space. They're just not fit for existing language implementations. You can't bolt them onto the current interpreters, even if the underlying mechanisms of partial evaluation and meta-tracing theoretically could. So what you're left with doing is re-implementing the language. And that turns out to be incredibly expensive, just as building a language-specific JIT is. On top of that, you may run into issues where Truffle or RPython can't optimize particular language features the way you could if you were to handwrite it. But most importantly, warm-up time and memory suffer with these two frameworks. So if meta-compilation wants to succeed, I think we need to take in the realistic concerns of deployed software more seriously. So in particular, we need to handle those non-peak performance concerns. We need to be able to run tests in a time-efficient manner. We need to be able to run on cheaper VMs and things like that. What this comes down to is, I think there's a lack of fine-grained control over the code it generates. I would love to have a system where I could sacrifice peak performance by slowing down the warm-up cycle or reducing the total amount of memory. And the only solution I've really seen put forth there thus far has been tiered compilation, and that just hasn't really been enough. So where will we be in 2 or 3 decades? I think the future of dynamic language is actually still pretty bright. So the current crop of languages, I don't think are going to go anywhere. Ruby, Python, well, Python's more popular than it's ever been. PHP, these languages power a huge amount of the economy. So whether they become legacy code or if they're going to keep thriving, I don't really know. I know at Shopify we're investing in Ruby, so we're hoping it'll be thriving. I see dynamic languages also needing to converge a little bit with static languages. Gradual type systems have helped the problems with maintaining large dynamic code bases. I'd love to see more low-level access things, so you don't have to sacrifice so much performance by using a dynamic language. But more to the point, I don't see interpretation being suitable in the future. So if you're working on a new language, I think you need to take performance more seriously as a baseline feature. If you're building a new language, I absolutely would start with either RPython or Truffle. You get a huge amount of value right out of the box. If you find that these approaches don't work very well, like you could gradually replace them with something more hand-rolled, but I think they're a great way to get started. And they allow you to get feedback as you're developing your language. So you don't end up in a situation where some cool feature you add just can't be optimized well. Our dynamic languages went through something of a midlife crisis over the last, 5 years or so. We saw a lot of large tech companies trying to solve the same maintenance problems. Principally, how do we get new engineers working effectively in these large code bases without types, and how do we scale them? So we got gradual type systems out of it. There's renewed investment in JIT compilation and other optimizations. Some kind of gave up and they developed languages like Go and started replacing services. But I think dynamic languages are actually in a really good place now. And I think this competition has forced dynamic languages to really up their game. So for the future of JITs, it really comes down to whether these language-specific approaches or meta-compilation are the way forward. There's an open question, I think, of are these maintenance burdens of language-specific JITs or the warm-up time of meta-compilation just inherent to those two approaches, or are they engineering challenges that we can solve? And if we want to solve them, then we actually need to invest in doing that. So I kind of see it as a race. Will language-specific JITs find a way to become easier to maintain and build quicker than we can solve the startup and the memory consumption problem at a compilation? And yeah, thank you.
Thank you, Kevin. Thank you, Kevin, for the talk. So we have a couple of minutes for questions. Questions in the audience? Anyone? Okay, I have one while we warm up. So you mentioned this meta compilation part. Are you thinking about being more specific? For example, thinking myself something like Graal snippets, something like that, so you can gradually load constructs, high-level constructs in something more specific to get performance. So it looks like a compromise between high-level workload or high-level expression of constructs and performance that you can get.
Sorry. Well, what I was suggesting is, particularly for new languages, you don't sacrifice much by adopting one of these frameworks. It'd be like using a parser generator to get going and then realizing later that you actually want to hand roll something. So then you could gradually start replacing parts if you found you really wanted a customized bytecode interpreter. But I'm hoping that Truffle and our Python continue to advance such that you find you don't actually need to do that conversion.
Okay, thanks. More questions? We have one back.
Yes, you mentioned LLVM, for example, in passing. Does the existence of things in the machine or architecture independent JIT compilation space, I think, like if you could do a JIT version of LLVM or WASM is another example of something that's down close to the machine, but you're not having to deal with the details of exactly what instruction set do you have. Does that help address any of these problems effectively, or is it still too big a gap?
Yeah, so part of this is I think the techniques are sound, but the actual embodiments have been problematic. Every project I know that's targeted LLVM has ended up coming to regret that because it's just not a stable IR. So if you want to support a new version of LLVM, then you got to start going back. And so there was a project in Ruby called Rubinius that did that, and they basically had to rebuild the whole JIT. So I'm a bigger fan of things that will just generate the compiler for me. Like I'm decent with x86 64 assembly. I'm terrible at RISC or ARM. So if I can get something to actually generate that for me, that's a huge win. But yeah, the two big ones at the moment have problems. I think they've been very good at proving that both partial evaluation and meta tracing are valid approaches to optimization. So if those two frameworks aren't the way forward, then I'd love to see what the next thing is.
Okay, time's up. Thanks, the speaker again. Next talk, it's a pleasure to present Andreas Rosberg. He's gonna showing us keeping the assembly in WASM, running high-level languages on the low-level VMs. So, floor is yours.
Yeah, thank you very much. So when Stefan asked me to give this presentation, I was thinking like, oh yeah, interesting idea. And then a couple of days later, I thought like, oh God, what should I actually tell? So I should apologize in advance if for those of you who have seen my talk on Sunday, there will be some overlap with the slides here because I have to do some kind of similar scene setting here. So I hope that doesn't bore you too much. So WebAssembly is this like virtual machine that is running in lots of different environments, not just the web. That is more like a historic accident in that name. So we really have to support a wide diversity of ecosystems, right? Ranging from desktop to embedded. So one of the characteristics of WebAssembly is it's a low-level virtual machine. It's supposed to be language independent, so no specific language has no bias to any specific language. It also doesn't have any bias for a specific platform at all, so it's not a web thing. It can be embedded anywhere, and in reality there are more than a dozen implementations of WebAssembly engines already that you can pick from and embed in your program. And they have very different characteristics. And an important part of it is that its semantics is designed to be portable, right? Ultra portable, deterministic, and there's a sandboxing model which also makes it attractive for many. And it's an open standard, so that anybody can work on. But so I don't know how closely you follow the development of WebAssembly over time, but there has always been like this grand roadmap essentially underlying the development. So when we started out, it was clear the first kind of thing we have to achieve is having good support for low-level languages, right? That was our first line of customers. They were already compiling C++ applications to the web, for example, and we wanted them to support them and be able to deprecate like other legacy technologies like NECL, native client, and ASM.js, which were more hacky things. Since then, we have more or less worked on kind of stage 2, like better support for high-level languages, right? So, and I'm thrilled to say that very recently, many of these features we have worked on for years have kind of, we pushed them over the finishing line, so things like tail calls, garbage collection, exceptions, and stuff like that, many of which would be relevant to dynamic languages as well, I suppose. And then there has always been like this stage 3 thing as well in the back of our heads, but to be honest with you, nobody has really like given that any real thought yet. So most of my talk here will be rather like me speculating about what that could even be, right? Right, so to give you a bit of a picture of WebAssembly, so imagine you have an application, let's say a web browser, and you want it to run WebAssembly. So the way you do that is you use an existing engine and embed it, right? So it's kind of, you can use it as a library and you embed it in your program, you link it in somehow. And then we call the program that does that the embedder. Inside the engine, we have 2 main components. One is the actual runtime, which is mostly about memory management and stuff. And then there's the compiler, which goes from the WASM bytecode to the respective native code of the platform you're running on. The embedder can, and that can actually be both a JIT or it can be an AOT compiler that is completely dependent on the setting you're running in, and the whole design of WebAssembly is such that you can make both of these choices. So this is kind of important for the context here as well. Right, so the embedder can talk to this engine through some embedder API. There's some standardized or semi-standardized ones, but they also usually have their own ones. And one of the obvious things it might want to do is ask it to instantiate a bunch of modules, right? So WebAssembly binaries come in the shape of modules, and you instantiate them, which means they will be passed through the compiler on your local machine and turned into native code, which is then placed inside the runtime, and more specifically the WebAssembly sandbox. So all the native code there will be in terms of modules that run inside this sandbox. And then the embedder can talk to these compiled modules through their imports and exports that they have declared initially. And that's the only way to talk to them as well. But that's just like one scenario, right? The web browser. So on the previous slide, you saw all these other environments we want to support. And another one might be embedded systems, for example. So what does that look like? The situation is a bit different here. You want to run on basically some chip, right, directly, more or less. So the setup will usually be a bit different. You actually want to do AOT compilation outside the system and then create the final code and load that onto your hardware. So part of your engine, if that is even the right term in that context, then lives outside the engine. And also, so the compiler in particular. And also you want the runtime probably be like as lean as you can possibly make it, right? So really just consists of the code ideally. So just to give you a bit of background of what the constraints are that we have to meet across these diverse landscapes. So I had this list of kind of defining features, and one was like low-level virtual machines. So what do I mean by that? There are various characteristics that you can assign to that property, but the basic idea I usually describe as being that WASM is an abstraction of hardware, right? Unlike other like mainstream VMs, it does not abstract some language above you, like the JVM would be an AST for Java essentially. We try to basically be an AST for your CPU instruction set. And that means that all the languages that you can hopefully run on WebAssembly, the goal is that they're all like really equal citizens. We don't give any of these languages any particular privilege, right? That is very important to the design. So, and that is the way for us to support both like language and platform diversity in an equal manner. And as far as I'm concerned, that is the only way to do it. That's the only way to achieve this kind of neutrality. You have to be low level. Everything else will eventually like get you into some dead end or completely unmaintainable mess of semantic constructs. So we want to maintain this kind of property for WebAssembly. And that is probably why my talk might be a bit disappointing to some people in this room. But let me first concretize a little bit what that means. So yeah, WebAssembly is an ISA, so it's really just an instruction set like you would find on a CPU, but a virtual one. And the idea being that it really maps almost directly to hardware instructions. And you can predict what instructions it maps to if you know the hardware. In most cases anyway. There are some exceptions, but in general that's the idea. And that should give you a very transparent and explicit cost model, right? So you really know what kind of code you're generating ultimately. And that is important if you're writing a complex compiler or runtime targeting this thing. You really want to know what's going on. You want to have predictable performance in the end, right? If there's a higher level abstraction in between, you often have the problem that you don't, like you have competing abstractions and competing optimizations and stuff, and you don't really know what you're doing. You already have this problem today with modern CPUs, right? They do a lot of fancy stuff under the hood, and sometimes optimizations are completely counterintuitive in their results. But yeah, you also don't want anything implicit like runtime type tests or anything like that. So that is important. Again, if you compare to the JVM, when you access a model, an object, you essentially have a runtime type test every time, right? This is not something we want to have on this level. Or that you would have to optimize away with complicated things like inline caches like a JVM would do in practice, or more complicated compilation patterns, JIT patterns. Yeah, so of course there also is no such thing as an object model, and in particular the whole VM is designed to not require GC. Even now that we have a GC extension, that is completely optional. You don't have to use it, and if you don't use it, it doesn't cost you anything. Right? Yeah, most optimizations is really the job of the compiler producing WebAssembly, like as if you were compiling for native code, right? We don't assume that the engine is doing anything particularly clever. So really, we are using JITs because you have to somehow translate the portable abstract bytecode to actual machine code, but that is really all it should be doing in an ideal world, right? It should not have anything clever in it. So the JIT is really just a way of translating the instruction set. But that's the ideal. Of course, there are some limits to it. So because we are operating in this like triangle or tetraeder of competing constraints and concerns, and you have to balance these somehow. And that means that we can't really be as low level as a CPU in reality. In particular, because we have to maintain safety, absolutely, right? That is not negotiable, we have to do that. And that means we have to rule out certain behaviors and we have to do certain checks. So my slogan for explaining this usually, we want to be as low level as possible, but no lower. Meaning that it's not a free pass, right? We have to raise the abstraction level sometimes, but that is not a free pass. That doesn't mean you can do anything, right? We often get like requests, okay, why don't we add like, I don't know, vtables as a primitive to WebAssembly or other things, right? And then that would kind of like go against the spirit and bring you into this hell of like ever-blooming complexity ultimately, and creating language bias. However, there are obviously counterexamples of where we had to raise the abstraction barrier, and I just want to mention a couple of them. So the first one, and I also mentioned that in my talk on Sunday already, is like functions. So CPUs don't know anything about functions, right? You just have code in memory, you jump back and forth between that. In WebAssembly, we have functions as a primitive notion, and there are various reasons for that, having to do with safety, security, so you don't want to expose the stack, but also performance, so that the engine, which knows the actual hardware, can pick the right calling conventions, the ones that are efficient on the hardware it's running on. and other reasons. But it's really just a mechanism to group code. It doesn't do anything more fancy than that. A function reference is still just a code pointer. I mentioned garbage collection, which we now provide, but again, that is much more low level than you might probably expect. So I talked about it like 2 days ago more extensively, but it's really, the idea is that you don't have objects or anything like that. You really just describe the data layout of data structures like you would generate them on native code and use them to tell the GC how to manage the memory. But it doesn't do anything else for you, right? It does just manage the memory. It doesn't do objects or anything like that for you. You still have to encode all that manually. Another thing we're working on right now is continuations, for example, that is not yet like close to being accepted, but again, this is kind of like an abstraction trying to be as low as possible over like the notion of a stack, essentially, right? So really, it's a way to model stack switching. So those are a couple of like higher level abstractions, if you want, that are in WebAssembly already. I'm going to list you a number of things that we don't want to put in there. There would be higher level abstractions that we don't think should be in there, or I at least think they should be in there. So higher level data types like strings. There has been long controversial discussion about making strings primitive in WebAssembly. Bad idea, because they're way too diverse. Things like big noms and other things you can think of. Obviously, an object system, I already said that. The dispatch mechanism, I also already mentioned that. All that you should have to implement yourself. Dynamic typing, obviously. Runtime types, not something, at least not in the way they occur in the source language level. They should not be primitive in a system like this, or let alone reflection, right? In general, like anything that is specific to a given language or family of languages or language paradigm should not be put into WebAssembly as a feature. You should have to implement it on top of WebAssembly. And anything that can be efficiently implemented on top of WebAssembly as well, even if it's kind of like universal. So garbage collection in a way is already kind of like the boundary to which we are willing to go, if you want, and some people would argue it's already too high. Yeah, so the basic message is like you should really think of implementing a language on top of WASM like you think about it on top of native, right? In an ideal world, anyway. Unfortunately, when it comes to like dynamic languages and type-challenged languages, then there are a number of limitations you will run into here. Because we have these constraints and this slightly higher levels of abstraction, when you want to make a dynamic language fast, you basically have to pull every dirty trick from the book, right? And more, tricks that are not in any books. So I've worked on V8 for 8 years or something like that, and I still, even in retrospect, I find it mind-blowing what is going on in an engine like that, and also kind of disgusting. And many of these tricks you play there to make it fast just won't work on something like WebAssembly, at least not as it is now. So for example, there's no way you can have unsafe code, right? VMs are full of unsafe code because they make all these global assumptions about invariants, and sometimes they get them wrong, but that's the way how you do it. We also have this strong module system in WebAssembly, and you should absolutely not break that encapsulation guarantee because the whole sandboxing mechanism depends on it. You don't have any access to registers directly. You don't have any access to the stack directly, right? All these things that VMs do where they need to pin registers or, I don't know, traverse the stack, do all sorts of weird things you can't really do directly. One thing that engines like JavaScript engines do is more advanced even in terms of stack stuff. They rewrite the stack, right? So when they have this thing where at runtime they optimize and de-optimize functions that are currently running, so who have stack frames on the stack, live stack frames. And that might completely, if you recompile a function to a different format, like you tier up, you tier down in your compiler pipeline, that might need a completely different stack frame layout. So the VM would dynamically rewrite the stack. It would even merge multiple stack frames when you have like inlining or you stop having inlining in that process. So again, something that's completely out of scope for doing that in WebAssembly, right? And of course, self-modifying code. No way you're going to have that. This is something I would assume is a bit on the way out, but like traditionally engines are full of that, right? In particular, one popular technique that uses that, or at least traditionally uses that heavily, is inline caches, like they are used for JavaScript, but have been pioneered in the Smalltalk community. You can do them without self-modifying code, but then you pay for an extra indirection, right? But there are many reasons why you probably need to go that direction anyway, because security, control flow integrity, and all sorts of things coming our way more and more, that this is probably not gonna be sustainable using self-modifying code. And then ultimately JITting, right? How would you JIT in WebAssembly? And I should say that many of these things are kind of related to having access to code in some way or the other. And that is one place where WebAssembly really differs from real hardware, in the sense that real hardware is a von Neumann machine, right? So you have code as data somewhere in your memory. You can just play around with it if you want. That's not at all the case in WebAssembly. WebAssembly in that sense is really more like a Harvard machine, where code is in a completely different space. You don't even have access to it at all. You can't see it, you can't do anything to it. And that definitely is a feature, not a bug, right? But it gets in the way of all these things. So what does that mean for a roadmap? Right, so I showed that. So in some stage, we might want to have better support for dynamic languages anyway. So what do we mean by that? And it's a good question, and I want to be honest with you. I don't really know the answer. So the rest of my talk will just be me speculating over a bunch of things that I think are kind of at least necessary in some way or the other. But that is not a definite answer at all. And also, there's no time frame here. I can't promise anything. There's nobody actively working on it, because we haven't had much pressure or interest really from these communities to get involved. And I mean, as I said, it's an open process. So if you're a dynamic language implementer and you need some features, then you would have to step up, write proposals and stuff like that, right? That's how it works. We are not doing it for you unless there's somebody who needs it. So, but the general idea really just is that, yeah, we won't provide high-level language mechanisms. We want to provide, at best, implementation mechanisms, and low-level ones at that, right? So a bunch of examples I just have out of the top of my head, more or less, that I could think of that seem to be relevant, especially in the context of JITting. So the first is we probably need a way to do dynamic code instantiation. So in WebAssembly, code comes in modules, and modules are mostly like a static notion, right? You can dynamically instantiate or link a module, but right now that is only possible through external APIs, right? So on the web, for example, the JavaScript API gives you a way to instantiate a new module, and then you can pass out its exports to other code you have already instantiated, and that way you can link them together. But that only happens in JavaScript, or similarly in other APIs like on the C level. There's no way to do that from inside WASM. So if you wanted to implement a runtime that does all these things with dynamic code generation or specialization, then there's no way you can implement that in WASM itself right now. So the first idea would be that we somehow have to lower this instantiation API into the language in some way, one way or the other. So I don't know who is particularly familiar with WebAssembly here, so this slide might be a bit technical for those who don't know WebAssembly, but just to roughly sketch the idea of what that could look like more concretely in WebAssembly. So the first thing would be that we would have to introduce, would have to allow modules to define local modules themselves. And we would have to introduce the notion of first-class reference to these various things that modules can define. So what you already have in WebAssembly is function references. So you can reference local functions. But to be able to link up modules from inside the language, you would also be able to need to be able to reference globals and tables and all the other things that modules can define. So have like instructions for taking the address of, I don't know, a global or something like that, intuitively. And then you would need like kind of an instruction to instantiate one of these nested modules, for example. So it could look something like this. It takes as operands on the stack a list of imports, so references to some of these things it requires, and it gives you back a list of its exports. That would be the most direct way of providing this, right? And there's nothing in principle that prevents doing this. And yeah, but of course, if you want to get any benefit out of it, it kind of implies that the engine does compilation of this nested module at instantiation time. So only then you get the benefit of it being able to specialize any code for you get out of that. I have an example here, but I think in the interest of time, I might actually skip over that. It just tries to give you the general idea that you could have a local module that is, whose role is to specialize some stub code or something, and by instantiating it, you specialize it to some specific descriptor value. I don't know. There's a lot of like VM speak here, which probably I don't have time to walk you through, unfortunately. So let's rather move on to the next kind of thing. So this is like a first step, right? This is like still, the code here is still sort of static. So I had this module, this nested module already defined, and I instantiated dynamically, but the code itself I can't really do dynamically. So basically, there's no way, another way to look at this is like engines have a JIT, but you don't have any way of using that for your own purpose. You can't really JIT code other than very indirectly through code that is already there, and then you're kind of depending on the compilation strategy of the engine. But runtimes like want to use JIT, sometimes anyway, so that would correspond to the ability to actually generate a module dynamically, not just instantiate one dynamically, but generate one dynamically, which is not currently possible, even with the extension I just showed you. So the idea there would be, again, to lower something we already have in the API, namely the compilation interface, into the language. So first of all, you would need some new notion of types that define the types of modules, so they're signatures if you want, so that you can form references to modules, right? Yeah, you can reference these things, and then you would have like this one super meta instruction for creating a module. One way it could look is like this. So it takes a reference to some memory and a range in that memory and interprets that as bytecode that it's supposed to compile. And then it gives you back a reference to the module, and you can use a variation of the instruction I showed before to instantiate that thing. So the variation would be here that it actually takes a reference instead of a static module name. And these are mega complicated instructions, of course, and they embed the entire, like, they definitely require going into this model where the entire engine is inside the execution environment, right, where you can't do AOT anymore. So this is definitely not for all environments. Okay, again, example, variation of the previous one. Let me skip over that. And the last thing I have is that is a bit different direction. So the technique that languages use is sometimes called hidden classes. So that also comes from the Smalltalk community originally, where you kind of try to infer from the layout of an object. You identify that with a class that you generate on fly, some identity, or which is kind of a descriptor. And you transition objects when you change their change, you transition their class to something else. So engines do that behind the scenes. In V8, these are called maps. I think in Firefox they're called shapes and so on, but they all have them somehow. And in the GC proposal for WebAssembly, of course, you also need to have descriptors internally somehow in the engines for the GC to use, right? But they are completely encapsulated. You can't like piggyback on them as a runtime on top. So in particular, you cannot attach any like additional data to these things. So it would be nice if you could do that and use these for your own purposes. So that would be possible by providing access to these descriptors somehow. So introduce a way of generating custom ones. So first of all, you somehow have a new form of type that describes the descriptor for some other type. So it's kind of like a meta thing if you want, and attaches a number of fields to it, for example, that you can pick. And then you can allocate these things, blah, blah, blah. And then you have variations of the allocation instructions for regular objects that take one of these as an argument explicitly instead of you doing the implicit thing and inserting an internal descriptor. So you don't really have to read all that, but the idea is, yeah, you can provide that explicitly. And you can extract that then in any place you need so that you can work with it and use its information. So this would give you a way to attach essentially static fields to an object, for example, right? Which is, again, something that engines do on a regular basis, engines for dynamic languages. Right, and you might think of more things you can do with that. So these are, as I said, this is just me speculating. There's lots of open questions here. I'm not gonna go through all of them, but one big one is like, yeah, if we do all that, how does this not become a huge reflection mechanism? And maybe the even bigger one is it actually worth it at all? I mean, given Kevin's talk before, maybe we just don't want to do JITting. That might be an answer too. This is all too complicated, not worth it, and you should just be writing an interpreter if you insist on self-inflicted pain of using such a complicated language. Then that's what you have to do, perhaps. I don't know. That might be an answer. I'm not saying that is the answer. Okay, that's all I got. It's pretty much an open problem. It's a summary, and we don't really know how to solve it yet. But we would very much appreciate input from this community and actually investigate this, because right now we don't have anybody who's doing that, right?
Great, thank you. Let's thank the speaker. So we have time for a couple of questions. We have one here.
I was just wondering, so I guess when you were talking about the JIT compilation and you called back to the slide where you have, in the embedded scenario, you have the AOT that's outside of the system.
Yeah.
Is it possible that there may come a time where there's sort of like a host profile or a better profile where you have kind of some embedders that only support a subset of the spec?
It's funny how this question around profiles keep coming up lately. Yeah, I have a proposal actually for introducing profiles into WebAssembly. There's a bit of controversy around that because some people just don't like the idea and think this like furthers fragmentation of the language. I think it actually does the opposite because that fragmentation already happens. It's just completely growing wild and we should control it some way. But I would definitely think that for a mechanism like that, yes, you have to have a profile that excludes it somehow so that embedded systems can work with the lean VM. Right?
Okay, and this, you have a profile, or sorry, you have a proposal that's already open?
So it's yeah,
or?
It is, I don't know what stage it's at, but yeah, I mean, it's two parts. It's a proposal which is just like an editorial framework for doing this kind of thing. And that's already adopted for one of the features we have now voted in, which is relaxed SIMD. So relaxed SIMD has this very unfortunate property that it introduces implementation-dependent behavior. So we required to add a deterministic mode so that you don't lose the nice properties of WebAssembly over this. And that is defined in this framework. So basically the setup is the specification of the language specifies the whole language, and then you can mark individual constructs or rules as excluded in a certain profile, right? And this way you can have like subsets, well-defined subsets or intersections of subsets even for certain needs.
The proposal is stage 1.
Yeah, technically it's stage 1. I think we had an in-person meeting 2 weeks ago where we essentially decided because relaxed SIMD, which just got stage 4, depends on it, we kind of implicitly accept it. Yeah.
One quick question. So it's more like a clarification. You mentioned that you have support for GC, but if I understood correctly, you say it's not required. So then
Yes.
why is it there? In which cases are required?
Well, you can use it as a producer, so compiler targeting was a more runtime, right? But you're not required. Like if you don't use it, then there's nothing in the rest of the language or the instructions that depends on you using it. So it's completely isolated from the rest of the language, and there are no cross dependencies with other features. That was very important in the design.
Okay, we have one more question and then we jump. Can I ask you for setting it up? Yes.
Hey, thanks for the talk. I guess somewhat naively, I assumed because WebAssembly's text format is, you know, like S expression based, that it would be okay to operate on the WebAssembly text format itself for optimizations, but you suggested that that's just a bad idea. Could you add some color to that?
Oh, well, so the text format is a text format, right? Which means that engines don't understand that. Engines only understand the binary format. The text format is just a human readable representation of that. So, yeah, I mean, you can hack on the text format, but that's not what you want to do inside a runtime, obviously.
Good, let's thank the speaker again. So now we have the last speaker of this session. Rodrigo Bruno is going to talk about language runtimes for the new cloud era. So, floor is yours.
Thank you. Hello, everyone. So, all right, so I must be honest, I was extremely relieved that Maxime used this morning the popularity index. I was really afraid I would have to change my slides afterwards. But essentially, what I wanted to show here is that if you look at the most popular language that you have right now, we always find the usual suspects. You find Python and Java and JavaScript and C#, and then the list goes on. But the important point that I wanted to convey here is that most of these languages, they are languages that provide you high-level abstractions. They provide you with dynamic types, architecture independence, sandboxing, automatic memory management, among other features. And we have seen that these features are pretty important for developers. Basically, they help developers get high productivity, and companies value this quite a lot. However, the dark side of these high-level abstractions is that this has a cost, right? There is always a cost associated when we introduce another abstraction level. And I'm showing here a plot from a paper from 2019. Now, granted, these guys were trying to implement a network driver, which might not be a reasonable thing to implement in all of these languages, but even if we abstract from that, you'll see that, well, we have our C as being as our baseline for what you could expect to get as close to the hardware as possible. And then you see that you have Rust getting very, very close to C. And then as you start going down, you see that these are languages that introduce more and more abstractions, right? Until you hit like rock bottom with Python almost kind of close to the zero, right? But then in the middle, you have JavaScript and Python that are kind of languages try to balance these several layers of abstraction. So, and then we might think about, okay, so what kind of motivated all these languages that have so much gap in performance compared to, for example, C? And if we go back and see actually the evolution, and this is a point that was also brought in several talks before, Kevin and Maxime as well, when we look back into how the performance of our CPUs evolved through time, and we start seeing, okay, when were these languages proposed, we actually see that many of the languages that have, like, I would say, lower performance compared to C, they were actually proposed and started being adopted in a time when CPU performance was also almost for granted, right? So a lot of times, instead of actually fixing our performance issues or rethinking our performance, developers were like, okay, no, just wait for the next CPU to come around, right? And now we see that, well, we don't have free CPU performance anymore. We actually need to take care of our performance, and we need to optimize our runtimes. And this actually started gaining attraction on new languages, right? We see Go as one step towards this direction. Then there was Rust. TypeScript is also trying to fit types into JavaScript. And now, well, WebAssembly is not directly an end-user language, but it also shows this concern for performance, where we're trying to bring higher performance closer to other environments, initially the browser. Right, so what can we do from here? So we're basically stuck in the good sense with high-level languages, and I don't think we're going to get rid of these languages. I'm a little bit more optimistic. We're not I don't think we're going to go into a winter on dynamic language. I think we're continue loving them and building new languages. But as a consequence, we invested a lot of time into producing high-performance interpreters, high-performance JIT compilers, and garbage collectors, right? To the point that if we use the Linux kernel as a comparison in terms of lines of code, and this is, I think, including all the device drivers. If you take all the device drivers away from the Linux kernel, maybe it goes down to half of it. And we compare it to, for example, the OpenJDK ecosystem, we almost have like a small operating system worth of lines of code. Okay, so there is this amount of effort that people have put into these languages. And the same goes at the lower degree for JavaScript and for Python. Okay, so people have invested a lot of time into trying to optimize a lot of these languages. And this actually became very huge pieces, very heavy pieces of software, right? So the fact that we stopped having free CPU enhancements every year also had an impact not only on programming languages, as we saw before, but it also had an impact on how people develop software. And one of the reasons is how can we actually scale and how can we make our infrastructure a little bit more elastic, right? And back in the day, we used to have like our applications built into a very big piece of code. Eventually, when CPUs stopped getting faster, we started breaking this down into modules or microservices, and now the new trend is to actually build applications into functions, which are very fine-grained pieces of software that we can deploy very easily. And this brings several advantages, right? It's faster to develop because now you only need to look at one very small piece of code when we have to, for example, run tests and so on. It's better for scalability because now you can target pieces of software that are actually the bottlenecks of your application. Since there are smaller pieces, they're more elastic. You can deploy them at a faster rate. And at the end of the day, they also enable you to pay as much as you use because you're never deploying more code than you actually need or more resources than you actually need. However, this had an impact or an effect on runtimes, right? And this means that our code will have a shorter lifetime because it will run for a small amount of time. We'll have fewer resources. Resources are going to be very stranded. We'll have many concurrent instances. We have, instead of a single monolith with dozens of cores, we might have dozens of instances of single core allocations. And we'll have a lot of internode communication, right? Whereas before we had maybe many modules, internal modules that were communicating through method calls, right now these are going to be turned into RPCs, right? Or messages that grow across the network. So in fact, what I want to raise here is that I don't think language runtimes are a good fit for this new model. So language runtimes, they were built in a time where we had large pieces of software, where we had large allocation units, they had a lot of cores, they had a lot of memory, and there are some problems that start happening when we start decreasing and we start reducing the amount of resources that we give to each of these. And I'll build on this point throughout the talk. All right, so some of you might not be familiar with serverless and function as a service. I have just this slide to give you a very, very, very quick intro to that. Not that this is central to the talk. The idea is that compute is going to go finer and finer granularity. And serverless and function as a service is just an example of this trend, right? So the idea is that you provide some piece of code. For example, I have here like a very simple Python function. And you just provide this definition of a function that includes an entry point. Obviously, your code can grow as much as you want. This is just like the minimum amount of code, which is just implementing a function that the provider knows how to call, right? You upload this piece of code to the provider, and the provider controls everything else. So you don't have to have an API gateway always on. This is installed and maintained by the provider. And then these functions will use a lot of other cloud resources for databases and storage, right? So essentially, you only give or you only supply the core domain knowledge of your application. If you look at the software stack, all of it is managed by the cloud provider, or actually the provider of this function as a service platform. Only the function instance, or should I even say only the logic of the application is managed by, or is provided by the user. Everything else is managed by the provider, even including the runtime. So the provider has full control over the runtime that you're using. So this ends up being an event-based model. There is no control over the infrastructure. We expect functions to launch in far lower than 500 milliseconds. If you try Amazon, it's around 100 to 200 milliseconds to get your code running. You are built at the 1 millisecond granularity, meaning that every millisecond that your application consumes, you're going to be built at this granularity. And whenever you're not using the service, meaning that your function is not running, you actually pay 0. Okay? So this is dramatically different from VMs or containers, where you're basically paying for the entire duration of the resources that you're renting. Here, you just pay for the amount of resources that you actually use running your own code. Right. So bad news is that I don't have a lot of answers for you. And this talk is going to be more about asking questions. Hopefully, I will ask some correct and some of the good questions. But my hope is to start some discussion and to basically give you examples of things that I've seen over time where this new trend in developing software into finer granularity pieces of code actually hurt or go against some of the principles that we have in our language runtimes. Okay? So these language runtimes are very hard to optimize, and this is one of the things I'll go over, is that cloud providers have a hard time optimizing because a lot of times they see language runtimes as a black box. And I think this is an artifact of cloud providers being mostly maintained and built by people in the systems community, and people from the language runtimes usually come from the PL side, and there is some lack of intersection between these two areas. And then when we want to optimize cloud computing platforms, we talk with people from the systems community, and they tend to look at language runtimes as a black box. So I think there's a lot of opportunities for intersection and to actually make these systems more optimized. So just to give you kind of a perspective in terms of cost here. So this was measured a couple of months ago. So Docker, QEMU, and Firecracker. So Docker, I think everyone knows, this is like a packaging software. It basically virtualizes the OS. You can have multiple applications in some sort of isolation on top of the same OS. QEMU and Firecracker are virtual machine managers, right? And they cost around, let's put them around 100 megabytes and 100 milliseconds to launch. This seems pretty high, and it is pretty high, but these technologies are pretty easy to optimize. You can, for example, checkpoint and restore them, and the cost will actually reduce quite a lot. So this we can actually optimize. The hard part becomes the runtimes, right? So the runtimes live inside, let's say, inside this block between 10 and 100 megabytes of footprints. So this footprint here is just a footprint to have an empty runtime in memory. It's basically how much memory do you need to run Hello World. And the same goes for latency. It will take around 10 milliseconds up to 100 milliseconds, let's say. And ideally, we wanted to go into microsecond and kilobyte scale, right? So the idea is that for every additional execution environment, we don't want to pay another 75 megabytes of memory just to have a very small piece of code executing. Now remember, if you look at traces of, for example, function as a service, and there are some traces available, you'll see that many of these functions, they execute for 1 second or even less than 1 second. If you take 100 milliseconds just to boot up the runtime, this is going to be a huge impact on performance. And then there's other things that, like warm-up that we're going to see in a second. The same goes for memory. Many of these functions, they will use a couple of megabytes because they might be processing a web request, or they might download a chunk of a video that is maybe 1 or 2 megabytes, okay? If you put an overhead of, let's say, 15 megabytes for Python, or maybe close to 50 for Java, again, this is going to be a huge overhead on top of the system. So people have been looking at this, again, using systems techniques, forking and snapshotting. This is like operating systems people, okay, what are the tools that we have that we can actually apply to reduce these overheads? And the problem is that, well, most of our runtimes, they are not very good candidates for forking. There's all sorts of problems that start happening when you have like 2 copies of the same process. And snapshotting is a similar process, has a similar problem. For example, when I'm snapshotting my JVM that has 2 gigabytes, I have no idea how to differentiate pages that actually contain user data or pages that the GC has just because it's part of the heap, but they contain basically garbage. right? So this is a very simple example of like, I can do snapshotting, but it's extremely inefficient, right? And there it goes into like all sorts of problems. I think we're going to explore some of this later on. So one kind of angle or one direction that we have been exploring is, well, maybe we just need a new virtualization layer, right? We know how to virtualize the hardware. We have been around with virtual machines for some time. We know how to share the same operating system. Containers have done that, right? And now maybe the next step is to actually, well, maybe we need to share the same language runtime and create the ability to run multiple applications or multiple instances of the same application and share the same interpreter, the same GC, the same JIT compiler. And this is actually what we have tried. We've tried building a sandbox that can actually run multiple applications on top of the same virtualized runtime. So here, the idea again is to say, well, I'll pay the price of launching and keeping this runtime in memory, but I'll pay the price and I'll dilute this price over as many applications as I can, right? And then the price per application obviously becomes lower and lower. It's even more cool if you actually manage to have multiple languages executing on top of this single runtime. This has a very good practical impact, which is now you don't need to guess which VM image or container image you need to launch. You just launch the same every time, right? And this can actually improve the way you manage your cloud resources, because now you always know it's the same image. There is a lot of optimizations that you can do if you have like very few very popular images. So this is an example of one of the systems that we have built. I'm not going into details. The point of this talk is not to go over this this system that we are building. If you have more questions, I'm super happy to talk afterwards. But essentially, consolidating applications and functions in a single runtime, it avoids memory redundancy. It avoids paying the cost of initializing runtimes multiple times. It brings a lot of opportunities for sharing, and it avoids more and more cold starts. But there is obviously a lot of questions, and this is the part that we are not sure. We have built this prototype. We're still working around a lot of the corners. So multiple language runtimes already have the concept of memory isolates. You see V8 is a good example of this. They have memory isolates. Maybe we can actually use these memory isolates as a way to multiplex the same runtime. Usually the problem with isolates is that they only are capable of executing codes of the same language, so meaning that I can only execute JavaScript in a JavaScript engine. The same goes for native image isolates. They also have the same problem. By the way, in this project, we are actually using native image together with Truffle, and Truffle using as an escape hatch for other languages. Again, Truffle has a lot of performance inefficiencies. We're still trying to look into this. WebAssembly is a potentially very interesting solution. We're still thinking how can we actually have multiple sandboxes that are sandboxed using WebAssembly. Again, the most, I think, unclear way is to, or the most unclear answer is how do we retrofit or put dynamic languages on top of WebAssembly. If we actually compile the engine down to WebAssembly, or if we wait for language implementers to basically re-implement the languages on top of WebAssembly. So this goes back into Andres' talk. So this is polyglot support. Another idea that has been around is to basically use a VM or a container that has all these implementations. Okay. So again, this is sort of similar to the environment that we have in web browsers today, where you see they have many web pages. The difference is that in a web browser, the engine is already running. In this scenario of cloud computing, for example, function as a service, you need to create the runtime in the critical path, right? So this is a problem of the cold start that we want to avoid. So another problem that we have also seen is long warm-up, and this was another project. It's going to appear in a conference next year in Eurosys. And here, basically, we were looking into, okay, snapshots is the de facto solution right now for avoiding cold starts in function as a service. But most of the people, what they do is basically they snapshot after one invocation, which might seem like a great idea, but actually there is a huge performance curve that still needs to be went through in order to get to somewhat better performance. Okay, so basically This is a very problematic curve. The hard problem is deciding when is the right moment to snapshot. And again, this is another instance of the problem of lack of transparency. The runtimes are basically the better entities to know when it's the right time, when the JIT thinks it has enough optimized methods and there is no very good need to optimize more methods. From the outside, it's really hard to estimate when this happens. And this is basically the goal of the system. And another interesting fact that we found is that if we run for the same application over and over for different ranges, we see that the version of the code that gives us the best performance is not always the last. Meaning that along the way, if you keep sending more and more requests, JIT might actually de-optimize the code into a worse version. Okay, so it's not just a matter of like waiting forever. It's a matter of like tracking when it's the best performance. We can discuss into why this happens. We actually didn't dig too much into the compiler, but we have some speculation of why this happens. So again, we've built this system around this. The idea was to try to track when is the right moment to snapshot the engine, basically to reproduce this better performance. So again, the main question is here, snapshotting works great, but the problem is when is the right time to snapshot? And what should we actually snapshot, right? Code caches probably is a good idea. I need to know when. We probably also need to snapshot the heap. And this is, I mean, I need some insight from the garbage collector to know exactly what to snapshot. So a lot of these questions are currently very hard to answer without some transparency or some extra information from our runtimes. AOT compilation is a possible solution. It's a great solution. You have like, for example, several talks already mentioned GraalVM native image as a way to precompile Java ahead of time. There is some performance trade-off in exchange for the lower warm-up time because it's supposed to run as very fast from the start. There is PGO that you can still try to use in order to cover some of the performance that was lost. This is still, we are still trying to play with it and see how much we can actually regain. There is also security implications if you try to decide to share profiles. For example, there have been some guys that published a paper last year. I forgot to include a reference. It was called JIT server, but essentially they had like one server that cached compiled versions together with their profiles and then tried to decide if the profiles match enough to see if they return actually the compiled code already. So this is interesting. Maybe a way to exploit new side channels, I don't know, but this is, I think, an important question. So I'll probably need to move a slightly faster show. Another aspect is memory footprint. Again, this was a study that we did a couple of years ago, and we tried to load an 854 megabytes a plain text file into memory, and we saw that it used almost 6 gigs of memory. This is because, I mean, a lot of the headers in memory, they're super bloated. References also take 64 bits. We might not always have the best format, and even if you use compressed references, it's still very problematic in terms of size. And another problem that was also discussed at DPLR by Marina 2 days ago is that we have very little control over how much memory is actually being used. So if your application has a profile that changes over time, it's very difficult to convince GCs to actually maintain their memory reduced to the minimum that is needed. So GCs, by default, they will try to use as much memory as is available. You can fine-tune heuristics, and there is work that has been done on that side, but it's still very hard to control. And there is, again, lack of communication, lack of transparency for the operating system to say, well, you should maybe evict now memory because memory is being lower and this is affecting performance for the application. Maybe it's a time to actually try to reduce. So I think language runtimes are still a very encapsulated box that have no way to communicate with the outside. Right, so this is, optimizing memory is I think it's a very important aspect. A lot of the runtimes, I mean, I'm a bit biased on Java because this is where I spend most of the time. But one of the things is that the language sometimes exposes the internal architecture, the internal layout in memory, and this causes problems because if you want to optimize memory, then this becomes a problem. An example is object identity in Java. If as long as there is object identity, this might actually prevent you from doing more aggressive heap layout optimizations, because you might lose identity in this process, and if you want to be 100% transparent, this is going to be a bottleneck. Right, so I think I already mentioned all of these points. And finally, there is a high cost in input-output operations. As we have more and more fine-grained applications, this means that all method calls now translate into RPCs to external components. And when we have external components, we actually need to serialize and deserialize our data. A couple of years ago, we looked into this problem, and if you look at the cost of serializing network and deserializing, you'll see that as our networks get faster and faster, the amount of time that we spent on the network becomes lower and lower. And this puts more and more pressure on CPUs that, as we know, they are not getting any faster, right? So this puts more and more pressure on the ways that we use to serialize and deserialize. So I think this is another aspect that runtimes need to be aware, is that eventually most of this cost, I think we're not yet in this 100 gigs, at least for the average system, maybe in some very specialized infrastructure, but eventually we'll get there, and it's going to be a very problematic thing. We tried to send object graphs reading raw Java from one side to another. I think this is very similar to what Juan probably have done before. We used RDMA to move, but what I want to say here is that it was really hard. We had to pull a lot of tricks. We had to use something very similar to speculative type graphs, was basically inline polymorphic caches. It was mentioned this morning. So we had to use a lot of tricks to basically be able to transport memory, raw memory, from one JVM to another. And again, this is the problem that JVMs are not ready to expose their internal representation to the underlying platform, to the operating system or to some host environment that they're in. So it's very hard to coordinate all of this. So if we want to improve the way we do serialization and deserialization, to basically remove as much as possible, we need better coordination with the GC. We need to make sure that the GC is not moving. This is a problem that Juan mentioned 2 days ago. We need to make sure that the mutator is also not moving objects. We need to know, and we need a way for language runtimes to expose their internal header layout and the way their references are built. So again, I think at the end of the day, this means that language runtimes need to be more transparent to the layer below, and maybe a little bit more opaque to the user, as not exposing any internal details about the internal representation. This would allow more aggressive optimizations, not only in terms of I/O, but in memory as well. All right, so to conclude, so I think, and this is my opinion, please disagree with me, I think abstractions are not going away, and I think we need to keep optimizing our language implementations. I feel there is still a lot of room, and this new trend in building functions as a service is basically a new area where there's a lot of opportunities for optimization. So this is a different environment compared to what environments we had before. This is not a client-side VM, and this is also not a server-side long-running VM. This is something that stands in between, and this is something that our runtimes are not prepared for. Performance is not critical, again, because this is not the client side. We pay by the megabytes second. I think we should not reinvent the wheel, and I think many projects, this is kind of an orthogonal aspect. They tend to implement new GCs and JIT interpreters, JIT compilers and interpreters. So a couple of projects have tried to avoid or try to make language runtimes a little bit more modular, trying to reuse some pieces of our runtimes. I think this is a good initiative. I think we shouldn't be implementing the same GC over and over and over for each runtime, but actually trying to reuse. And finally, I think, mentioning what I was just mentioning before, to handle high memory footprint and I/O cost, I think runtimes need to be slightly more transparent to the environment underneath, and should be able to adapt their internal memory management, or the way they manage code, basically to foster a better integration with either the VMM that is running below, or actually some external hardware accelerator that is under the runtime. Okay, so with that, I conclude, and I'm happy to take any questions.
Okay.
Okay, I think we have time for a couple of questions. Okay, I'm gonna start one. So, I like the idea of this sharing, language runtime sharing thing. The question I have is, how do you know how much I'm gonna share? Because if you share too much, you are wasting memory perhaps. But if you share too little, you need time. So it's kind of in the first situation in which we just start the presentation, right?
Right. So when we're sharing right now, you're sharing basically the infrastructure of the runtime, and then you're sharing code as much as possible. All the memory that you have is private memory. Okay. So it's very similar to the idea of isolates. We have a single isolate for each application, and this is basically a heap that is dedicated to this application running. So this is the part. Any other dynamic libraries that you might use, this might be shared because you're running on the same process. At least in our prototype, you're running the same process as long as you don't invoke native code. If you try to, for example, again, in the example of Java, if you try to use native interface, then you might actually run your application or your function invocation in a subprocess. This is something I didn't explain. This prototype we have, it's supposed to be aware that you might fork the runtime to actually run it in a subprocess.
And when the context that you mentioned now that you're sharing code, and then you mentioned, I think one slide that you say, after a few runs we have to recompile because it was a deopt and then go back.
Right.
But in the concept of sharing, it might happen that one application is de-optimizing while the other one wants to use the first instance, let's say. And what do you do in those situations?
So this is not using that old project. So these are two separate projects. But yeah, so for example, in the context of JIT server, this was this paper that was, I think the folks from OpenJ9 did this. So they had like this kind of server that hosts like compiled code, and I think they tried to match the profile. So they might actually have different versions of the same code depending on if that application used a method with these types, they have this version. Use this application with different types, they might have something different.
More questions? Yeah, one more there.
So I've got a very general and a very specific question. So the general one is, feels like these issues have been known for a long time, that the way we implement languages doesn't seem to be integrated well with operating system mechanisms for things like sharing memory or snapshotting or whatever. And I wondered if you had a sense of who, it feels like it's not a technical problem anymore, it's a social problem, right? Somehow these communities are not doing things the way that each needs to do so that the other one can make use of them. So do you have a sense of where that lies? Like, can we blame some party and say it's the operating system guys or it's the language runtime guys? And my specific question was about forking, because you said that language runtimes don't fork well. And I guess that's an instance of this problem, right? But I wasn't sure I understood exactly why they don't fork well.
Right, so the first question, I have no idea. I think maybe people from the PL community need to pay more attention to like systems advances and papers and the other way around as well. I tried to cover slightly on both ends, so I see a lot of things happening in systems that are like, there is like many obvious opportunities for optimization if you actually want to look inside the runtime. But again, they look at this as a complete black box. And I think the PL people also, they spend too much time, and I'm not trying to criticize, implementing compilers and like all things inside, but not looking outside and actually looking at performance and how these things actually happen in the cloud and what happens when you try to squeeze performance. Now for the forking question, I mean, anything that is, for example, imagine that you have a Unix domain socket and you fork it and you try to use it and you have like two guys fighting for the same socket. This is a problem. Another problem is if you fork and you have like 10 compiler threads, when you fork, all of those threads dead, and it's a problem. You can try to revive them, but again, you have to be very aware of what's happening inside the runtime to be able to revive all of those threads. It would be super awesome if we could say, well, create a very inexpensive copy of this runtime in a subprocess. What we did here is kind of a mix, or kind of it's a slight optimization where you say, well, we just load a dynamic library, which happens to be an application with a very slim runtime, and then we call into it. So we are basically not forking the runtime that is creating the application, but we are basically forking into something that is very slim, has a very simple runtime inside. So they will still create threads inside.
Thanks.
Okay, time is up. Let's thank the speaker one more time. And we resume at 4, right? Yes.
All right, welcome back everybody to our last session of DLS for this year. This session has a lot of fun stuff and some obscure stuff. We are going to see the fun stuff from Christoph on debuggers, and then there is something AI related. I don't know whether you heard about that before, but it's a little bit obscure. So Mark, maybe could you give us a...
Well, thank you for the introduction. So, I'm loud. I'm Mark. I'm actually very excited. I was at Microsoft Research for many years, and I'm just joining the University of Kentucky, so really cool to be moving back into academia a little bit. Today I'm going to be talking about, as been mentioned, there's a bit of discussion about AI in the air. It's going around, some excitement. And oftentimes it's people talking about AI for domain X, like I'm using AI to write code, I'm using AI to debug code. And so I'm kind of trying to pivot this a little bit and ask, as programming language practitioners, what do we want to use programming languages for in supporting AI programming agents? So turn this around a little bit and ask what role do we play in this transformation of how software is developed? So kind of the mandatory, start off. Well, is programming languages relevant in a GPTX world, right? Is it just going to be, you're going to get another order of magnitude of model size and another order of magnitude of data, and GPT-5 will write code better than any human possible, and we'll just never have to worry about programming languages again? Well, I've met some great programmers, and even the best programmers I've ever met are like, there are programming language developments that I wish would happen that would make me a better programmer that I can benefit from. So I think even in this amazing scenario where GPT just continues to achieve superhuman status, improvements in programming languages are going to help it do a better job of generating code and solving programming problems, and will also help humans. So I think we absolutely have a role to play here regardless of the developments in this space. Another thing I see come up a lot is, well, right now there's just a ton of training on something like Python. There's just so much Python in the wild, so much code generated from Python. Is there some sort of snowball effect where if you're not Python, any improvements you have are just going to be dwarfed by the fact that GPT is really good at, knows all about Python. So we're kind of going to be limited to doing research on tweaks to Python, and that's about it. And I think actually one interesting thing is these models tend to generalize very well. Like they kind of understand what a programming language should look like, and they do very well with few-shot learning. You give them a couple examples, and they generalize pretty well. So I think it's actually quite possible to, even if you have a very niche programming language or small thing, to bootstrap it pretty quickly so that they understand it well and can work effectively with it. So I don't think we're in some sort of like, small data, trap where we can never escape from. So that's good. So I've been pretty positive here, but I think the other question is, do we need to change how we think about programming languages, programming language design, and the research we're doing? And I think this is an emphatic yes, because I think one of the big things we're seeing is programmers and programming languages are not about me at a keyboard typing in text or AST structures to implement some algorithm. They are really becoming me about the programmer curating code that's coming from previously frameworks and libraries, and now AI agents generating a lot of code. So it's not about me expressing my thoughts abstractly, but it's about me having a conversation and understanding and organizing a lot of these pieces. And I think that changes a little bit how we think about the role of a programming language as becoming the substrate for supporting this ecosystem and these development workflows. And I think that's a bit of a mindset change. So let me distill this down into a couple of questions that I think are going to be the most relevant problems and general things that we need to be addressed over the next decade or so. The first one is, how do we design programming languages for AI programming languages? Now, are these the same design decisions as you would make for a human, right? Do they have different needs? Do they have different strengths? Do they have different weaknesses? And how do we actually have programming languages to support them, not just our human developers that we've always been thinking about? The second one that's very interesting is, and I'll talk a little bit more about this, give some examples, these language tools don't understand code in any deep sense. They're language models. They see text, they see tokens, they generate text and tokens, but they don't have an intrinsic understanding of what these tokens mean. And in a sense, they can generate hallucinations or garbage or whatever you want to call it. But the question is, how do you help them? How do you give them tools that allow them to ground the output that they've generated in some model of truth about how well it addresses the user intent, it interacts with the rest of the code, it actually accomplishes its goals, right? So how are we going to have programming languages that support this kind of grounding and a bit of sort of metacognition here? You know, related to that is, well, this changes the experience of development, right? Now, how are we going to build programming languages that support workflows where humans and AI agents are both generating code and this is being integrated into larger and larger software artifacts that still need to be understandable and vouchable and reliable, right? And kind of hinting there, these actually become not just linear flows where I'm a human and I'm writing code and I'm a human and I'm telling an AI agent to do things, but I'm actually getting feedback from some of these AI agents. Like, how do we have this dialogue and develop these systems? And not only the artifacts that result from these dialogues, but what parts of these dialogues and these experiences are important to keep as artifacts in, the source control repository, codified as part of the application, just like source code, right? So I think these are really sort of big, profound questions that shift the way we think about programming language research as these agents become more and more powerful. So let me, this is forward-looking. I'm just going off the cuff from my experiences. So let me be honest about what my experiences and biases are so that you can, kind of be aware of what I might be blind to and disagree with me strongly. So I come not from the machine learning space. My background is really sort of formal methods, SMT, abstract interpretation, programming language, compiler-based. So that's kind of how I approach the world. I did some very interesting work, I thought at least, sort of this natural language to formula synthesis in Excel about a decade ago, which was a big push at Microsoft there. And then I had a fun chance to work with the Codex team, building their training data set for the initial GitHub Copilot. So I got a sort of a sneak peek at this world before it happened. But my experience and maybe my bias tends towards this desire to be like, when I'm synthesizing a program, and I see LLMs as kind of code synthesizers, just like the old, semantic guided abstract syntax tree enumeration synthesizers. They're a lot more powerful, but they're doing the same thing. They're taking some approximate signal and trying to generate code that satisfies that, right? My bias there was always, how do I take this possible answer and validate that it is the correct answer? And that's my bias. But as GitHub Copilot shows, well, maybe that's not the case. Like, it just spits the code in there and asks the user, figure out if this is the right answer. And it's immensely popular, and it's, transformed the way a lot of people develop code. So, opinions vary. I think this view on, like, correctness and grounding is going to be very important going forward, but, feel free to disagree strenuously if you want. So let me talk about the first thing, like an example of sort of what does this mean to have a programming language that's designed for an AI agent. Now, if we start talking about, when I say AI agent, I kind of talk about large language models, GPT-3, GPT-4, and they're purely textual, right? They're trained on large strings of text. They learn to predict tokens. They have some attention mechanisms to things that are maybe most relevant in the text, but they don't have any foundational understanding of what any of this text means, right? They're just generating very likely output sequences. And now we've seen in the past that code is very regular and very natural, right? And so a very good proxy for the correct answer is one that seems like it looks very natural in context, right? So they do a very good job, right? This is a very powerful thing to be able to do. But it also means that if something is not syntactically explicit in the text that they're given when they're asked to generate new code, they have no knowledge of it, and they can only use some sort of statistical prior that they've learned by looking at large amounts of code online. So an example here is, suppose I have a method named getUser, right? Now, if I look at that, if ChatGPT looks at that, it's probably going to say, well, get usually means this is pure, right? So I will assume that this text is pure, and that if I pass an argument to it and I use it later, that's going to be the same value. But that's not always true, clearly. In fact, we did a little study related to another project, and we found about 5% of all get or fetch or lookup name methods are in fact not pure. So this is an example of if, for ChatGPT, it's going to basically get 5% of all its predictions using these gets wrong, right? And if you can lift this mutability or purity information into some textually explicit form, whether it's in the language design or it's in a tool built to surface purity information, and just sort of embed that, some way while ChatGPT is looking at this or in the prompt construction, that's going to get you sort of a 5% improvement in its ability to generate code in these methods, right? So yeah, I guess that's subjective. So let me give you an example of some playing around I was doing with ChatGPT and generating code. So let's say I have this basically TypeScript code here, and I'm going to put this little defer block in, and I say, okay, I'd like you to generate code that implements this method, and I've provided it some natural language input to describe my intent for what this code does. I say, find the largest pair of values from two lists, and it has this function signature, takes two lists, and returns me a pair. So if I go to, Copilot or ChatGPT, and I type this in, and I ask it to generate some code, it returns something that looks like this. It says, zip the list together, and takes the max of the first value from the list and returns that arg. So, it's not wrong, it's not terrible, but I don't think picking the max of the first arg matches that. So I'd say that's the wrong answer. And again, it's kind of sparse here on what it has to go from. But what's interesting is, let's say I want to make it more explicit. I want to give it multimodal inputs that describe my intent. So I can go ahead, maybe I can just type in, this doesn't even have to be compiled. I can put this in the comment as well, but it's really cool if it's in the programming language. I can say, here's an example of an input and an output, right? And I could also maybe put in some, pre and post conditions, like X should contain the first element from the return value. Now, ChatGPT, Codex doesn't know the semantics of these at all, right? It doesn't understand what these mean, but just by putting this text there, it can pay attention to things like, oh, the output contains 2 and 5, but that doesn't quite match there, and you go, and it's actually able to do a better job, and it'll generate this as its most likely solution here. Now, this is cool. This, just from the text, this would look like a believable result to me. It just took the max of the first list and the max of the second list. But you can see that it fails on that example. So just by giving it more context and this multimodal ability to express my intent, we've definitely improved its performance. Now, the question is, this goes back to what I was saying about grounding. Like, how do we give it the tools to enable it to sort of have this metacognition loop where it's not just one shot, I get some prompt, I spit out some code, and I'm done, but I spit out some code, and then I'm able to evaluate in some more meaningful way whether that's the correct answer, refine my result, and build. So, okay, there are my slides. All right, so let's go back to this example here. So here, now I can say, the first thing everybody does is say, well, you got a test there. Let me run that test. And ChatGPT actually does a pretty good job with this. If you give it something like this in the prompt where you say, oh, if you give it this input, it fails, and you got this result and you expected that, can you fix this code? It'll actually go back and generate the expected answer there, or the one that matches all of the intent inputs I gave it. So you can go further than this, though, because this just sort of checks some basic sanity, right? It's not just that I wanted to produce the answer that I gave there, but I wanted to integrate within the larger piece of software I'm building, right? And so you might want to say, well, really, I'd like to then go and run a static checker on this. Like, really, this is not a good answer if it produces the right output in this example, but on other inputs, it'll immediately segfault in the following code, right? Or something like that, right? So we want to go and maybe say, hey, can I actually run a symbolic checker and say, can you generate me any input, not just this example, but any possible input, in which case this code will throw an exception. And in this case, yeah, it's pretty easy. If you give me 2 empty lists, then maxarg doesn't have anything reasonable to do other than fail. So you can go back and say, ChatGPT, can you recommend some spec adjustment or some fix, right? Because I can't, change this code in a reasonable way. And so it can come back and say, oh, maybe you add a precondition here, like I'd like to go and check and see if any of the call sites of this proposed method are going to violate this. Or maybe I should change the return value to allow you to return sort of a failure result. So this is kind of an example now. You see, not only am I just asking the coder to generate some random code, but there's actual feedback between me and that agent, right? We're having a conversation because I'm saying, oh, you know, I need to integrate this in a larger piece of code. It can use tools to find cases where this fails, come back with multiple proposed solutions. And so the interesting question is, how does it now start communicating these results back to me, and how do I start to understand them, right? So I thought this was a fun little example because it shows using not just the source code text, but we're using, you know, natural language, we're using input-output examples, we're using formal specs, and all of these things are a great way to communicate into the you know, Codex ChatGPT style model to generate code. But then also it comes back with texts, examples, perhaps disambiguating examples. If it's going to generate multiple solutions from the code, say, not just dump me 2 bits of code, but produce an input and say, I have one solution that produces output X, one solution that produces output Y. Which is right, X or Y? Like, it's much easier for a human to look at a single output and say the answer is right or wrong than look at 50 lines of code and guess what is there. So there's this, I think this opens up this huge area that's kind of been neglected for how do you have a much more tactile way of interacting with data and results and manipulating code in this sort of live programming experience, right? Because this becomes really a powerful way to interact with these agents, just like we do with other devs. We go to the whiteboard and we start drawing pictures and, you know, writing test cases, little test-driven development. And then the other thing that's interesting is, even today, I talk with someone on the whiteboard. Well, that artifact is lost after we erase it, right? Our discussion is disconnected from the source code, right? There's all these issues in the GitHub tracker. Those have been integrated with the source code, but you know, these other side conversations are not part of the programming language model. And particularly if we're talking about having these interactions, multi-round interactions with one of these agents, and we're generating lots of examples and tests and witnesses and disambiguating context. We don't want to throw those all away, because if we're going to change the code and we need to go re-implement this, we don't want to lose all that context. We want to take one more interaction to improve it. So how do we encode all of these experiences back in the programming language as a holistic artifact, not just fractured bits of context, you know, scattered in some sort of source control repository? And so I think one really important area of research that comes out of this is data, right? Data is often seen as sort of a secondary citizen in programming language areas. And I think, you know, it's very interesting with Jan talking about loading a CSV file. It's just a bag of strings, right? And there's so much stuff out in the world that is a bag of strings or a JSON object with, you know, unknown values. So how do we bring data in as a object of study for programming languages, right? What is that programming language for that data format? The semantics, how it needs to be composed and built and type checked and, you know, really exposed throughout the ecosystem. So let me go to an example for this. So, you know, here's sort of state of the art for data encoding in JSON, everybody's favorite language. And so I went to the National Weather Service and I got their temp thing. And so it says low, high, 25 and 34, and it's got some other strings in there. You know, and this is a really impoverished data language for communicating between humans, but also ChatGPT. I mean, if it looks at that, low is 25 and high is 34. That's either a really hot day or a really cold day, depending on if you're in Europe or you're in the US, right? So there's not this contextual information, again, textually exposed. The only way I would know that is, oh, that I told you I got this from the National Weather Service. You'd probably guess that that was the US National Weather Service and probably guess that that's Fahrenheit, but there's a lot of guesses there, right? So, you know, what is a data format that actually allows you to encode type and structure information explicitly in the data format in a way that allows you to link back and check it if you're doing like programming language type checking? If you want to load that CSV file and not have code that has a bunch of strings and other stuff, but like be able to load it and use it nicely. But also, if you look at this, even if I didn't give you any of the definitions of these types or anything other information on this, just from having the names textually explicit in there, you can make very reasonable inferences. And a system like ChatGPT is going to be able to key in on these and then operate on this system much more intelligently than if it was just, strings and numbers. So as an example here, like we've got a little bit of code. This is back to this defer, find, max, pair. I make a bunch of calls here, right? And I can go and run this code. I can actually, now when it hits that defer, it's going to ask me, can you type in the correct answer? So I can just start, I can write my signature. I can start running my program without writing a line of code. I can go through, I can generate a couple of these examples for it. And it's nice because even though this is structured data, I can just type in the answers textually. I complete that, and now I can save off these examples off into that sort of example section, so it's all ready to go for ChatGPT, right? So this becomes kind of a workflow where, as an orchestrator for generating code, I can sit down, just write some skeleton structure, start interacting with it in a tactile, iterative way, build up all the context and examples needed for one of these AI agents and to come in and then have all of this information to generate the code with tests, with information on how it's grounded, right? And when you start moving into a larger application context using something like React, which is very cool in the fact that it is sort of tactile, structured, data-driven, and now as they're adding multimodal support to these large language models, so I can take a whiteboard, sketch what UI I'd like, and have it generate the React component code. You can start imagining a scenario where there's this dark matter of IT and low code and semi-expert user programming. I can come in as an IT developer to somebody who says, I have an app I need you to write. Okay, so we sketch the landing page on the whiteboard. We can generate some React code. And I say, what's the first thing that happened? They said, we should go to the activity database and load all the to-dos. So we go in there. We have this sort of, and I should name this. This is a paper from Onward 2012 called Progging, which introduced that notion of don't write the body of your code, run your code, and pop examples in. So we can go get this Progging thing to say, suppose this was the stuff that came back from the database, right? Just type in some examples. And say, by the way, now how should the UI look? Okay, we can, do the React render. There you go. And, our user says, yeah, that's great. And then you say, okay, now I want to add a new task. So we get sort of a new workflow. And so you can see I've, a couple of rounds of this, and almost within an hour, out with my stakeholders, just walking through doing the requirements gathering that I would have to do anyway. I have the LLM agent in the background. They have a chance to just complete this app, put all these scenarios together, write the code to generate them. The other thing that's very interesting, and it's coming up a lot, is going even further on this, the notion of mixture of experts in these models. So I've always been talking about a model that generates code, right? But then you say, well, look, I have these workflows. So I really want an agent that generates the workflow structure in the application. Then I want other agents that are actually going to go and generate the code within it. And as we go back to this notion of grounding, since we have this nice structured setup, we have this nice structured programming language for how this works, we can go and say, by the way, run a checker and make sure that if I have any unhandled errors in this flow graph, I want you to go and flag these so that we can make sure that we handle them and the agent can then iterate and improve on that. So I think this is an incredible way to bring programming languages to actually make these agents not just smart autocompletes, which they're great at today, but allow them to actually build rich applications, with some supervision, but in a very, very free-form way that really, especially with the grounding, people have confidence that it's doing the correct thing. So I don't see this as being, a threat to PL research that's really going to come in and disrupt and diminish the work we're doing. But I think it's actually an opportunity for us to expand what the view and role and importance of a programming language is in the world, right? It's not just there as sort of a substrate that the agent is going to, write in, but it's an actual tool that it's going to use and is going to make these AI agents much more powerful. I talked about some old ideas, sort of live programming, tactile programming, Progging, static analysis. These are all things we've talked about a bunch, but this is an opportunity for us to show the value in the context of these agents. And I think we should really embrace that. You know, and the work that our community does is critical to empowering these AI agents to really fulfill their potential of being true co-pilot programmers, not just IntelliSense better. And, you know, it's in the name. They're large language models. They work on languages. We work on programming languages, right? So it's right up our alley. Okay, and I think that's was my slide set. So I'm happy to have any questions, critiques, disagreements, whatever.
So you had a few sections in there where you were having a back and forth with the AI agent and providing answers. And I guess this is more of an idea than a question, but would it be possible to instead of providing just prompts, provide the AI agent's best guess as well, and then just have the programmer be responsible for corrections instead of doing the full answer work and have it even faster?
Yeah, I think you're absolutely right. Like, I think we want to move away and, like, I think today Copilot generates a block of code. You have to look at it and say it does what I want or it doesn't, right? And I think the ability to have simpler ways to disambiguate between, because in the background that LLM generates top 5, top 10, top 20 answers. It just spits out one. That's obviously not going to work in the case where there are 2 or 3 plausible solutions, as I showed in my example. So it's when it comes up with 2 or 3 solutions, are there, like, I think you're absolutely on the right track. Are there better ways to disambiguate which one of those is the most relevant and explain to a developer what the different characteristics are so they can quickly and confidently make that decision? I think is a critical thing as you scale. It's one thing to do 5 lines, 50, 500, it's a very different story, yeah.
Hi, it's an interesting talk, thank you. So during the demo, you are giving examples to teach, what kind of code you need to the system. But in the demo, your way of teaching, showing an example was what the code was really looked like a code, right? You didn't, but according to my small experience with ChatGPT, I think it's a better way to use natural language like English to teach ChatGPT, to guide ChatGPT. So for example, to me, when you're showing an example, instead of using brackets and curly braces and parentheses and comma, using more natural English-like sentence would be a better way. But what do you think about that?
I think we're at an interesting point where prompt engineering is quite a black magic, and so I didn't touch on that, but I think that is going to be very interesting to see how that evolves, whether it continues to be a very important skill for the way to get the most out of the model, or if the actual training techniques do a better job of distilling out the fundamental interesting parts versus the strange quirks of, telling it, I'm an expert programmer, to get it to write better code, or, how do you, those are a little funny. And I think the ML community is going to make some progress in reducing the amount of black magic that's needed for that. But I definitely agree. The issue of prompt engineering today is very important in how you phrase these things for ChatGPT.
Yeah, my guess was that because LLM was trained with a bunch of English text. That's why it's easy to understand English language rather than programming language.
Yeah.
But you're expert, so if you have any other
Yeah, I think
that
is going to be interesting as well, because my experience, or our experience has been that multimodal inputs are good, right? Saying the same thing but in a couple different ways. So yeah, I think that's something that needs to be quantified a lot more. I just, right now it's all, I tried this and it kind of worked. It's not the most empirical evaluation, yeah.
Hello, thanks very much for an interesting talk.
I think what I'm taking away from your presentation is that techniques which make human programmers more effective, like test-driven development and programming by example, are also good for AI-based programming systems. So is that a valid takeaway message from your talk? And if so, right, dynamic languages make us really productive, don't they? So is AI better at generating dynamic language-based code rather than static stuff?
Well,
Thanks.
so yes, I think that's the first part. I definitely agree with the statement that you know, if it makes it easier for humans to write correct code, it's also going to make it easier for AI agents to write correct code. I think that's a pretty good rule of thumb that I use. As far as dynamic languages versus static languages, I think this is a very open question. You know, so right now, ChatGPT is very good at writing Python, which is a very dynamic language. But like the example I gave about get being a pure method versus impure method, right? Or having types associated with various things, that gives more syntactic context for ChatGPT to queue on when it's generating code, which in theory should help it. It also gives you a way to run the type checker real quick and make sure that the output is, you know, syntactically, semantically at least sane, which improves the output by pruning after, you know, top 5 generation, and then we filter that list. Now, whether that's an inherent advantage and exactly what features make it a better or worse language for these AI agents, it's a very open question, and I think is going to take a while to sort out. But I'm really looking forward to, you know, getting some more understanding of that.
Hi, thank you. That was a really eye-opening talk. Just to follow up from the earlier point about these models being trained on natural language, I think the tokens they use are basically just characters, right? Or like streams of characters.
Yeah.
And I was wondering if there's any research done in training these models on the abstract syntax tree of like these languages to see if they actually understand these programming languages a little bit better and can generate better code.
So this is why I said I have this bias, because about, let's say, 5-6 years ago, yes, there was a lot of desire to train code completion models on trees and graph-gated neural networks, right? Because obviously you have not just, you know, in the tree you have the scoping and all this structure, but if you look at the graph networks, you can also have data flow edges and other edges, and the model can learn you know, does not have to reinduce these just from the token stream. So it seems like if you had this additional structure, they would perform markedly better. But, you know, basically it is, don't underestimate the power of scale, right? So these models are more expensive to train. And it turns out if you just throw the entire internet at it and, you know, make it really wide, it learns everything that you had in that structure just as well and probably better than your sort of hand crafting of features, and you just lose to it. So this is where I said this is an open question. Well, maybe types don't help at all because ChatGPT is just really good, you know, and people have used ChatGPT to infer types for JavaScript, you know, so maybe it just learns that better than the programmer's type in, you know, annotations would even be, and it doesn't matter at all, and Python's great for that. In my view, I think types are nice, but, you know, maybe scale crushes me too. We'll have to see.
All right. Let's thank Mark again. So after that obscure AI stuff, we are now coming to the fun debugging talk.
Okay, so thank you very much for being here. It's the last talk, and so naturally I'm going to keep this very lightweight, but I still wanted to make a very engaging and hopefully entertaining, inspiring talk. So I read some blogs, and apparently one of the ways to get your talk very engaging is to start with a very controversial statement about a topic that you are going to discuss. So I thought really hard about debugging and what would be the most controversial statement that I could come up with that I can still defend. And so I came up with this one. Debugging is fun and exciting. And so if I look at the room, I'm very happy that this reaction is there, but it's also a little bit sad because it seems to be that most people experience debugging as not fun and not exciting. And so depending on which research paper that you're reading, you will encounter numbers from 40 till 60% of the development time is spent on debugging. And so basically, if you are saying like, well, this debugging is not fun and not exciting, you're basically saying that programming is not fun and not exciting. And being on a PL conference, we should at least strive that debugging should be fun and exciting, right? And so just to, is there something wrong?
I don't know. Continue.
Yeah, and just to make sure that we're all on the same page, I will just describe what I think is debugging and what the debugging process actually consists of. So the debugging process consists of 3 different steps. Namely, you first need to detect that your program has a bug. Yeah? And then you need to go into the code to locate where in the code the bug actually has manifested itself. And then finally, you need to eliminate your bug. And that's hopefully the really fun part, that you are converting your program into a working program. And apparently, this is very difficult. And so the reason why it's difficult is because there can be a very large distance between locating your bug and where you, actually I have another adapter, maybe I can just quickly change it or, well, there is an excellent paper about my hairiest bug war stories that I would everybody recommend to read. So in this case, there is basically a program that he describes that is only working on Wednesdays. So what happened? Basically, the documentation said that you only needed 8 bytes for your day, to store your day, and Wednesday has 9 bytes, right? And then you get a buffer overflow, but actually it was working. Why? Well, the 9th byte was actually being used for user input, and totally by accident, it was reading yes. And so only on Wednesday it was correct. So you can imagine that it's horrible to debug this kind of bug. No? And so if we agree on the debugging process, then actually for this presentation, I'm going to assume that the debugger is any tool that can help you with the debugging process. Okay? And so there are many tools developed, going from delta debugging, back-in-time debugging, machine learning techniques, and so on, that help you in this process, right? But if you go to a developer in the wild, he's not going to come up with these kind of examples. What he's basically going to tell you is some kind of vision that comes from the 60s, right? There is like this excellent presentation, The Mother of All Demos, by Douglas Engelbart, that describes a system where you can already step into, step out, and so on, all the things that you are that you know from Visual Studio Code, for example, right? But it's actually even a little bit worse, the situation, if you just ask the average developer, because all these debugging techniques that I've shown here, together with like the older debugging techniques that you have, they have one fierce competitor that can actually compete with all these kind of debugging tools. Print. So print versus all other debuggers, which is which is actually, you might know this anecdotically, but there is actually a research paper that actually posed this question to more than 100 developers. And so they also investigated other things, but one of the statements that they were actually asking to these developers was the best invention in debugging is printf. So I'm just going to quickly summarize the results of asking this or posing this statement to the developers in 3 categories: the good, the bad, and the ugly. And so printf, the good, is that there is some evidence for disagreement. And that basically means that there are developers out there that think that printf is not the best invention for debugging. And then the bad is that there is a strong partial agreement, which is kind of that you can that is being explained by the ugly. So many developers think that from the moment that you have a difficult to debug program, for example, with concurrency and so on, that all these debuggers, that they interfere with the actual base program. And so if you are using these debuggers from the 60, that's true, but like all these different techniques that we have been developing actually really make sure that this is not the case. You know? And then, which I also find very ugly, is that some developers, they are like, well, of course, I'm not using printf for debugging. I use structured printf, which basically boils down to logging. And so from a software engineering point of view, that's true. It's better to log than just put printf through your whole program. But from a debugging point of view, this is not debugging, right? There are much better tools for that. And so this begs the question, why is it that these developers think in this way? And so if we go and look at the IDE usage today, we see that Visual Studio is clearly winning. And so if we go back to when the study was done in 2018, then we can find on GitHub that just the action of starting the debugger was very problematic. So there was a bug report in 2017 that basically said, like, I don't know how to, I cannot start the debugger. And then luckily that was addressed almost a year later. In 2018, it became much easier to start the debugger. So it already starts with how do you start a debugger? And then when you have the debugger, it seems like they are not very sophisticated in these industrial tools, because most debuggers do not know about while. You know? And so while has been invented for some time now, and if you are a developer and you want to debug your program and you encounter a while loop, one of the actions that you would find very normal is that you can jump out of your while, for example. And so I also found this to be one of the questions on Stack Overflow, and the solution is, there is a solution for that. So basically what you need to do is you need to put a breakpoint after your while loop, and then while you're in your while loop, you need to disable the breakpoint, and then you press play, and then you jump over your while, which is a way to do that, but you would imagine that like modern debuggers sculpted for your language would be able to offer you this kind of functionality. Okay, so that's based on the language, and then I'm going to still show you one small example. This is the Inside debugger for writing CPU programs. And so I'm going to zoom in on one particular point where there is a threads view. And so you see this list of threads. Well, in the Inside debugger, you get approximately 16,000 of these, and you can manually click on it. And so basically what this boils down to is that you're transforming debugging literally into finding a needle in a haystack, because you need to go through all these threads in order to know where the bug actually is. Okay. And I kind of want to give a positive message, and I only have been saying actually things like, well, the industrial debuggers, they are not making use of all these kind of things, but that also brings like a huge opportunity, because with the PL community, we have been developing all these different kind of techniques in order to help you with debugging. And so I was lucky enough to be working with some people on several of these techniques. And so I will kind of highlight some of these next generation debuggers on 3 different topics: non-determinism, resource constraints, and temporal and event-driven programs. Okay, so I'm going to start with multiverse debugging. And basically, this is a technique that we did with people from Kent University and VUB. And so what this basically gives you is a way to debug non-deterministic programs. And so instead of just showing one execution trace, a normal debugger shows one execution trace, we decided, well, wouldn't it be cool if we make a debugger that shows all the execution traces? And so this is a small example in the context of ambient programming. So this is a small actor language that we modeled. And so you basically have a model where actors have objects, and so these objects, they can have references to other actors, and then you can send messages between them, and you can get a result as a future. Yeah? I'm going to highlight one small example, which is of course constructed so that it's easy enough to show during the presentation. So we have three actors, a math actor which has 2 methods, double and get result. And then we have 2 clients. The first client sends a message double with the argument 12, and then gets the result from the math actor and prints it. Right? And then we have an annoying client 2 that is also sending, for no particular reason, double 33. Yeah? If you have this kind of system, you can get different kind of interleavings. Namely, client 1 can send double 12 first, and then the client 2 can also send double 33. Yeah? And then it's going to go wrong, because basically what client 1 is going to get as result is the number 66, because the interleaving of the client 2 was in between. The other 2, they are correct, because client 1 sends double 12 and then gets the result, and then the last is client 2 first sends double 33, then client 1 sends double 12, and then you get the result. And so we consider these also to be what you actually want. And so with multiverse debugging, what you actually can do is you can execute this program and you see all the different states. And so the red states are the end states, that the end of your program, and you also immediately see that there are three different interleavings. So we actually did this in a rather formal way, and I'm not going to go into details about this here, but basically what's interesting about doing this in a formal way is that we have like a recipe in order to debug non-deterministic programming language semantics. So first you define your semantics, and then what the paper describes is that you can actually embed your language semantics into the debugger. And so if you do this according to the way that we have described in the paper, you get a debugger that is not interfering with the base semantics. Okay. And then some of you might be here like, well, you just showed like this example from NVIDIA Insight that shows 16,000 threads. Basically, you're doing the same. You're just now showing a bunch of nodes, and they can explode, right? Yeah. So what we also did is we defined a query language on top of our debugger that allows you to prune this trace. That's the first thing. And then the second thing is that this is actually an interactive debugger. So instead of showing the full execution graph for bigger programs, it actually allows you to go into certain directions. And then, of course, it's up to the debugger, the programmer that is debugging, to explore certain parts of this space. But what's really important is that we give the developer the tools to see these states, because a normal debugger will just show you one execution path, and you will have to rerun your program in order to find your bug. Right? I think there are lots of opportunities, and I'm also really happy that this idea of multiverse debugging is actually being picked up by other programmers, researchers, I mean. And this morning, actually, there was a paper that actually defined different kind of breakpoints for multiverse debugging. Okay. But there is still a lot of things to do. For example, state explosion, it's not really solved, right? There are techniques to make it better, but we still have lots of problems. Okay, let me go into the next kind of debugger for resource-constrained devices. So for resource-constrained devices, the story is exactly the same, right? We found that many embedded developers just use printf. And that one other technique that in embedded systems which is used a lot is that you just simulate the device. But from literature, we know that the programmers like to debug on the hardware because there are just some things that you can only find out if you're debugging your embedded device live. And so there are, of course, techniques in order to debug embedded devices. It's just a kind of remote debugger. And so how does this normally works? Well, you have some kind of debug monitor running on the device that is talking to your developer's machine, and then it basically instructs like how the virtual machine that is running on the device needs to step through. So the disadvantages of remote debugging is that the debugger is actually running on the microcontroller, and you need communication with this device for each of the debug instructions. So you can imagine that it becomes quite slow. So we got some inspiration again from people from the VUB, which is called out-of-place debugging, which was a technique that was invented for big data applications. Yeah? And so we kind of took that idea, and the basic idea is that instead of running everything remotely, that you're actually going to run it hybridly. And so you're actually going to execute part of your program on the developer's machine instead of on the microcontroller, and then you're going to communicate with hardware only in certain spots. So we call this location-independent and spots in your code and non-transferable resources. So where does these non-transferable resources come from? Well, your microcontroller is connected to sensors, and these ones you cannot just move them to. You really need to talk to the microcontroller. And so there are actually two kinds of ways in how you can do that. One is pool-based, which means that the developer's machine is going to ask, like, what is this certain sensor value, and the other one is push-based. And that actually means that the microcontroller is going to send values to the developer's machine. Yeah? And so we work this out, and then we have an event queue which actually is going to run part of the program on the developer's machine and is going to execute only those things that it cannot transfer to the developer's machine. So what did this give us? Well, actually, what we did is we made a Visual Studio plugin which allows you to debug programs written in WebAssembly on our virtual machine. And as an example of the kind of things that then you can actually get, we implemented back-in-time debugging. Yeah. And then one small thing that I also would like to highlight: whenever there is an event coming in, instead of executing all these events at the moment that they come in, while you're debugging, you can actually just queue them. And that's also very helpful because then you can choose a good interleaving in order to reproduce your bug. Yeah. Again, here there are many opportunities. We haven't explored, like if you have groups of IoT devices. We also don't know how to do this debugging on IoT devices which are remote in a secure way. And then, of course, we could also think about making this debugging infrastructure more performant. Okay, so after looking at non-determinism with programming language semantics, looking at resource constraints, then I thought like, well, let's make one ultimate challenge, and let's make a debugger for a multi-threaded language with a message passing interface, with event-based graphic applications used by millions of programmers, and then with programmers who actually do not have a computer science background. Can anybody guess which language this is? Close, but it's actually Scratch. The Scratch programming language, it's actually a very weird kind of language. And so in order to debug this, we needed to think about an interface that makes it easy for children to use the debugger. And so what we came up with is like we introduced, so for people who don't know Scratch, it's a block-based programming language. And so we introduced some blocks in order to allow children to debug with blocks. And then what I call the YouTube interface. Whenever you are running your program, you can actually just make a recording and then go back in time. So I'm just going to show a very... no, I'm not going to do that. Sorry. So if you want a demo of the system, you can talk to me later. So we actually evaluated this with a bunch of children. We gave them some task in order to debug, and then we actually got some quite good results because most of the children really liked the debugger. And just to give an anecdotal example, there was, after the workshop, there was a kid that had been debugging his application for almost a week. And then we attached our debugger and we went through the program, and I don't show Maxime completely out of privacy reasons, but I can tell you that while we were debugging it and we found the error, that this kid was extremely excited to have finally found his error. Okay, so for opportunities here, well, we only explored like one kind of advanced debugging technique, and there are other research groups busy. There is with Scratch. There is on the ICSI conference, for example, Nuzzlebug, which is where you can ask questions about your Scratch program. For example, like if you move a ball, you can actually ask like, why did a ball hit something? So if you're interested in this kind of research, you should really check out also that work. Okay, so let me round up. I really think that debugging should be fun and exciting. And so I have like 3 kind of suggestions of questions where I think as a community we can think about. And so one is programming language design. Instead of looking at debugging as an afterthought, wouldn't it be great to shape your language so that the language actually makes it that debugging becomes easier? I don't know how to do that, but it would be extremely beneficial. And then how to formally define debuggers and their proofs for correctness, because if you read type systems papers and so on, we now know how to prove type systems correct. There is like progress and preservation, but for debuggers, there is of course formal research about that, but there is not such a widely known technique to prove the correctness. And then finally, many of you are in an educational role, and so I think it's really it would be beneficial to think about how to teach debugging, because most curriculums, they actually do not teach you how to debug. And so if you are interested in knowing more about this, you can check this book by Zeller, and it's an excellent book that explains you how to teach debugging. So to really round up, I'm going to give some, I'm going to make some advertisements. So this year we organized the depth workshop together with Elisa, and so we got actually quite some people. There is somebody from Japan, which is remotely there, and so we are going to organize depth again next year together with eCube. And so I want to just stop the presentation or finalize the presentation with a with a call for action. So let's make debugging fun and exciting again.
Who got a question for Christoph?
I guess I'll go. So I actually had worked with the Chakra JavaScript engine team in about 2015 when they were doing their time travel debugger. And one of the things I found really interesting, JavaScript. So, people love printf debug, console.log, same thing, right? One of the things that was really interesting to me when talking to people about why they use that as their debugger, and that was the first thing they reached for, that two things came up. One was, this is a live incident. I'm trying to fix the bug now. I don't have time to learn to set up and use the debugger. So I'm going to use what I know to solve the problem quickly today, even if it's not optimal in the long run. And so we ended up doing, and I've spoken with some other people, that do time travel debugging work. And this adoption really has had most success when you integrate it at other points in the development lifecycle, like flaky unit tests, CI pipelines, other things. I was wondering if you sort of had experiences in that area, or what your thought on that was. Like, not just thinking about it as debugging, but as a tool generally.
Well, I partially already said that I think it's really important to educate people on debugging. And so I think lots of times outside of debugging, yeah.
So basically, I got the version of, I don't want to learn a new tool. It's not exciting. I need to fix it right now. So you had to kind of sneak it in somewhere so they'd start using it and say, oh, this is really cool. I learned it. Now it was in their toolbox. But if you went and said, let's learn about debugging, people were like, nah, pass. I don't know why, but that's a very strong signal we got there.
Yeah, but even on the debugging workshop that we organized, one of the topics that came from the discussion was, well, I don't like debugging. So you would imagine that people submit papers about debugging, have some kind of affection for it, but even there, we actually saw that some people were like, let's make automated debugging tools and so on. And so I think it's our job to show that if you use the debugging tool, you get some benefit from it. And I fear that many of the tools that are being generated in general, for example, Visual Studio Code, they are not making a specific debugger for your programming language that is going to be the most valuable for you, right? And it's normal because they are an IDE, and so what do they do? They develop an interface for all different kind of languages, and so you end up with like the greatest common denominator, and you get a step into and step out, which we kind of know from the 60s. So I think you should show value to the user, and then adoption will come, hopefully.
And get the users very early as you do.
Yeah.
I was the second, but you already answered my question, actually. But maybe you have an additional insight into it. I was wondering, there is obviously, this was very interesting, thank you, and there are things happening in the academic community in terms of like extending debuggers, writing debuggers that help you debug different things. My question was, why doesn't it end up being adopted more in the industry? Why don't people, to your answer, which is that there are these IDEs that cater to multiple different languages and have to have uniform interface. Surely there are languages that are popular enough that there could be a specific IDE for this language that could incorporate some of the debugging techniques that are more interesting, and I don't think there are. And again, why do you think that is?
So why do I think?
Why do you think that there are no industrial applications for more interesting debugging techniques that are obviously being developed and currently being developed?
Well, I kind of answered the question, yeah. But yeah, I think from research we should show value, and if we do that, I think industry will follow.
So maybe this is the point where I step in as an industry representative, and my colleague here and I have been talking about this a bit, and we use debuggers very extensively. In particular, RR, the time-traveling debugger, is the tool I use daily that makes me feel most like a wizard. And Matt is a very heavy user of Pernosco, which is the sort of extended web-based interface to that. And so at Mozilla, we actually make pretty good use of time-traveling debuggers as a means of capturing and then exploring intermittent bugs. And one thing that we have done, which may be a partial answer to how do we integrate this into the rest of the process, is that we have the ability in our CI system to capture a Pernosco trace of a task that is failing in an attempt to then grab something that we can then debug. And so we have tried to take these tools and like actually build them into useful things that like fit into people's workflow. And I mean, I think time-traveling debuggers are incredible, so do more of that.
I would go one step further, and I would actually argue that in your undergrad courses, if you were teaching C and C++, and you do not teach time travel debugging, or Pernosco, which is omniscient debugging, I think you're committing malpractice, because it is an actual, like, it is incredible, the difference in power. And if anybody wants a demo of Pernosco, I'm totally willing to show, because like I'm literally quoted on their front page as one of their customers. But like this is the biggest productivity improvement that I have at my Access, and I want to see more of it. You know, I get incredibly annoyed that Microsoft and Apple have not like built something of this level of power and made it like totally available everywhere. Like, okay, Pernosco's UI is terrible. It's designed by computer scientists. Like, sorry, we're all bad at it. But like, it is, like debugging tools have gotten a lot stronger, and teaching debugging as here's next in printf is bad. Stop doing that.
Any more questions, comments?
Okay, just a comment why I'm using printf and why I will keep using it is...
No. We should see all sides of the story, right?
I'm building compilers, and when at the third round of bootstrapping my compiler I have an error, then the debugger is just of no use. Okay, when at the first time of bootstrapping your own compiler, your compiler crashes, what can you do with the debugger? The error was 3 times sooner, and then you have no execution at hand, so you cannot debug with the debugger. It's too late. It's way too late.
Hi, interesting talk. Thank you. So I think it's all the debuggers we can use today are basically tools for visualizing what's going on on the machine. That are not really too directly to help debugging, because you know the work the debugger does is just visualizing what's going on. It doesn't help, right? It doesn't give any hints or directions or no guides. So, do you have any ideas, possibly whether we can get some much really debugging tool, like, which helps, you know, what's next you do?
So I have not personally been involved in these other kind of debuggers, but basically what I think is that we should basically use static analysis tools in order to guide the debugging process. And so there are, from that perspective, we have developed many tools in order to get more automated debugging, right? So like for example, you could use symbolic execution to guide where you have to go. You can generate coverage tests for your application and so on. And I consider all these kind of tools as debugging tools. So I think there is plenty of this kind of research.
So you showed us that you're interested in resource constraint debugging. Do you also have some ideas on the resource abundant debugging? How do you debug 1 trillion actors?
I should think about it, but it's a nice remark. We can talk about it later. I don't have anything from the top of my head.
Hello, thanks for your talk. Do you know algorithmic debugging? And I think the way like interact with the debugger is better than just time travel debug, next step or last step. So is there a way to combine this? It uses the time travel technique and ask users some questions. Is this right? And the debugger will tell the developers we should go next or go back. Or do you know some interesting work after the algorithmic debugging? I know little about this, so.
So actually, the debugger that I showed you, well, that I showed the reference from for Scratch, is kind of combining these things. So it is actually reasoning about temporal aspects of the Scratch programming language, and so you can basically ask questions like, this ball is colliding with some other sprite. Why did that happen? And so instead of actually having to go into a back-in-time debugging, it actually is going to tell you in the code, well, because at this point in time, this code is going to be executed. This is why they are going to collide in the future. So it actually already incorporates these temporal aspects. Yeah.
All right, let's thank Christoph one more time. So before you all get up and leave, I have a small conclusion for today's DLS. And we are mirrored, very good. And so, as I said at the beginning, the Dynamic Language Symposium is typically research papers that you guys submit. This year we did at the roughly 20-year mark, slightly different thing to look a little bit forward, and the room was pretty full, so I thought a lot of people are interested and enjoying it. I want to thank the program committee for helping to set all that up. I want to thank all the speakers, of course, and the session chairs as well, so perhaps a hand of applause for everyone involved. And before I close, I should really end on a very positive note. So every year we have a committee of 3 people. It's typically the last 2 PC chairs and then the PC chair of 10 years ago, who select the most notable, which is not necessarily the most highly cited, but what these 3 people thought was the most interesting and noteworthy paper from 10 years ago. So this year, the prize goes to Cast Insertion Strategy for Gradual Typed Objects by Esteban Allende, Johan Fabri, and Eric Tanter from the University of Chile. And let me read out the citation. This paper explores the cost, both at the micro and macro scale, of various strategies for protecting gradual types. And we heard about gradual types a little bit today. In a gradual type programming language, examining how different strategies affect untyped, typed, or both components of the code. It's a seminal contribution to understanding the performance of gradual typing, which since then has been an area of important research. The strategies used in gradual type languages today can trace their lineage back to the strategies described and proposed in this paper. In particular, the proposed hybrid approach has been adopted time and time again by many systems, giving this work a lasting impact beyond its original scope. So congratulations to the authors. I believe at least Eric is watching online, he said. So, okay, so on that note, DLS'23. We're not quite sure whether that's going to be happening. I think if it's happening in LA. But it very much depends on you guys. So we have had, I counted about 100 people here. If only a tenth of you submit papers, we will have a very exciting program. But we have to see about that. So thanks everyone, thanks for coming.
Can I interrupt for a second? Because this year we had so few submissions that a bunch of us were skeptical about organizing DLS, but I think that Stefan insisted on having a DLS, composed the entire program, did all the work. So I think we should thank you for organizing this.
All right, enough clapping. I don't think there is a coffee break anymore, but there are posters upstairs from 5:30.